Hello everyone and welcome to the Third Joint Egocentric Vision workshop, or EgoVis 2026 for short. Normally, this is a reasonable way to start, and this is what I would have said. Here's some increasing trends of papers in the egocentric world. On the y-axis is papers or something, whatever you care about. And typically this is what I do, but last year has been relatively wild in general. And so instead of looking at these kinds of trends, I thought it's worth looking at just what happened since last year CVPR in this space. And plenty has happened. If you look at big companies are now finally realizing that this stuff is important. They've always known it's important to some extent, but they've sort of relegated a lot of it to research prototypes and initial products, whereas now we're seeing Meta's put out glasses with heads-up displays on them. Google in just last month announced these new AI glasses. And so there's a large push really for these wearable devices. And then here's another one that caught me off guard. These guys dropped in the marketplace just last year. And now if you look at, for just a bit more than the cost of an Equinox gym membership, you could be the proud owner or at least renter of one of these humanoid robots. Or if you want to buy it in full amount, then this is about the cost of one semester of tuition for a PhD program in the US. But the fact that you can own one of these right now really puts egocentric vision in center stage, and it's a little bit crazy to me. This happened sort of overnight. We're also starting to see news articles pop up about its importance. Here are two recent articles about how smart glasses are unlocking the independence of visually impaired individuals, or why surgeons are wearing the Apple Vision Pro in operating rooms to help guide through procedures or to help training. This is a slightly older article from 2024, but you get the point. And then more importantly, I think we're also seeing the flip side of this, where for the first time, we're seeing actual legislation come up to combat the risks of egocentric vision. And you can do your own Google searches to figure out the various lawsuits out there. And the corresponding legislation, which was before thought of just sort of shouted in the darkness, whereas now there are actual bills that are being proposed to target this. All of this is to say that egocentric vision now is more relevant than ever before. And this is a good thing. And there's no better place to be talking about it than this workshop. Underpinning all of this, of course, this is the sort of the consumer-facing public outlook of egocentric vision. Underpinning all of this is the research. And so we've seen data sets starting in 2021. Ego 4D was 3,000 hours, and at that time was an unprecedented volume of data. Fast forward to 2026, and we see data sets like Ego Scale, and there are plenty of other ones that are just orders of magnitude more, although maybe their scope is a little bit different, but it's still order of magnitudes larger volume than what we had before. Along with data, we're seeing bigger and badder models pop up. And so if you look at recent papers that say egocentric foundation models, whatever that may mean, it might mean different things to different people. Some people might get upset. But you see this becoming a trend where now you need more data, you need more compute, and it's targeted specifically to the egocentric perspective. And this is a reassuring sign. On the right is a real bar chart, I promise. These are paper titles in the last cycle that just include ego. And so these are just paper titles. The real number of actual papers about egocentric video perception is more closer to 300 or something. But we see an upward trend. And the dark bar over here is just papers that have the ego prefix, so Ego 4D, Ego Scale. And it's doubled since 2025. And so if this trend holds, we should have about 1 million papers in 16 years. Don't worry about the logic, it's airtight. So yeah, what better place to do this than the EgoVis workshop? We have a really good schedule prepped for you. Here's the workshop, scan the QR code, bookmark the link. We have keynote speakers, 6 keynote speakers that cover a whole spectrum of areas in egocentric vision and surrounding it: robotics, fine-grained activity understanding, procedural understanding, 3D, you name it. We have challenges. We have a rich history of hosting challenges and awarding prizes to these winning solutions. So there'll be a session dedicated to that. We have the EgoVis Distinguished Paper Awards, which we've been doing for a couple of years, where we recognize the most impactful set of papers in the last couple of years, the last publication cycles in the egocentric vision space. We have poster sessions and oral talks, and then we have a panel discussion, which is going to be a bunch of the keynote speakers as well as some other speakers that are going to answer difficult questions, hopefully spicy questions that I've prepared for around these areas, around the challenges, the risks, the good things, the bad things, all of the above. I will say we are now at 10 years of these egocentric vision workshops. They've been known by various names in various editions, starting from the Epic Kitchens workshop all the way to the EgoVis workshops. And in the spirit of unifying models into these gigantic foundation models, we're also unifying workshops and workshop names. Hopefully that'll go well for us. And so, with that, here are your workshop organizers: Siddhant, Masashi, Chiara, Antonino, and me, Tushar. If you see us around here, give us a thumbs up for all our hard work. Big thanks to the co-organizing advisors, the sponsors, Google DeepMind, and camera support from the ARIA team at Meta. And with that, I think it's a good time to kick off.
So I'll talk about egocentric vision, actually both for applications to assist humans, as well as also towards enabling robots to get stuff done. Here's a little bit of an overview. I'll talk about a number of different topics. First, I'll talk briefly about Lamaria, which is an effort we've been doing with the ARIA team on benchmarking SLAM. And realize that for egocentric vision, there's still a lot of challenges out there. And so we're trying to essentially, make this benchmark so that these kind of, it opens up the field for further research, in particular the methods that are publicly available, or like academic methods and so on, really don't work well on many of those settings. And so there's lots of work ahead. Then I'll talk a little bit about egocentric action recognition to assist a human and understand what humans are doing and assist them. Then we'll talk about CoMind, which is an ongoing effort on having multiple agents with egocentric kind of perception kind of interact with each other, and essentially we're trying to understand that interaction and use foundation models to kind of understand the joint attention and how they're interacting and so on. And then there'll be a few works on things we do in the space of robotics, of using egocentric vision to enable robots. Okay, and I apologize already for the slides being a little bit rough and so on. This is where I was last week. I organized this workshop, and you can kind of see a little bit, some of the folks that were there. It was a great workshop, but that's what kept me busy the last many weeks. And so this was all a bit last minute then for preparing for CVPR. And somehow I was silly enough to accept too many workshops. Okay, so that being said, so essentially my lab in general is really focused on spatial AI. And so you'll see here the teams that are focused on egocentric vision. But more broadly, we're essentially, and egocentric vision fits very much into this, is becoming a bigger and bigger component of that. But it's about understanding the world from sensors to assist people and enable robots to interact with the world. And for that, we often try to understand the three-dimensional world. So I've always been interested in moving cameras, and there's no more interesting camera than a camera that moves with an actor through the scene. In other words, egocentric vision. You see here a few of the different platforms that we're working with. And also what we're trying to do is both reconstruct geometry, but also semantics, affordances, et cetera, et cetera. Okay, so first on the localization side, for many of those applications, if you want to do something useful, you want to be able to assist a human in doing something, the first thing you have to do is somehow keep track of how you're moving through the environment, what you're looking at, and assuming you are in a non-trivial environment with a lot of kind of relevant information that relates to that environment, you typically start by being able, by the need to be able to keep your, to keep track of where you are and what you're looking at, and so be able to essentially localize yourself and map the environment. So that you can also keep extending and updating the environment. Okay, and so typically this is a question of finding your 6DOF pose on Earth, particularly so that you can retrieve then, as you see in this scenario here, which is a bit an older scenario, you can retrieve the information in context. Okay, so what are the challenges of egocentric augmented reality? Typically your sensor, like a head-mounted display in particular, or head-mounted display and therefore head-mounted cameras, can move widely, as you see kind of on the right. There's quick changes of environment, as we'll see later, also change of illumination, changes, all kinds of challenges that show up. Okay, and if we're talking about AR, much more than many other scenarios, we really need ideally pixel perfect alignment between our digital display, augmented reality display, and the physical world, right? So if I'm in a place, I'm a technician, and let's say in a nuclear power station, and I have to press a particular button, and my assistant, my AR assistant is telling me which button to press, it better points to the right button and not, one or two buttons to the right or to the left, right? Okay, so in many cases, it's really important to have this really precise alignment. Okay, so we did a benchmark a few years ago. It was called LAMAR, Localization and Mapping for AR. And we captured a few environments in Zurich. So the CAB building is it's actually the computer science, the main building of the computer science building at this point. The HGE building is actually the main building of ETH, with that being the main income hall. And then Linn is Lindenhof. It's a district of Zurich with cobblestone and mostly pedestrian, so it was easy to record data there. So it's a mix of indoors and outdoors, and essentially we captured, multi-camera rigs, both headsets and wearable devices. In addition to the images, we often collected depth, IMUs, radio signals, and other things, and then we got ground truth reference data. Okay. And so we built up a whole pipeline. We had anonymization for faces, license plates, all that kind of things. All in all, it was a very complex pipeline, complicated. This actually became a lot easier with the ARIA pipeline now. Also, the custom stack that we had built to record the data had a number of challenges. Again, here, ARIA was super helpful there. In particular, also blurring faces and license plates. We had a dedicated system set up for that. Also there, Ego Blur is essentially an off-the-shelf component you can use. Also, we had limited access. Sometimes we had access to those, but not, HoloLens has an IMU, an iPad has an IMU. You don't get access to the raw data, okay? And so it's already pre-processed. There's some kind of, you don't have full control. There's a challenge if you actually want to enable people to actually develop VIO algorithms, you actually need to have them be able to work from the raw data. That didn't work with those platforms. You can do lots of things with those platforms, what we recorded with Lamar, but if you really want to test VIO, it doesn't actually work. Okay, so with ARIA, we're actually able to collect all of the raw data. And then we have a really nice, or the ARIA team has a really nice SLAM system, offline SLAM system on the machine perception services that you can access in the cloud. Okay. So we continued, and the key challenge that we wanted to do was really to scale up the kind of visually inertial SLAM trajectory estimation. Within a building, we only have a limited scale. People typically, when they want to test visual inertial odometry algorithms and so on, if they want to test long range, what they do is they start here, they do a huge loop, and then they come back to the same location. But you always end up in these situations where you only test really accuracy at once you close the loop, and this creates a number of these biases, essentially, what you can really do. Okay, so here we wanted to, our goal was to be able to have long range over multiple kilometers of walking, tens of minutes or half hour of walking or more, be able to have these really long trajectories without kind of just resorting to closing the loop. We wanted all along the trajectory to actually have ground truth accuracy, and when we say ground truth, we essentially wanted to have, at many places along the trajectory, centimeter accuracy, at least some control points at centimeter accuracy, and the whole trajectory is in the kind of decimeter range globally at every possible kind of frame. Okay? We also wanted to handle challenging scenarios in terms of low light scenarios, transitions from indoor to outdoors, which is something that's often ignored, but it's a huge challenge. Back in a time with the HoloLens, if you went from inside to outside or so, you would systematically lose track, typically. So there's real challenges there. Also moving platforms. This is something that there are some solutions, travel mode in some of those VR settings, or on HoloLens there was a moving platform mode, etc. But it's actually still a challenge. What are we talking about? Well, a moving platform is essentially a place where you are inside a platform and visually you are seeing the inside of the platform. And but inertially you are sensing the motion with respect to the world. Okay, so visually you see the motion with respect to the platform, and inertially you feel the motion with respect to the world. This is essentially why we get motion sick in vehicles, or we can get motion sick on ships, in a car, etc. And so this is actually also a problem for all of the VIO systems. Okay, and so we also integrated some of those challenges in there. Here's a little bit of a video. So we have in total 86 sequences, just kind of showing you one that's aligned with high precision aligned to the world. The only problem is that in this video is that Google Earth is actually not high precision aligned to the world. So you'll actually see some offsets here where we walk through some things, but that's actually due to Google Earth, actually partially on purpose, not being centimeter accurate localized. So here we show you all these dots essentially correspond. So these are all the trajectory. All these dots correspond to ground control points. Let me go through this here. So we have long sequences. We have these moving platforms. So trams in Zurich, we hop on and off the trams. We also have this thing that's called the Polybahn, which is a funicular that's very popular to go from Central, which is near the main train station, to ETH, which is a polytechnic university. And so that's where Polybahn comes from. And so we essentially had all of those trajectories also integrated in our challenge. This is how we get the control points. So Zurich has lots of control points already established by the city. We decided to kind of validate a lot of those control points. So we had actual survey equipment to go control them and validate the accuracy. So most of those are publicly available. And as you see, this is done very carefully. This is how construction and other things are essentially based off these reference points. And so we also leverage those. Okay, and how did we leverage them? So I think I had a picture here before. We essentially, as you see in the picture here, let me try to get the cursor to wherever the screen is. Here we go. So you see here, so every once in a while we look down, and there was a second person that would walk and place this kind of this marker centered around the control point so that we can have a very accurate localization in the images. And then we have an accurate localization in the world of that point, and that allows us to register the trajectory to the world at centimeter, within a centimeter, essentially, in those locations. Okay. So here was how we checked the survey. So we borrowed this from our colleagues in the civil engineering department to do this. This overlaps with the original Lamar data set. So this is the computer science building, the ETH main building, and then this is this area of town, pedestrian area of town. But now we have all these trajectories in between here that we carried. Okay. This is just a little bit of how we were doing. So essentially the ground control points, they're centimeter accurate. And then by registering to those and having the trajectories corrected to align to those, we get essentially this decimeter level. 10 centimeter or so accuracy on the whole trajectory. This is a little bit of a comparison to other data sets. The kind of closest one was the Lamar data set, but we essentially make it larger. We have the raw IMU access, we get essentially also more accurate accuracy and much longer trajectories here, as you see. Typically, Lamar was very short data sets, and here we get very long trajectories. And we have all of these additional challenges here in dynamics. So here's showing you a few of those videos of people walking around. And so notice the egocentric motions are actually often quite challenging compared to, let's say, doing slam on a vehicle that drives, mostly straight, and the camera is always at the same, location with respect to the world, with respect to the road, etc. So much wilder motions. Even drones are actually much more stable, typically. So here you see some of the challenges. So some of the existing state-of-the-art methods here. You see that they quickly start failing as the motion pattern becomes more natural, head-worn kind of data sets. Okay. He's showing you a few of the kind of all the things we compare to. By the way, in a sense, we actually had to delay the submission once we realized how bad the current state of the art was in the public methods. We ended up actually delaying it by one deadline because the table just looked too bad to be able to publish. So we had to, in a sense, a little bit dumb down the benchmark. In particular, in this sense, we segmented it in short sequences, medium sequence, long sequences, and then additional challenges. Because the overall numbers here, the average numbers were a disaster, but at least for the short things, there's some signs of life of the existing methods, right? But if you compare to what AryaSlam is doing, there's a huge gap. Okay, so you can see it here. Of course, AryaSlam also has challenges. Doesn't work everywhere, and as you see here, it only works 50% of the time, and so on. But the other methods really completely fail here. Where in this case, in some of the regions, they do something reasonable, but they're still struggling. Okay. So if you look at open source, there's really nothing that works really well at this point. Okay, so this is an encouragement to all of you students here and so on. There's actually work to do here. This is kind of showing how things get harder, especially if you actually want a reasonable accuracy. Okay, even for short sequences, a good accuracy is actually really, really hard at the centimeter level. Here's some of the challenges with moving platforms. So this was, these trajectories. Even for Arya, it's still a problem. So we're currently looking at extensions. We're actually working on extensions indoors. So specifically, we've surveyed some of those buildings. So you could say we already did this with Lamar. With Lamar, we just used this high-end laser scanner as a reference, and then whatever the reconstruction, which has loop closures and everything included, whatever came out of that NavVis system, we used as ground truth. In this case, we actually went back, resurveyed and surveyed actually ground control points so that we have an alignment between the outdoor physical world, so the outdoor sequences, and then the buildings are now at the centimeter level registered to between the indoor laser scan and then the outdoor ground control reference points. Those have been surveyed, and so they're aligned. And to do that, you actually have, so this is the survey networks we measured inside the buildings. And then the NavVis system, this is the newer NavVis, backpack NavVis system, laser scanners. You see laser scanner here and here. This one is more to localize you. This one is more to map the walls and everything. And then high-end cameras and everything. But there's also a reference point down here. And if you measure the ground control reference point, you can actually take off the backpack, place it on it, and actually get an alignment between the NavVis system and the ground control reference point. Okay, so we got everything in the same coordinate system for our ground control reference points. Or that's ongoing work, essentially. That's an extension that we're currently working on. Here's some of the challenges with visual and visual inertial systems. So visuals, low light, sudden illumination changes, entering and exiting rooms, switching on the lights. These all causes huge problems for visual tracking systems. Notice also if you enter or exit, so if you enter a room, typically as you enter the room, you get straight in front of a door, which closes, which essentially fills most of your field of view. The door is typically textureless, and then you open it, and then the one thing you were still seeing that was occluding most of everything else Now it starts moving. And so these are actually things that actually make it really hard. It's kind of the reverse visual inertial confusion. Now the visual world is actually moving, kind of the door is moving, and that's most of what you're seeing. So those are actually also real-life practical challenges. Other things are elevators for visual inertial, for example. You're in the elevator, you are in a small box, nothing moves, but inertially, of course, you're moving, you're going up and down and so on, right? There's a few other scenarios that are actually also challenging, okay? Okay, so I should actually move faster here. So now onto interactions. So this is where we started with egocentric vision. So I entered egocentric vision in many ways about 10 years ago when I started working on the HoloLens at Microsoft. These were the scenarios we were thinking of. It's really scenarios of assisting people, getting maybe a remote person to assist a local person, be able to align things to the world, as you see there. Also be able to give tutorials to people. So for things that many people have to learn, you would build up tutorials like this here. Again, you need the kind of precise alignment to the world. We started building, capturing scenarios from egocentric viewpoints. And, so you see the hand here was captured and it is displayed to kind of illustrate like what the person should do, how to make a coffee. That's the machines we have in the office, or printers also. So in this case, we do action recognition. We actually segmented the procedure in 5 tasks. And so the system is now able to follow along. So it might give you a tutorial or you've been instructed and now you have to validate that you actually know how to do it. So the system can follow along and, as in this video, can correct you if you would do something in the wrong order and make a mistake. Like here, grabbing a new cartridge without having taken out the old cartridge, okay? So this was the early work we did in the space on action recognition. But let me skip through that. We also then went to 2 arms and collected data sets. This is Tain here, Tain Kwon, who, we mounted the Azure Kinect instead of the HoloLens, in this case, because we could very precisely synchronize this together with the exo views at the same time. I'll actually skip through that. We've also started, I'll talk more about this in another workshop, collecting not only visual, but also sensor, touch. So this will come up in the sense of space workshops a little bit later. I'll talk more about this, but essentially we are, we're essentially able to, so we collected lots of data on a reference platform, and you can see we can measure then, as you see on the right, the actual touch points, because we know exactly where the hand is, and then we also we sense the platform, and then we learn to recognize things like as you touch, your fingers actually turn a little bit red because of the blood kind of being compressed there and so on. And so we start, we then can do that, as you see here, once you're in interaction, I think, okay, it's on here, but you can then use it in the wild on VR settings and other things without the whole setup, okay? This was a data set where we collected egocentric data, all types of activities. I explained you this kind of main scenario was a remote person explaining to a local person how to do something. We wanted to understand like these type of scenarios, okay? And so we captured lots of those scenarios with a remote person explaining what a local person had to do. We collected 200 hours of data, fully multimodal with hand tracks, eye tracks, so also gaze. We know where the person is looking, what they're paying attention to, the full conversation. Actually, let me show you that quickly. So RGB, of course, the head pose. These all come for free also with the HoloLens, but also now with the AR glasses. Depth, then hand poses, eye gaze was also recovered. The audio and the conversation, so the bidirectional conversation, and then also the IMU, of course. And then also we had a company annotate and provide essentially a whole write-down of what was happening. Also annotate, so this is the scenario that I just explained earlier, and then we also annotate if something is correct, if the remote person corrects the local person, so we essentially annotate all of those things in the data set, okay? So things like this here. These are some of the object categories we manipulated. Here's some examples of how this then looks like. The person has to assemble here this thing, so we had many subjects do the same tasks, so that some people are fast with it, some people are slow. Oh, okay. So let me actually skip quickly through this. Right, so essentially lots of different actions. categories and so on. We also collected then a more exo data set in this space with colleagues at EPFL. This was a NeurIPS data set last year, where we have 9 exo cameras, 1 egocentric cameras. We even have IMUs mounted on some of the tools. So like the knife, for example, is instrument. So if you're chopping, you can measure that. This is kind of showing some of this. And so we have also very rich data sets. There's about 30 hours at this point of data, but 30 hours, you know, with all of them, the 10 different views, et cetera, et cetera. Still, you can never collect enough, so we also worked on generating. And then built multimodal models on top of that. And then I think I'll actually have to skip all the robotics, it seems. No, wait, was it? Oh, there's still 5 minutes for questions. Okay, I'll go a little bit into that, but very briefly. So we've also looked at, you know, at combining people, at seeing how people and robots could potentially work together. Here you see a kind of a scenario here where we use a relatively sparse representation to share. This is co-mind, which is, here the idea is, for now it's 2 people that work together in the kitchen. You have a leader view and a helper view. The goal is over time that we could learn something on how a robot would be able to help a human. Think of those humanoids we saw earlier today. You know, if they have to help you, they should understand how to interact with you, right? So in co-mind, we collected you know, all of the usual things of aligning it all to the scene, 3D, and we scanned the objects with scanners, the scanner on the right there. And so had a number of subjects do this. You see kind of good mix of distribution of different people doing that. And then we essentially are kind of annotating all of this in the data set. We have verbal actions, we have gaze. So this is all using the ARIA glasses. So we have also the objects that are detected, et cetera, et cetera. And so we annotate all the actions that are taking place. And in particular, we estimate the joint attention. So when you're interacting with the other person, you kind of see it, okay? So, and then we test essentially how, let me see, we have okay, so these are all the things we collected. In the end, we use the high-end models, so the frontier foundation models, to look at to estimate the joint attention between the 2 videos, but then also we fine-tuned a smaller Quen model or you know open weight models, and you see we get pretty good results on the fine-tuned once we fine-tune the models. So this is the kind of things that we see. Let me get the cursor here again. Okay, so we get the cursor. So here the standard Quen is kind of confused. But once it's fine-tuned, it actually gets the consistent attention here to the pan. The Gemini also does pretty well, and then you see the ground truth here, right? So we have numbers on all of that. This is not yet published work, but let me skip through that. To then wrap up with functionality and affordances. So this is work that will be presented here at the conference. Let me also quickly go to some of the results here. Let me skip through that. The idea is to be able to go from egocentric data to a functional 3D model. Okay, so the idea is you are doing things in your kitchen or in your space, like this here. By the way, notice again, like egocentric video data is tough, right? As you see here, if you do it in a natural way, and don't pay attention, actually too much attention when you interact. Okay, and so from that we then built a functional 3D digital twin. This is a big project we have with the Swiss National Science Foundation, where we're essentially building kind of interactive digital twins of the world. And so here you see kind of the output of that method. And so I think I'll leave it at that. I'll skip other methods. You can see this later at CVPR. Also training from egocentric data, how for a robot to interact. So we learn the motion that should come and then do that on cross-embodiment. And let me also skip through that, given time. Also for interactive manipulation, sorry, it was, where is it here? Okay, so you'll see it here. Okay, so this is the work, it's fine. This was essentially hand interactions. The last thing is a collaboration with Georgia Tech and many other partners on collecting lots of egocentric data, also specific dedicated data to particular types of manipulations, and then build on top of also here the ARIA glass and the whole setup there, both in the wild collections, but also then dedicated specific tasks, and then with the goal to transfer that to robots, where we also collect some specific robot interaction data, so to teach the robot how to do it, but then mix that with the larger kind of body of human data, and in particular build these bridge data sets. A line data set that allows us to bridge essentially the kind of robot-only data with the EgoVis, the kind of broad set of generic data, with the aligned data set that has the same tasks as the robot needs to do. We get a clear boost, and that was the whole point here. Okay, and so and this was mentioned earlier, the GEM data set, like the GEM generation data. This is ongoing work that's trying to, there were lots of challenges with egocentric data using a general frontier mode. Video generation model is actually very hard for egocentric data, in particular the hands and the objects. And so this ongoing work with also the goal of being able to transfer to robots, as you see on the bottom here. So where also we can control, so we can have the thumb here, for example, was controlled to be different. Here we can, on the bottom, we control the left hand kind of orientation, things like that. Okay, that was it. I'll leave it at that. Thank you.
Hello everyone, my name is Luigi Seminara and I'm a final year PhD student at the University of Catania. And today I will present my work with ViterbiPlanNet that I made in collaboration with Davide Moltisanti from University of Bath and Antonino Furnari from University of Catania. So in this work we study the problem of planning in instructional video, in particular how to leverage the knowledge and external knowledge. But what is a procedural knowledge? A procedural knowledge can be represented as a graph where each node is an action and the edges represent the transition probabilities to move from a node to another. And prior works usually create very big models like transformer-based model, diffusion-based model, and they try to learn these knowledge inside their weights. But in a real world, people don't use this, don't memorize all the procedural knowledge, but they use external knowledge like a book for following recipes or other stuff. So following this type of concept, we build this architecture where you have a start visual state, a goal visual state, and then we build a neural model that predicts emission probabilities, and then we use a differentiable Viterbi layer that leverage the procedural knowledge graph and produce the final plan. So this final plan depends from the graph that is this one, that is an external knowledge, and the neural model produce the emission probabilities. So our framework is very easy. It's based on an hidden state that depends from the previous one, where each hidden state is an action that produces a specific state that is a visual state. So this is the classic problem of sequence decoding framework that can be resolved using Viterbi algorithm. The problem of the Viterbi algorithm is that it is not differentiable. So we made some relaxation in the max operation and argmax operation, and we build an algorithm that allows to do the gradient, the backpropagation that pass through this graph. Here we have some results in cross, task, and nib that are two procedural datasets, and in particular we can observe that our model is in the top left. This means that it uses fewer parameters and obtains better results. And another good experiment is this one, the sample efficiency. In particular, using less training data, we can observe that using just 5% of the training data, we have a gap with the best prior work, that is schema, of about 5% of success rate. So this means that we can obtain good performance with fewer training examples. And also, this is another experiment that is very interesting, that is called cross-horizon generalization. What we made here is that all prior works trained different models for each horizon. In this case, we trained a single model of horizon 6, and then we test this model for horizon 3, 4, and 5. So if a model is able to understand the knowledge, it should be work for horizon 3, 4, and 5. But our method is the best in this case because we use this external knowledge and we don't need to memorize any single pattern in different horizons. So here are some qualitative results. In particular, in the base model, we can observe that the model learns to memorize this procedural knowledge, while in ViterbiPlanNet, just has to get a reasonable sorting and then rely on the graph for the correction. So this is a summary. We avoid memorizing procedural knowledge. We obtain good performance with fewer training examples. And our approach generalizes from long to short horizon. So thank you for your attention. And if you have any question, we can meet at the poster session.
Okay, hi, I'm Tim, and I'm here to present to you our work called HOI, a multimodal dataset for force-grounded, cross-view articulated manipulation. Let's start with the introduction. When we deal with robots, they interact with the physical world and they need to both see and feel, but existing vision datasets usually don't give you these physical signals. And this is why we introduce HOI here. So we present a data set that captures both or articulated object interactions from multiple viewpoints simultaneously. It has egocentric, exocentric, and manipulation-centric streams and pairs those streams with physical signals, such as RGBD, and effector forces, tactile, and 3D structure. The result, as I said, is HOI. It's approximately 3,000 multimodal sequences. They're all temporally and spatially aligned across 380 articulated parts, 38 indoor locations, and each interaction or each recording here, each stream kind of combines, bundles interaction forces with articulations, grounded articulations across multiple manipulators. So we have a hand, a custom HOI gripper, a UMI gripper, and we also provide ground truth trajectories, so head poses, gripper poses, hand poses, and eye tracking. We capture multiple viewpoints, so each interaction is captured by 1 to 2 exocentric cameras, egocentric camera, and a manipulation-centric camera. We also have ground truth geometry, and very interesting, we also have tactile stuff. So we kind of bundle all this very comprehensively together. The data set, or all recordings, kind of they took place across 38 indoor locations, predominantly at IKEA showrooms. And this gives us a very wide range of different kitchens, offices, bedrooms, everything that IKEA has to offer essentially. And the hope is that we get a data set that allows robots to generalize across all these different locations and interactable parts here. What's in the data set? As I said, we have bedrooms, we have kitchens, we have living rooms. As I said, everything that we can find at IKEA. In terms of articulated parts, we've got mostly cabinet drawers, doors. This is kind of the distribution of things you would expect in like a normal human environment. One thing, one of the novelties here is that we introduced is the HOI gripper. It's a custom gripper, and this actually allows us to kind of capture or combine the visual and physical signals. So we have this, which gives us, we have a Z camera for stereo depth. We have ARIA glasses, which give us super nice slam, as Marc mentioned beforehand. We also have the force torque sensor, which actually gives us these physical signals on top of the digital tactile sensors, which gives us just tactile feedback. And we can actually see, if we look at all these different articulated parts here, we actually get very distinct physical signals during interaction, which is something we can capture here. What does the data set actually look like? You can see we have all these different streams, egocentric, exocentric, streams. We have the tactile stream. We have our 3D ground truth, including instance segmentations and 3D kind of poses of the gripper during interaction. Down here, we have the force torque signal during interaction. And in the beginning, you can see how we actually kind of temporally and spatially align all these things using these QR codes, which I held into the visual stream, and then we can see what this looks like. Yeah, we introduce, we test stuff, we test different, we introduced 3 different benchmark tasks on our data set to show kind of that the kind of given methods for articulation, predictions, and these things kind of don't work too well. As Marc already mentioned beforehand, it's kind of hard. It's kind of hard to do it on egocentric video. And we also introduced new benchmarks for force, tactile force prediction and visual force prediction. You can see again, current methods don't really work that well on this data. It's quite hard. Yeah, in conclusion, we introduced this data set with lots of cool stuff. And yeah, my time is done. This is the team, cool people, very fun to work with. If you're interested in Dataset, you can download it here. We also have an ECCV workshop. I will be presenting the poster in the poster session here in the main session. And thank you very much. We're at 65 minutes, perfect. Yes.
Hello. I'd like to present my and Professor Frank Keller's work on PyV, a semi-syntactic pipeline for injecting realistic mistakes into clean procedural videos. Well, let's start with the example. Here's an example from EgoPair dataset. Maybe you know this one. The task is brewing coffee. On the left-hand side, you see the correct step, and on the right-hand side, you see a mistaken step where a person spills some beans. How many beans is it enough to spill to consider it a mistake? If it's just too little, we do not see it as a mistake. It's just a normal deviation. But if it's too much, it's too exaggerated and it seems unrealistic. So we see that there is no clear definition of visual mistake to date. And it's not all. We don't have many mistake-aware data sets to date. The biggest ones have fewer than 400 videos. Tasks are limited, and they have small dictionary of unique steps. Also, they have different taxonomies of mistakes, additionally restricted to a particular domain, and their labels are not directly comparable. And lastly, only 3 of them account for mistake corrections. This is because these datasets were designed for a visual model to trigger a prominent error at a specific step. However, when viewed as a whole, the video may lack coherence, and long context procedure study becomes unrealistic. On the other hand, in cognitive science, we have many, the mistakes were studied since the late 70s. So we have accumulated a lot of material from there and a lot of insights. So the question is, can we put these insights in an algorithm? Can we automate human mistake patterns? And the answer is yes, and this is what we do. We can represent the complexity of the procedures in semantic complexity of each step plus step load. For semantic complexity, we can use semantic roles. We normalize the whole procedure and divide the load in 3 phases, beginning, end, and middle. And then we calculate the likelihood of a mistake in a particular phase. We also built a taxonomy of universal categories, which is transferable from sequence-edit operations. Now we can specify what type of error happens more or less often in each phase, and the taxonomy is no longer restricted to a particular domain. For instance, wrong execution is a change in a semantic role. It could be a wrong object, amount, location, orientation, instrument, or manner, and substitution is when a plausible step incorrect action replaces the correct step. Then we put it together in a pipeline. From clip steps and their semantic representation, we go through the error and correction planner. Then we use LLM writer for natural step descriptions and LLM judge to verify the coherence of the procedure. Then we use VLMs to generate the video. With this pipeline, we took 50 scenarios from EgoExo4D, one to three for each of the 17 tasks, and generated 102 mistakes, 27 corrections, and then we started assessing it with our 9-metric rubric. The rubric classifies mistakes along 3 axes: the realism of the error itself, its coherence in the procedure, and its visual representation. So we took 4 existing datasets, sampled randomly 25 videos from each of them, and also set a setting when we just in a free-form asked LLM to generate mistakes and compared to our PyV pipeline. So we, and then 5 annotators assessed the results by our rubric. Then we see that the plan conditioned generation improves validity of the mistake and procedural logic. Also, it it also gives the increase in human plausibility, and also it's comparable with video generation, video grounding. The plausibility of the generated video is somewhere in the middle with the existing datasets, so quite natural. And here I go with the example, our PyV example of spilling coffee in the end of the procedure. The person spills coffee and then wipes it out on the left-hand side. So this is it.
I'm Enrico from the University of Bonn, third-year PhD student. I'm presenting our latest CVPR publication. And yes, it is another video generation paper, so if you want to scan the QR code, you can find some cool examples there. In this paper, we try to address a specific question, which is what will the egocentric agent see next if his body moves in a specific way? And this is quite important for a few reasons. Well, we know all the trends of embodied agents and word models, so for word simulation and planning, but also for entertainment, or eventually to generate new data which come from with annotation of poses. What was missing when we started this work back in August, September last year? Well, most egocentric video generation model were either just text controlled, which is not very specific, or camera control with amazing models that work very well, but very limited to simple navigation. So we want to go far beyond that and have something that can be controlled on the full body of the person to eventually explore and interact with the world. So first of all, we needed a way to represent the body motion in the video space, and we designed this around 3 components. 2 are related to the motion, frame-to-frame motion of the head and the root joint. And the third one instead is specific for each frame. So it's the relative position of every other joint with respect to the pelvis in this current frame. Coming to the method, we use the Nymeria dataset, which comes with synchronized videos and poses collected via a motion tracking suite. So it's quite well aligned and very precise. And we build this on top of the Cosmos Predict 2 diffusion transformer for generation. Coming to how we actually inject the pose to control the generated frames, well, the simplest approach would be in generation is to use adaptive layer norm. So you just flatten the pose, project them to the same embedding space of the diffusion time step out together, and use this to modulate the activations. But we also use cross-attention where the temporal structure of the pose is preserved, and we'll see later why this is important. About evaluation, we have 3 main dimensions of evaluation, visual quality and alignment with standard metrics for images, and global motion control where we run structure from motion on the generated videos, but also body control where we basically segment body parts in both the ground truth and the predicted frames and compare them. So we can see that by using full body control, we can have best results across all the dimensions, especially segmentation, so the body control, but also the motion of the agent, so the head in space. Coming to ablation, about our pose representation, it's quite important to use differential motion, so like frame-to-frame motion, because this keeps the values in a limited range compared to use cumulative values, especially for the translation. We also compare this by to instead using, for example, motion for all the joints that belong to the agent body. And if you use this, the model will really struggle to learn a relation between the pose and the generated frames. About the control mechanism, why are we using two? Well, it looks like if you use just adaptive layer norm, which is quite global, you will get camera control working pretty decently, but the spatial, more low-level details of the body moving will not perform very well, while with cross-attention this works, and by using both of them together, we solve both issues. This is an example of like an agent moving his arms and interacting with an object, like sort of a towel, so quite complex interactions. And you can use eventually this to explore like the same word in different ways or interact with objects in different ways. Coming to what we've learned by working on this topic, well, first of all, if you train these word models long enough with a control, they will at some point prefer the control over the simulated physics that they're trying to simulating at least. So the control will be reproduced faithfully, but the simulated physics might break. Second question, and this is quite interesting scenario where we have multi-agent interacting together. So how can we extend this to a multi-agent setup? And third question is if I will manage to get an internship after this CVPR. And let's see. But thank you for your attention. You can find me in the poster session, in the main poster session, a bunch of other workshops too. And just feel free to reach out if you have any questions.
Okay, thanks a lot everyone for coming. Thanks a lot to the organizers for inviting me. It's my very great pleasure. Yeah, so I'll talk about video understanding for robot learning today. Okay. All right. So the $1 million, actually not the $1 million, I guess if you go by current startup evaluations, maybe the $1 trillion question right now in robotics is, where do I find the data to train my model? There are many sources. Some companies are betting on large-scale teleoperation. We'll just collect a lot of data and that'll be it. People have come up with creative ways of collecting data. So you can, take the hand out and just take the hand around, collect data that way. That's another possibility. There's also the possibility of video data, using video data for training your model. And these three, by the way, the top three are regarded as, very VC-friendly items. But I think there are others too. I think simulation is another one. You can generate lots of things in simulation and use that for training. You can, right? I actually feel pre-trained models are also in some ways a data source. I mean, this is a data source which just gives you the answer perhaps, right? Or classical methods is another data source that, motion planning where it works, right? So my philosophical, and I think robotics is difficult. I think there are many different things you need to do. There's high-level reasoning that you might need to do. And I think the different data sources are actually compatible with different things you might want to do. So high-level reasoning, for example, you can best get it from video data, I think. It will be very difficult to get that from simulation, from large-scale teleoperation. I think pre-trained models have a lot of high-level reasoning information encoded in them. On the contrary, if you look at something like whole body control, I think simulation is a very good source for that. You have many degrees of freedom. You cannot teleoperate easily and such. If you have a contact-rich task, maybe real-world data collection is the way to go. So I think my take on this is, many of these data sources will be useful. We should figure out ways in which we can use disparate and kind of all these different data sources for training. What I want to talk about today is video data specifically for the interest of this audience. And I'll show you some work where we are trying to use video data. We are understanding video data for doing robot learning. So let's dive in. So how can, and I'm agnostic to whether it's egocentric or exocentric, but I'm going to phrase it in context of egocentric. So, how can egocentric videos help robots? Videos are easier to collect than robot data. You don't have to take the robot around. So you might get large diversity, which could aid generalization, right? So videos are easier to collect. You can get many more diverse things, and that might be easier. A second aspect is videos directly show demonstrations for you how to solve the task. So if you're in the business of opening locks, looking at a video of how people open locks, you have a key that you insert somewhere, and then there is maybe a knob that you have to twist and so forth. I mean, I think this is all demonstration data, which nominally, if you're training with RL or something, you'll have to have the thing discover, which is difficult, right? So demonstrations may directly show you how to solve long horizon tasks. A third often overlooked thing is it depicts what the world is like and how it works, right? So, this mundane clip, you can actually see, you hold the handle, you open it, and so forth, like a cupboard. And you sometimes end up seeing things you did not think you will see, right? This cord can get stuck in there, and, it is typically wrapped around over here. So this is like some common sense in some ways about the world that is shown in videos, and it's be helpful to learn this from here as opposed to other sources, right? Okay, so I feel there is a lot of promise over here, and I think, right, so egocentric videos can aid us. At the same time, it's not so easy to use videos for robot learning, right? The forefront of it is there's embodiment gap, right? Sensors, actions, capabilities are different. Right, the capability of a human hand, for example, might be significantly more than the robot end effector that you are using. So the way you will do the task maybe has to be different. What senses you have are different, right? I have tactile feedback, your robot might not. I have tactile feedback, but in the video, I don't observe the tactile feedback, right? So there is a gap of that form as well. Yeah, videos don't come with motor labels, goals and intents may not be known, trajectories may be suboptimal, you only see the on-policy data or like successes, you don't see failures as much perhaps, and such, right? And all of these are challenges which prevent this trivially that, okay, I just download a bunch of video and, train my robot on it. That's just not possible. My way of thinking about how to meaningfully use videos in spite of these challenges is to learn at different levels of abstraction. For example, I have human actions, and humans are operating with their muscle tensions and so forth. Robots are operating with motor torques. You cannot observe human muscle tensions, and neither are they useful for inferring what the torque should be. But if you think of the control hierarchy, I don't just look at the raw muscle tensions, but I look at, macro actions, some skills, some sub-goals, or actually what goals can one have in the world. There's a full control hierarchy. And in some ways, video understanding, in my view, lies on this axis where I try to take very basic things and infer high-level intents and sub-goals and skills, that this human behavior analysis axis of this. At the same time, there's robot behavior generation, that if I have some goal in the world, or let's say I have some sub-goal, how do I actually generate motor torques and commands that realize that sub-goal? Or if I have a macro action, how do I realize that macro action? What are the torques I need to apply for it? So there is this very nice control hierarchy. And depending on the amount of gap you have between the goals, embodiment, and what you can actually observe in videos, we may benefit from transfer at different levels of abstraction. The obvious path of going from human muscle tensions to motor torques may not be the right one. You might have to go up in the hierarchy. You might have to do some video understanding. And then you translate that understanding at a level which is kind of transferable to a robot. And now you do something to actually render out that behavior on the robot side. So this is kind of my overall philosophy in trying to think about videos for robot learning. And we have found success at applying this idea to navigation. And this is actually very old work, so I'm very embarrassed to present it, but I'll still talk about it very briefly. So for example, for navigation, we were able to use videos for learning affordances and subroutines. What are affordances? So let's say you have this video. You just observe this clip. You can now actually go back to the first frame. And this clip very naturally tells you that at this location, you could go out of the door and turn left, right? It tells you that. And so we were able to use this to actually mine what can you do over here. So you can turn left over here. So we trained a model. And over there, you can actually, we could find that this model reliably fires on kind of entryways, wherever there is an entryway to the left. So this is what I'm calling affordances for navigation, if you will. You also have subroutines. You also know how to actually do this. So in this case, I'm showing you some robot time lapses where the robot is actually turning left in different situations. And this was all done by training on video data. We can actually infer these things about navigation. We have also done this for semantic layout, which is this question of what is where. So let's say, again, you have this short video clip of someone entering into a house and kind of looking across the corner. Just by looking at this video clip, you can actually infer that at the very first frame, if I were posed this question, where is the couch likely to be? I can turn left, go forward and turn right, and that's kind of where I'll find the couch. So you can learn these semantic layout cues, right? So, you do this, I'm not going to go how we did this. It can actually learn not only what objects are visible, what directions are objects that are already visible, but can actually speculate that, okay, I'm looking for a bedroom, which is typically down a hallway. So it will fire, okay, going down the hallway is the promising thing to do if you're trying to look for a bedroom. We had some numbers back in the day. Our method, this is measuring how quickly can you find goals in a novel environment. And this was better than if you were to do reinforcement learning or imitation learning or combinations of that. And this is what kind of got me really excited, that there is the potential of being able to use video data for robotics in a meaningful way. So in the last few years, we have been actually, so in this case, this was a concrete example where we didn't translate exactly human actions to motor torques. Rather, we went up, we learned these value functions from videos, and then we had something else to render them out on the robot side. Okay. More recently, we have actually started applying this idea for manipulation. So in this paper from a couple of years ago, what we were doing is we were mining manipulation affordances from videos, right? So we saw this video clip. This person is opening this cupboard. And we can, similar to the navigation examples, I can use this data to answer questions. What sites can I interact with? Cupboard handles, right? How do I interact with those sites using an abducted thumb grasp? Or what happens when you actually do, right? The basic insight that we have built over here is that we can learn through observation of human hands interacting with the world, right? All three of these questions, if you pay attention to what the hand is doing, you can actually infer the answer. And so, we had some model for doing this. So you can infer, okay, you hold the plates at the edges and you can pull a drawer open by pulling on the handle. You can also infer there is this object that you're trying to pick up, a precision disc grasp is going to work for it and such. Now, all of this work was 2D and I couldn't figure out how to translate this into something useful for a robot. So what I'm going to talk about today is I want to upgrade all of this to 3D and try to show you how all of this will translate to robot policies. Okay. So this is the first project I'm going to talk about. This is bimanual 3D hand motion and articulation forecasting in everyday images. And we are operationalizing the same idea we had before. We were saying what the hand is going to do. What we're going to do over here is we are going to try to solve this 3D forecasting problem. The 3D forecasting problem is I want to predict, given this starting frame, I'm going to predict what is the hand going to do next. What is its 3D trajectory going to be and how is it going to be articulating. If I have this information, I can actually infer what can I do here and how, right? So this is answering some of the same questions that I had before, but in a much more grounded in 3D kind of a way. I can also retarget this to a robot end effector, right? So if I have that this is what I need to do with the hand, I can now maybe translate that into do some retargeting. Now I also know how I can do the same thing with the robot. So this is kind of, if I can forecast it, I kind of infer, I'm going to be sliding this handle over into this coffee shop, and that's useful. So what I'm going to do is to tell you how we can build a good 3D hand forecaster. By the way, 3D hand forecasting, I think, also has applications for in other realms, right? So AR coaching applications, right? So let's say you're trying to play a piano or, figure out how to clear a paper jam out of your printer. In a futuristic world where everyone has AR glasses or something, maybe we can, this can actually guide how you should be doing something. So how do we build a forecasting model? Okay, so The future, unfortunately, future is typically multimodal. Given the same input image, there could be many different things you could do. You could be picking this box up, you could be tilting it to the right, you could be trying to rotate it in plane. You can be doing a lot of different things. So forecasting fundamentally requires you to have a sense of how you can build multimodal models, right? And in 2016, we actually know how to build a multimodal model. We can train a diffusion model, right? I can essentially set up a diffusion transformer. It takes in the image, passes that through a visual transformer, gets some image tokens, and then I can try to denoise what the hand should be doing, and we can do this. But only if you had complete 3D annotations. What do I mean by complete? It's in this following sense. When you train a diffusion model, you need full samples for training. So in this particular application, I'm trying to build a 3D. I've been given an image, and I'm trying to learn this conditional probability distribution. What is the probability of 3D given this image, right? And if you're familiar with diffusion models, we are trying to train a score function, and I do this. How do I train the score function? What I would be doing is I will sample data point x3d, image from a dataset that I have, and I'm now going to add some noise to it, right? So I take x3d, the ground truth, I add some noise to it, I get a noise sample, and I now train a denoiser, which takes in this noise sample and your conditioning information, the image or whatever you have, and you try to predict the amount of noise that was added. And there are many equivalent formulations, but this is one. Okay, you can do this only if you have the full sample x3d available to you, right? So we need the full sample x3d to train the denoiser. If you just had, let's say, 2D annotations for images, and I'll tell you why, which are situations where you only have 2D annotations, you can't use that data for training a diffusion model. In some ways, you don't know what do you add noise to even be able to input into your function f theta, right? So this is a technical problem. And this is actually a different problem. This is different from what you see when you have to train a regressor. When you're trying to train a regressor and you have 2D annotations, you can simply use a reprojection loss, right? So if G theta is a regressor that you're trying to train on the image, it produces a 3D prediction, which is what you want. You now project it using a projection function, which we know, and now you get it into the 2D image space, and now you can put a reprojection loss on the key points, and that's how you train a regressor. In fact, that's actually how people were training models for predicting 3D without diffusion models, right? So you'll have lab data sets which will have complete 3D annotations. So you make G theta produce those complete 3D annotations, but then it will only work on lab data. It will not work on in the wild data where we want models to work, which are harder to get full 3D annotations for, right? So, but what I cannot have on these in the wild situations, I don't have good ground truth for 3D, but I can have annotations. People can do 2D annotations that this is where the key points are for the hand, let's say, or for the objects. And I can get 2D annotations relatively easily on in the wild data. Now, where I could use this this additional 2D supervised in the wild data for training a regressor model, I cannot easily use that for training a diffusion model, right? So my question is, the technical question we need to answer is how can we leverage partial samples for training a diffusion model that should produce the full sample? And our solution for this is the following. We start with lab data. I have full 3D annotations over here, and I'm going to train a lifting model over here, which is going to take the 2D annotations and try to lift them to 3D. In lab settings, I have all the data I have full data, so I can train this lifting model. So for example, for this forecasting problem, this lifting model will take the form of, I have 2D key point annotations on the hands over time, and I know how the camera was moving. I also know what was the 3D hand, how was that moving in my video, right? So I have both of this information. So I can train my lifting model on lab data easily. Now, once I have this lifting model, I'm going to essentially run this model on the 2D annotations that I have in the wild data. And now I'm going to impute some 3D annotations. And now I can use these imputed 3D annotations to train my forecasting model F, right? Which takes a single image, tries to produce this sequence of hand motion and articulation. So this is our solution. I can give you some intuition why we think this is a reasonable solution for this problem. We have X2D, the 2D key points and the image, and we want supervision for what is the probability of 3D given this image, right? So I'm really understanding what 3Ds are possible with this image. The lifting model is essentially building a probability model of the 3D given the 2D information that you have. What it essentially is, given the 2D information, it tells me what the 3D could look like. And in some ways, that's all the information I have about the 3D that there could be. And so what I'm saying is, when you're given this image, try to predict this, whatever information I have about the 3D. And that's kind of what this lifting plus forecasting model is going to do for us. I'm not going to go into the specific design of the lifting model. We're working with egocentric data. The camera also moves. So these key points are, with respect to different cameras. So when we train the lifting model, we want to give it all the information. So we also have to give it the camera information. And what we are doing is doing it through Pluker rays and so forth, which is not so important for the current talk, but you can find these details in the paper. So this is some results with the lifting model. We are trying to compare it with other methods for doing this. So you could essentially run Hammer, which is a high-performing hand pose estimator. And that doesn't get very good, very low MPGPs, mean per joint projection position error. You can also do Hover, which has been optimized for video data, but that also doesn't seem to work here. You could do something classical. You have some video, so you can use something like easy mocap to kind of triangulate the hands, but it's not as easy as triangulation because the camera itself is moving and the hand itself is changing. Whereas the lifting model actually does reasonably well. You can also refine it based on the 2D key points that you're actually observing at test time. So this achieves a 3.2 centimeter mean joint projection error. And if you were to collect data in a lab setup, you get error of the order of 1 centimeter. So it's off, but it is better. Whatever design choices we had also seem to make an impact. I'm not going to go into these results here. And what we see benefits of using the lifting model for training the forecasting model. In particular, you want to pay attention to the zero-shot numbers. So we are not going to train on this data set. We are just going to test on this data set. And what we are seeing is by injecting 2D labels, you get improvement in metrics. So this M metric, which is let's say the one we look at, is the mean per joint projection error. It drops from 24 to 18.8 in this EgoExo 4D evaluation, which is what we set out to do. We wanted to build forecasting models that can work on in-the-wild data. And this forecasting model is also better than past methods and reasonable baselines. We are also measuring diversity and multimodality scores because this is a forecasting task, and we also see better results over there. I'll defer to the paper for those details. Maybe I'll show you some of these visualizations. So this is the input image. These are the hands, and this is the coffee machine that you're seeing in front. I'm going to try to show you the forecast that we are able to get. Just to give you a sense of what the 3D scene is, this is what the 3D scene looks like. I'm just showing you multi-view data so that you can appreciate the 3D scene a little bit. And now I'm going to show different forecasts. So the blue hands are kind of reaching in and trying to press some buttons. The magenta ones are probably trying to manipulate the cup on the bottom. I think this magenta hand is reaching onto the top left side, maybe into trying to get to the cupboard and trying to get something from over there. I think reasonably plausible looking forecasts that one can get from this machinery. Here's another example. This is a printer kind of a situation. And again, it does something reasonable. Again, I'm showing you some 3D views to understand what the scene is like. And then, this hand comes in and you can be manipulating the screen in this case, or you might have samples which will try to reach for, I don't know what this purple thing is, trying to pour something, but I guess that's an error mode too. But you have these brown hands which are trying to reach for the thing on the right-hand side and doing it, right? So this is a forecasting model that is doing something reasonable. Okay, so this was the first thing that I wanted to talk about, where I showed you that we can build hand pose and articulation forecasting models. But to do this, you need to train a diffusion model on partial data. And we did this by training a lifting model. Now, next, let's see how we can actually use it for robot learning. So this is the second paper. This will be on archive soon, but you can look at the web page, which has lots of the videos. And there's a collaboration with Pulkit's students. And this is what matters when co-training robot manipulation policies on everyday human videos. So I'll just tell you very briefly, how do people do imitation learning for manipulation? You essentially have a vision expert, which could be, whatever pre-trained vision model. You feed in robot images. And then there's an action expert, which is going to output temporal chunks. So, you output actions for the next 25 time steps, something like that, using a denoising head, right? So it's, again, using diffusion models. And I'm going to get a temporal chunk that I'll produce, and I'm going to use a diffusion model for doing it. right? So this is how you do imitation learning for manipulation. The forecasting model that I told you is actually very similar. You have human images going in. I don't have robot proprioception, but what I have is past human poses. And essentially I'm forecasting, I'm actually outputting a temporal action chunk, right? Using a denoising head. So it's actually very similar. So what you can do is you can co-train a model jointly on all of this data. Sometimes you pass in the robot data. I guess you have these different heads. So whatever is modalities, there is one last layer which is specific to the situation, or one first layer which is specific to the situation, which you are seeing in the blue and the orange colors. Everything else is shared, right? And so this is how we co-train on both robot data and human data. The human data we use in this case is EgoXO4D. We are not using our forecasting model from before, but that's we want to do that. But for this Ego4D, what we did was we pre-processed the hand pose data to make it much more accurate. And so this is accurate 3D hand pose data, again, by triangulating the different views that you have in EgoXO4D available. We also had to do some alignment that, so this is the retargeting part. So what we're doing is we are retargeting the knuckle of the middle finger from the hand to be the tool center point for the robot, which is more reasonable choice than the wrist, because the wrist doesn't interact with the object. What interacts with the object is actually the fingers, right? So that's kind of what we are doing over here. These are some tasks that we are going to show performance on. And these are tasks which are not just pick and place. So there are some reorientation. So you have this cup that you want to flip, and there's some pushing tasks and so forth. They're largely pick and place, but not the trivial kind. There's some more interestingness to them. And so here are some results. So if you just train, so this is co-training. So you can compute how much robot-only data do you need. Can you just train on 3 environments? If you just use the 3 environments, you get 12% success rate, not very good. If you do this human co-training, you get 41% success rate, which is much better. Of course, if you get more data in the real world, the robot-only performance increases. The human one also increases, but not as much. So with 10 environments, you get 53% success rate for robot-only and 66% for the human co-training. Interesting thing we found was hand pose quality matters quite a bit. So you can either inject noise. With no noise injected, you get best performance. But if you have noisy hands, performance goes down. You can also look at, if you, instead of our method of accurate triangulated hands, you could use hands from Haver. They're not very good. You still get some improvement, but not as much when you get high quality hands. So in this case, if you're interested in like a fine grained kind of a task using videos for that, hand pose quality matters quite a bit. Second thing is data diversity matters. EgoDex is, I think, 5x larger than the data that we trained on. But training on EgoDex is not as effective. EgoDex is, by the way, like tabletop kind of things. Is not as effective as our method, which is using which uses diverse data. Okay, so in the second part, I talked very briefly about how you can co-train on robot and human data. And we saw that improved generalization through use of EgoXO4D, but needed high quality 3D hands. The last thing I want to talk about is going to be very brief, is that key points are not enough, right? So in the previous two, we were just saying, okay, it's the hand that is important, where the hand is what matters. In this latest work, which is going to be on archive soon, what I'm trying to make the point is that just key point tracking is not sufficient. You might be interested in making fine-grained contacts, right? So key point tracks do not completely specify the task, particularly when you're interacting with objects. So in this case, both of these are largely the same key point trajectory, but one is incentivized. The left one is incentivized to make contact at the wrist, and it is able to wipe this incorrect spelling of robotics on the whiteboard, whereas the one on the right is not able to do that. So what I'm trying to say is that key points, the same key point trajectory, but can have different effects on the environment. And tasks are defined not just by key points, but also key point plus contacts made with the environment. So we're going to do this. I guess existing work does not do this. They only train with key points because that's easy to extract from videos. Contacts are not so easy to extract from videos. We are going to essentially say, okay, we're going to learn a key point plus contact tracker somehow. And again, the way we are doing this is reasonably simple. We say, okay, this is what a typical policy takes in, humanoid object tracking policy. We're going to say, okay, here are the contacts you want to make. And we also add rewards that encourage those contacts, right? So with only these rewards and no task-specific rewards, we can actually start solving tasks, right? There's some more details here and there. And so we can actually control fine-grained behavior, right? So sit and lean on the back versus sit but don't lean on the back. I mean, the key points in this case are far away, but But we can get this kind of control. You already saw this, make contact at the wrist or don't make contact at the wrist, you get different behavior out. I guess the third example is going to be in simulation, where if you make contact at the wrist while trying to pick up this box, you can actually pick it up. If you don't, then you don't pick up the box, right? Okay, so to summarize, I think what I showed you is how can you build hand pose and articulation forecasting models? How can you train diffusion models on partial data via a lifting model? How can you co-train robot and human data? And then finally, I showed you that tasks are defined better as key points plus contacts and such. So I'll leave some questions for discussion. And I want to thank the students who did the work. And now I'm happy to take any questions that there are at this time. Thank you.
So we have time for one quick question if there is any.
Thank you very much for the talk. So you're defining these key points and the contacts, but you're not defining like the scene.
Yes, I don't want to define the scene. So if you define the scene, then it's a policy that also needs to inject the scene geometry along with the tracker controller training. Instead, if I say, okay, make a contact at the wrist, in some ways, I'm imagining there is a separate vision module which outputs this key point and contact trajectory, like a forecasting model. And this forecast is passed to a tracker, which can now, I am hoping, just using proprioception is able to do the job. The reason I'm trying to do this is this amplifies the data that I can use for training. I can train the forecaster on purely visual data. I can train my tracker on purely simulated data where I don't have to create scenes. I don't know if it'll pan out or not, but that's what we are trying to do here. Very, very good observation and question.
Yeah, I have a quick question. You mentioned you improved the accuracy of the 3D hand pose. Could you explain what change you made and to achieve that?
That's right. So in this case, we are targeting whole video clips. So I think the right comparison point is something like Hover. But in this case, when we have the whole video clip, the lifting model can learn priors on how the hand moves through time. And I think that's why...
Yeah, but as I know, if using the egocentric videos, the camera will move very randomly, and using triangle method to do the calibration, then to do the 3D.
That's right. So I think
but it's a little bit too noisy, not very accuracy.
Yes. So I think we did improve the camera hand pose accuracy in two places. One was in the place where we were on EgoXO4D, where you have the external views. So there it was mostly just redoing what was already done in the EgoXO4D dataset, but from these external views. So the camera is not moving. So they're time synchronized. So I can get triangulation signal from there. In the first project we were doing where the camera was also moving, where the camera motion is also input into the lifting model. We can take this offline, but yeah.
Okay.
Happy to chat more.
Let's thank our speaker again.
Hello everyone and welcome to the results for the 8th round of Epic Kitchens Challenges and the 2nd round for the HD Epic Challenge. Firstly, I'd like to thank all of the participants again for another successful year and say that we greatly appreciate all of the community's consistent engagement with the datasets and challenge that we release. This talk today will cover 3 parts. First, we'll have a quick recap of the history of how the 9 current challenges came into existence, then followed by a summary of this year's results, as well as a brief overview of the winning methods before announcing the winners. So let's begin with an overview of how the Epic Challenges evolved over time and how we ended up with the challenges that we have today. We start in 2018 with the release of Epic Kitchens 55. This introduced the action recognition and action anticipation challenges, which serve as the longest running Epic Challenges today. Moving on to 2020 and the release of the extended Epic Kitchens 100, 3 new challenges were introduced: action detection, unsupervised domain adaptation for action recognition, and multi-instance retrieval, forming 5 challenges overall from the vanilla Epic Kitchens RGB data. Of course, there's never enough annotations, so then in 2022, things got even more fine-grained with the release of Visor and its pixel-level annotations, enabling the semi-supervised video object segmentation challenge using the provided hand and object masks. Following this, in 2023, we shifted modalities away from the RGB with the release of Epic Sounds, providing audio-centric annotations and adding in the audio-based recognition and audio-based detection challenges and broadened Epic purely beyond purely visual annotations. And finally, taking all of this that was learned from the previous datasets, an entirely separate dataset, HD Epic, arrived in 2025, offering the most extensive set of annotations so far, with 2D annotations spanning recipes, ingredients, and nutrition, with the videos also being grounded in a 3D digital twin to provide rich scene understanding. Alongside the dataset came the VQA challenge, spanning 7 different forms of reading, leveraging the numerous types of annotations that we released. And the VQA was also designed in such a way that the visual information from the frames is highly important for answering the questions, meaning that text alone is not enough. And so with this timeline, this leads us up to today, so let's see what happened in this year's round of challenges. Out of the 9 challenges available, all of them saw new participants and submissions this year, and notably 7 of these challenges achieved a new state of the art, so we'll go through each of these. Let's start with the HD Epic VQA challenge. Starting with the baselines from the original paper, Gemini Pro achieved around a 37% overall accuracy across the 7 different reasoning categories, struggling mostly with the questions that required some form of 3D understanding. Then, in the first HD Epic challenge round last year, performance increased to 44%, an impressive 7% gain over the baseline. However, this year saw an even larger jump, with the entire 2026 podium exceeding 60% overall accuracy. First place reached 67%, a 23% increase over last year's winner, so very impressive results overall. So what changed to enable such a jump this year? One common theme was intelligent structuring of the input beyond simple frame inputs and text prompts used in the original baselines. So Third Place built a dynamic hierarchical memory, which builds a query-agnostic and temporally grounded video memory from fixed 30-second windows, groups these windows into semantically related higher groups using sentence embedding similarity, and summarizes the overall goal from these windows. Second Place used a course-defined semantic evidence pipeline, which captures global structure through semantic evidence, whilst object-centric visual evidence preserves fine-grained grounding through bounding boxes and visual embeddings. And First Place dynamically adjusted the sampling rates depending on the questioning type, enabling a dynamic interchange between questions requiring fine-grained information and questions requiring a broader overview. Another theme was task specialization. So Third Place used task-specific skills and inference protocols that combine reasoning instructions with optional tool-derived evidence per question type. Second Place tailored semantic and visual evidence differently for each task, allowing for semantic evidence to be beneficial for tasks requiring long-term reasoning, while visual evidence provides per-frame fine-grained information. And First Place used category-conditioned input construction with per-category prompts tailored to the semantic and temporal structure of each question type. So what set the winning method apart is that they had an additional test time adaptation which aggregated multiple predictions to resolve ambiguity for difficult questions. When we look at the leaderboard, we see that all forms of reasoning have improved, but we also notice that each podium submission have a clear category specialization. Third Place particularly excelled in gaze reasoning. Second Place was strongest on ingredient, nutrition, and action reasoning, while First Place dominated recipe reasoning, 3D understanding, and motion-related questions. So once again, congratulations to all of these teams for their strong performance. Now we move on to this year's Epic Challenges results and the remaining 6 challenges. For action recognition and action anticipation, V Jawahar 2.1 provided particularly strong features for egocentric video. These were especially effective for noun accuracy, which increased by over 3% for both recognition and anticipation. Overall, though, the results this year stand with a plus 2.1% action accuracy improvement for recognition, getting close to the 60% mark now, and a plus 2.9% action accuracy improvement for anticipation, now creeping towards the 30% mark. So we still see that strong pre-trained features continue to drive progress in these challenges. Moving on to multi-instance retrieval, the new state-of-the-art refined clip image features using a temporal transformer, which was then followed by a 2-stage re-ranking pipeline using a cross-encoder between the image and video tokens, which resulted in a plus 0.9% improvement this year. For semi-supervised VOST, SAM3 was combined with a competitive memory mechanism designed to suppress distracting objects from the initial input, which also resulted in about a plus 1% improvement and new state-of-the-art performance. When looking at audio, Ensemble still remain the strongest approach for recognition, achieving a plus 2% accuracy improvement in this year's round from models such as Audio Spectrogram Transformer, specifically PA-SST, as well as Audio Inception Next. For audio detection, the increasingly popular causal TAD framework helped to achieve a new state-of-the-art here, providing an improvement of around 0.7%. So to summarize, looking across all of these challenges, this year's was mostly driven by large pre-trained models. Across tasks, methods leveraged powerful foundation modules to reach new state-of-the-art performance. However, comparatively fewer approaches explore different settings such as unsupervised learning, zero-shot performance, or more data-constrained pre-training. So if we remind ourselves of the supervision level scale figure from the 2020 paper, which is also used to categorize submissions for the challenges, we see that there are many different possible configurations. Yet most methods typically fall into the large self-supervised pre-training with fully supervised fine-tuning across the combined training and validation set to achieve state-of-the-art. So there's still plenty of methods left to explore, so we welcome a diverse set of solutions for the future, even if they're not necessarily state-of-the-art. And that concludes this year's summary of the EPIC and HD EPIC challenges. Again, we'd like to thank all the challenge participants and the challenge leads for another successful year. And now we'd like to move on to announce the winners. So for those online, if you could please turn on your cameras, and I'd like to ask those that are here to collect their certificate in person to remain seated when called out, and then we'll have everyone at the end come to collect their certificate for a photo opportunity. So without further ado, the winners for this year's challenges are, in action recognition, for first place award is Chen Den Long from HKUST, Sorbonne University and AMI Labs. The first place in the action anticipation track is the Korean team from Harbin Institute of Technology in Shenzhen, Pengchen Laboratory, and Shandong Jiangsu University. For the action detection challenge, the first place award goes to the iLearn team from Shandong University and the Harbin Institute of Technology in Shenzhen. For the multi-instance retrieval challenge, third place awards goes to Uni Andes from the Universidad de los Andes. And the first place award again goes to the iLearn team from Shandong University and the Harbin Institute of Technology in Shenzhen. For the semi-supervised video object segmentation track, second place award goes to Team Yanzi from the Key Laboratory of Intelligent Perception and Image Understanding. And the first place award goes to the HCV group from the University of Sheffield, Northwestern Polytechnical University, and Tsinghua University. For audio-based recognition, the first place award goes to Team RRRRTY from Gideon University. For the audio interaction detection track, second place award goes to, again, RRRTY from Gideon University. And the first place awards goes to Team CLBQ from the National 111 Project Base of Intelligent Information Processing from Gideon University. Moving on now to the HD EPIC challenges, the third place award goes to Team YB from Yonsei University. The second place award goes to the Hippo team from Lenovo. And the first place award goes to the iLearn team from Shandong University and the Harbin Institute of Technology in Shenzhen. So congratulations again to all of the participants this year. And again, if you're in person, you can now come up to collect your certificate and we'll have a photo opportunity as well. Thanks very much. Do we have the people in person today? Yeah, you stay here and then we'll have a yes. I think that's everyone. If I'm the only one. It seems like you're the only one. Should we get close to the screen? Yeah.
Hello everyone, I'm here to present the results for the Ego4D and EgoXO4D challenges in 2026. This year we ran a reduced set of challenges. We ran 5 benchmark challenges, and the reason was because this was a year of transition, moving away from eval AI to Coda bench. And I'll next describe what the challenges we ran. So we ran 3 challenges from Ego4D and 2 from EgoXO4D. First was natural language queries, where what you're given is a clip and a natural language question about the clip, and you have to localize within the clip where the answer for that query lies. Goal step is somewhat similar, but instead of a natural language question, you're provided a goal step, which is like a key step, like an action description of what's happening, and you have to localize that region in the video. Then we have the short-term object interaction anticipation. This comes in the forecasting benchmark of Ego4D, where given where you are right now, you want to forecast what object the person is going to touch in the future, what action they're going to take next, and at what time interval that will happen. And then moving on to Ego XO4D, we ran 2 challenges, Ego Pose Body, which is the body pose recognition, egocentric body pose estimation challenge, and the procedure understanding, which is deeply understand procedural activities. So here you're given a video and you need to predict the task structure that the person is doing as part of that video. So we had good participation in all these challenges, and now I'm just going to list out the winners for each of the challenges, and in the end we'll do the certificate ceremony as we just did for EPIC. So for natural language queries, the first prize goes to OSGNet. This is Yesen Fang et al. From Harbin and NUS and other collaborators. Their method was primarily focused on generating a large number of candidate temporal segments for identifying promising clips, and then use a strong VLM model to re-rank them to find the most accurate clip for that query. They were also the winners for the goal step challenge. And so their method generalizes across both natural language questions, while also the action descriptions. The second place for goal step challenge went to Hero Step G, Andrea Zanotto from University of Torino. And their work was completely zero shot. They were not using like a strong VLM. What they were doing is like trying to estimate a hierarchical structure based on steps and sub-steps. So do these low-level step detection and build some hierarchical structure of it, and then do some temporal clustering to identify areas which are most promising for that particular goal step. Moving to the short-term anticipation, and here we have first place and second place, and both teams are using JEPA style like encoders along with other sort of techniques on top of that. And that this is possibly to leverage like forecasting sort of temporal features that are probably better in the JEPA architecture. So Vista team from Harbin and other collaborators, they got the first prize. And then Frost STA from Behang University got the second place for short-term anticipation. And the last one, the participation from procedure understanding. For body pose, we did not have any submission which could beat the previous year's baselines. So we are not like awarding any prizes for that. But for procedure understanding, again, the top entry here still remains the one from the last year. But this is a second place winner. And they build a graph structure to do this reasoning for procedure understanding from Zhejiang University. So yeah, before I call all the participants here for the prize, I just wanted to highlight that we have a new license server for Ego4D and Ego XO4D as well. This was like a challenging issue because of legacy infrastructure that was being used. So it's all fixed, and we are using modern tech stack for doing it. So hopefully there's no longer issues with the licensing for these data sets. And if you're releasing a new data set and you want to leverage some of the tech that we have built, we are also happy to share the code for that as well. So yeah, if there are any winners here, I think there's some on Zoom for sure. So any winners from the challenges who are here? Okay.
Yeah, thank you for joining our Holocyst Mistake Challenge. Unfortunately, I couldn't join in person for personal reason. So yeah, I will just do it online instead. So yeah, let's get started. Just like to remind what the Holocyst dataset is. We collected Holocyst dataset for interaction between the object and then like with AI assistant here in person. And we collected around 169 data set, around 200 pairs of people with more than 8 different objects. And basically, we collected these interactive remote assistant scenarios. So we have like a performer, instructor, and then whatever we performer does shared with the instructor, and the instructor give feedback to performer by verbally. Anything performer makes some mistake. So, for example, in our mistake detection, there's a given like a task, for example, replace an ink cartridge, and anytime I see the mistake, then we label it as like a mistake, otherwise it's correct. So for example, in here, it's supposed to open the ink cartridge, but they open the paper tray. That's why it's called like a mistake. Otherwise, it's correct procedure or actions. So for mistake detection challenge, in this year, MRCA's team make 8.2% improvement. Congrats for Boyu, Han, and Kian Su, Xilong Bao, Jiyong Yang, Lun Chen Kui, and Qingming Huang. And from like last year, they have like make this like a good improvement. And then I will share the winner's presentation. We have a video for that, and then we probably have like just short like a Q&A session, like for 30 seconds or one question. So can you hear the sound from the video or not? Can you confirm for that?
No, we cannot hear.
Can you hear, Masashi?
No, we cannot hear.
Oh, you cannot. Okay, let me. Is there any way I can share my also computer audio? Then like Masashi, can you share the video from your side?
Okay.
Then maybe that's easier.
Hi everyone, I'm Bo Yuhan from the Institute of Computing Technology, Chinese Academy of Sciences. Today, I'm pleased to present the solution developed by me and the MRCS team for the mistake detection challenge of Hollow Assist. The goal of mistake detection is to determine whether a user makes an error while performing a task. However, this is not just a simple action recognition problem. In Hollow Assist, mistakes can occur at different semantic levels. The first type is a local execution error. This means the current fine-grained action itself is incorrect. For example, in a switch-related task, when the user is trying to insert a Joy-Con controller into the rail, they may align it in the wrong direction, push it into the wrong slot, or fail to slide it along the rail properly. In this case, the mistake can be detected by focusing on the current short action segment. The second type is a procedural error. Here, the action may look correct if we only look at it in isolation, but it is not appropriate for the current stage of the overall workflow. For example, pressing a button on the switch controller may be a valid operation by itself, but if the user does it before the controller has been properly attached, or before the setup step is completed, then this action happens at the wrong stage and becomes a procedural mistake. To detect this type of error, the model needs to understand not only the current action, but also the coarse-grained task context and the order of the workflow. So a single model with a single view of the video is not enough. At the same time, we also found that the Hollow Assist dataset has a clear long-tail problem. In this task, mistake events are much rarer than correct actions, and many of them are also ambiguous. As a result, the dataset is highly imbalanced and the model can easily be biased toward the dominant correct class. This means that standard optimization methods designed for balanced datasets are no longer sufficient. To address these challenges, we propose an understanding-enhanced model collaboration method. It mainly consists of two parts. The first part is a collaboration between a small model branch and a large model branch, which helps the system handle different types of mistakes at different semantic levels. The second part is a long-tail optimization, which is designed to improve the detection of rare and ambiguous mistake cases. First, for local execution errors, we use a large model branch based on the Chevron-3 VAR embedding model. In this branch, we freeze the Chevron-3 VAR embedding model and only train a lightweight classification head for mistake detection. This branch only looks at the fine-grained action segment. Its role is to focus on the current action itself and judge whether this action is executed incorrectly. Second, for procedural errors, we use a small model branch based on clip for clip. This branch takes both the coarse-grained video and the fine-grained segment as input. In this way, it can compare the current action with the overall workflow and decide whether the action is appropriate for the current stage. To make this branch stronger, we first enhance clip with diffusion contrastive reconstruction, and then use the enhanced clip to build the clip-for-clip video encoder. Diffusion contrastive reconstruction is also our work accepted by CVPR this year. Its main idea is to use a generative model to improve clip's visual representation. For the second part of our method, we focus on long-tail optimization. As I mentioned earlier, mistake samples are much rarer than correct samples in hollow assist. So if we train the classifier with the standard loss, the model may be biased toward predicting the dominant correct path. To address this, we use three complementary training objectives. The first one is weighted cross-entropy. This helps balance the clauses directly. The second one is AUC-oriented learning. Instead of only looking at each sample independently, this loss compares positive and negative samples. This is essentially useful when the data distribution is highly imbalanced. The third one is a label-aware adjustment. This method uses a class priori to adjust the logics, so the decision boundary can be better calibrated under long-tailed data. By combining them, our classifier becomes more robust to rare and ambiguous mistakes, which is very important for this challenge. Here are our results on the test set. Compared to random and times former, our method shows a clear improvement in F-score. When compared to the sorted method from 2024, we see a big boost in mistake recall. When compared to the sorted method from 2025, we see a big boost in correct recall. What's more exciting is that our method only uses the RGB modality, but still achieves performance that matches or even beats models using multimodal inputs. That said, we still believe this is a very challenging task. There's a lot more to explore going forward. That's the end of our presentation. Once again, thank you to the organizers for all your hard work. If you have any questions, feel free to reach out to me through the contact info on my homepage. Thank you.
Thank you. So on behalf of Teng, I'm gonna give the award. Is there anyone from? Oh yeah.
Thanks for organizing the EgoVRS workshop, and this is Yu Qianfu, and I'm very happy to presenting our EgoCross challenge under the EgoVRS CVPR 2026. And EgoCross is with a cross-domain egocentric VQA, and here I also very grateful for all the co-organizers who has made this challenge happen. First, I would like to briefly introduce the task introduction of our challenge. And so the main motivation of EgoCross is that most of the existing egocentric works, they assume that the chain and testing set, they are from the exactly same domain. But in the real world applications, we would wondering that what if the model and could they transfer the knowledge that learned, for example, from the daily activities in the Ego4D to some novel egocentric data set. For example, what if you are doing some exchange sports or videos from the pet's ego? And for this one, our previous work, EgoCross, wants to fill this gap and proposed the EgoCross, which is currently accepted in the IIII 2026. And this is a summary of how the EgoCross looks like. In short, EgoCross carefully selected and also integrated 4 different domains, including the surgery industry, animal perspective, and also exchange sports. And some typical VQA examples could be shown here. And we want to evaluate the model's generalization ability when it's being transferred to some novel or unseen target that is never being seen by the model. So this could review like how the model is good at recognizing or understanding those videos that is not so common to the model. And this gives another summary of how our data set looks like. So for example, this one is a surgery video, and this is a video for the exchange sports, and this is an example for the industry. So in general, EgoCross evaluated the model's generalization performance. And for more details, our challenging proposed 2 different checks. The first is called source limited check, and under the source limit check, we provide some small support set for each domain. For example, we provide 20 VQA pairs with labeled query and also with labeled answer. And so those queries, they could somehow guide the model to learn how the current target domain would look like, as some like few examples to give some guidance. And also we limited that the participant could only use the Q-Win3 VL4B as the only fixed backbone to ensure the comparison is fair. And also because we selected the 4B model to make it to be more GPU friendly, and so all those participants who are interested in this task could participate in and try to propose their new algorithms. So in general, the source limit check is we are strictly limited the data and the base model could be used. And by contrast, the open source check is under the open data setting. For example, in addition to the small support set, we also allow the model or the participant to freely explore all the open data that they could find, let's say, for example, web public or somewhere else. And we also didn't set any limitations on the base model. So in principle, any model is encouraged to include those like commercial-based ones. But we indicate that manually searching the target aligned data is not allowed, since this basically violates the assumption of the cross-domain VQA. And for both of the checks, we evaluated the models on more than 900 VQAs across 4 novel target domains that I just introduced before. And we use the multi-choice VQA as the evaluation task. And finally, we use the average accuracy as the final metric. And this page gives an overall summary of the challenge. As the first year of the EgoCross challenge, we received 19 teams for the open source check, 38 teams for the source limit check, and also in total we got more than 130 participants, and with more than 1,500 submissions for both checks. Next, I will introduce the solutions from our winners. The first is the right inference strategy is all your meat from the HKUST and the know-in. And this team, notably that this team is the first award on both the source limit check and the open source check. And the main idea of this team is it proposed that under the cross-domain VQA setting, a universal prompt is not enough for addressing the 4 different domains, but instead we should adapt the inference interface, but not the model parameter. So in general, it proposed a domain-wise inference router. It will automatically route the analyze the current target data and then give it a specific, let's say, for example, prompt or like domain specific knowledge to analyze and give it a better result. So the main key takeaway information is that careful domain aware inference could enhance the model even without any additional training, and overall it achieved the best result on both checks. And the second one is the Omni Ego R2 from the Shandong University and the Harbin Institute of Technology, and it wins the second award on both checks also. And this one, on this team, they first proposed there exist three main challenges under the cross-domain VQA. And for example, one is a temporal boundary ambiguity, and one is cross-domain semantic mismatch. And also, it discovered that there's some decision unstable under the cross options. And accordingly, it proposed several modules to address the pointed out issues. For example, it proposed a temporal evidence navigation to let the model to be aware of the current 10 step of the frames. For example, if you ask some questions about what is the 10 of the question, then the model is not aware of what is the second according to the frames. So it proposed to attach the 10 step information to the current frames. In that way, the questions related with the temporal information will be enhanced very significantly. And also it proposed a capacity-oriented router and row decomposed reasoning to address the issues with the cross-domain semantic granted mismatch. That similarly, that for different domains, it will propose different strategies to emphasize on different reasoning capacity. And eventually, it also found if the answer is close to each other, then the model will be confused. So it proposed to verify each answer according to. That means for each answer, it will try to check whether this answer is correct or not, and eventually it will enhance the model's performance. And the third one is enhanced VQA via a temporal token injection and retrieval augmented annotation from Xidian University. And this team wins the third award on the source limit check. Critically, this team mainly proposed 2 points. The first is 10 aware prompting, similar to the solution that is being proposed in the second team. So they also found that the current model or the current benchmark is very sensitive to the 10 related information. So they also proposed that the model, when we try to fine-tune or when we try to adapt the model should be more specifically aware of the 10 information for each frame. And its solution is to attach the 10 information, for example, in the way of hour plus minute plus second in a text format into the current frames. And in that way, try to fine-tune the model and also inference the model in a similar way could enhance the models. It also studied several strategies for efficient fine-tuning, and in particular, it found that the direct prediction followed with the explanation will produce the best result. The last one is the reflective dialogue between teacher and the solver, and this is from the authors of the Takuya and Nagoya. And this team, they win the third award on the open source track. And this team, they propose the novel idea of reflexible dialogue, which construct a multi-turn conversation between the two agents. To be more specific, the teacher will propose each support question and deliver the correctness feedback. And on the meantime, the solver will try to enter and also provide the visual grounding explanations or reflections for both the correct and incorrect answers. And here we can see like two examples. Like one is when the answer from the solver is wrong, and this example is when the answer from the solver is correct. And by collecting those multi-turn conversations from the reflection dialogue construction during the inference, they will first search the most allied VQA construction pairs to the current query, and then use them as for the in-context learning to enhance the model's performance. And that's all for our like the solutions from the team and also the basic introduction of our challenge. And lastly, thanks for your listening, and also special thanks for all the participants for their great efforts.
Thank you, Chen.
Thank you.
Okay, so last but hopefully not least, hi, I'm Luca. I'm the challenge lead for the Castle Challenge. We're running this challenge the first time this year based on the Castle 2024 dataset. So before I introduce the challenge tasks, maybe let me briefly introduce the dataset for those of you who may not be familiar with it. So the Castle dataset is comprised of over 600 hours of ego and exocentric video. You get 15 time-aligned data streams, 10 egocentric, 5 exocentric, that were recorded over 4 days in a common location. So what we did is we brought together a bunch of people in a remote location on the Irish coast late in 2024 and had them record their daily activities with the camera strapped to their heads. So you get their unscripted daily experience with 50 frames a second video, including the audio stream, including all the GoPro sensor data streams and various auxiliary data streams. And you can see some little preview of what this looks like here. And since this is the first time we're running such a challenge on this data set, at least in this context, we limited ourselves to one pilot task this year, and this was a closed form question answering task. And you can see some examples. I'm trying to get rid of my Zoom thing here just to make sure you can see all of this. So we had a total of 185 questions that are completely open across the entire data set, so you wouldn't know where to look in to figure this out yourself. And you get 4 answer options, and I have some example questions here. I think you can see some of these are have very precise answers that ask for a specific fact or a person doing a specific action. Others require more contextual understanding, right? You need to know, okay, where was this source located at this time when a specific event occurred or when a specific object was in view. The results, we were quite impressed with the results. We got 43 registered participants, which we were quite happy to see that there was so much interest in the challenge. However, only 4 teams submitted both runs and final reports. And these are the results. So the highest scoring team was Team WDL from Zhaidan University, followed by the Mars team from the Harbin Institute in second place, the team from Tahacom in third place, and Curious AI from SoftBank with 2 submissions in fourth place, all of them scoring significantly above the random baseline. Right? Given this was a pilot task, we didn't have a specific baseline. So yeah, congratulations to all the participating teams for this very impressive initial performance. Just as a brief outlook, given that this is the first time that we did this, we want to do more of this. We have another challenge with a slightly different setup this year, organized as a grand challenge at AC Multimedia, with 3 different tracks being event instance search, object instance search, and open question answering. So all of these don't have an explicit ground truth, but will be post hoc evaluated. And we hope to, again, bring back the challenge for next year's joint EgoVis workshop. And we're looking to introduce additional tasks in the challenge, such as visual reconstruction. So given that we have multiple sources, but not all the sources may have been active all the time, reconstruct certain views that you don't actually have, or given that we have additional sensor streams, do sensor or do activity prediction or things like that, just based purely on sensor streams. We're also very open to feedback from the community on this. So if you find any of this interesting, or if you have other ideas and comments, what you would find interesting, please drop us an email. Given that none of us were able to be physically present, we don't have any physical certificates to hand out right now. We will send those out to the highest scoring teams shortly. And yeah, that's it from my side. Thank you very much.
Yeah, thank you, Ricard.
Yeah, thank you. Thank you for inviting to speak in this workshop. So I was just due last year. I could not make it. It's an old debt where world is changing fast. So egocentric videos are getting used for different things. It's an era of egocentric we are seeing. We see robots learning from egocentric video. We see these intelligent agents need to negotiate, need to talk to each other, need to talk to others for carrying out tasks. I think driving is a very good example where you need both. You need robots to learn. You also need to know how to coexist with human drivers, coexist with the different class of agents, and then interact. So this is where I think the Ego Vision has a very interesting role in this space. So we have rich history of pioneering works in this area, where from egocentric videos and later multimodal streams, we try to understand what is really going on. But what's more exciting is what's going to happen next, or why people do. Deeper questions of this we need to understand. And when you get into driving, these questions are quite straightforward. Driving to me is way different from a machine which can navigate based on an instruction, because it has to coexist with many more vehicles struggling on the limited resources, particularly in the global south, interacting in different forms. Should I unmute?
Unmute yourself.
There are two.
Yeah, and share the video also.
Video also. Yeah. Thank you. Yeah. So we need to understand the driving from an egocentric viewpoint. And when you look at it from an egocentric viewpoint, particularly for global south, countries like India, where we have been trying to understand how the driving takes place in India. We still don't understand. And why? There are deeper reasons in terms of economy, the limited resources, you have a limited resource and you need to negotiate and navigate within this. The perception is very important, control is very important, reasoning is very important. And on top of all of this, there is a big missing piece of education today. Because that's a lower priority on the list. If I want to travel from place X to place Y, or if I want to have roads, vehicles on the road, education and regulations enforcement is still a lower priority. So what this sort of data will look like. So if you look at this sort of examples, you will see the two-wheelers and four-wheelers which are navigating on the road. There's a space, an inch space left out that is for me. And if you're taking a four-wheeler, like if there is no signals, there's a bunch of people coming from that side to this side and you need to go in the middle. And that's how the day, every day, those who have traveled in India or similar countries, you will easily appreciate that, okay, this is how people drive in this area. And this is more interesting because the spectrum of roads are very wide. Highways, which can compare with the roads of any country, to rural roads which do not even have a formal structure. And people travel with different vehicles. Bullock carts to BMWs on the same road, traveling at the same time. The navigation becomes very interesting. I think these are all super exciting problems which possibly today's AI is nowhere near and will keep us occupied for decades, even with the current speed that we are seeing today. So when we do that, so what is the next thing that we need to understand? So what is the driver going to do next? Is the driver going to do, because there is no signal, what the driver is going to do next? Can you understand from the behaviors or the movements of the driver? Things as simple as where the driver is looking, which side the driver is moving. So the moving on one side need not be based on only the intention. It is also based on the geographical. I have space left on my left side. I will move towards my left and then I will take my right turn. That's possibly the fastest way to reach my destination. So gaze is a very important area. And if you can understand where the driver is looking, then it can tell us a lot. So we were trying to see that the gaze that we need is not possibly the precise space where we gaze possibly that people need when you are manipulating smaller objects. What we need is an approximate gaze, and is it possible for us to get it at a much cheaper cost? So in the first attempt, what we tried to do a few years back was, is it by asking, say, people to drivers to watch the road, and by looking at their gaze, can you predict, by just looking at the eye, can you predict it and how accurately you can predict and map to the road? Of late, we extended this with the model where if you have a camera or a mobile phone, which has cameras on both sides, can it look at the road, can it look at the driver and see how do you map the eye gaze or the eye movements to that on the road? So the idea is like this sort of movements, you know that, okay, you are moving towards one direction or you are driving at certain direction, but you are seeing an old lady trying to cross, and is it possible for us to alert? Or is it possible for us to use this information for predicting the driver? So if you want to predict the driver intention or what driver is going to do next, you need all this information. You need to know the road geometry, road surface properties, the other vehicles, and of course the driver's movement history, driver's gaze, the head movements. And if there is so the idea was basically to capture all this with a ego exo setup and use this for predicting the driver. And not just the driver anticipations. So some of the earlier work in this direction tried to predict the maneuver when it is very, very close to the turn. So we would like to make this prediction as early as possible. That is where the value lies. At least few seconds early or few 10 meters early, if you can predict the movement or what is going to happen next, then the utility is very high. Of course, the problem is very challenging. And not just predict the driver's intention or anticipation, can we also explain why the driver is trying to make this turn? Is it the intention that driver wants to go take a U-turn here or to take a right turn there? Or is it that the driver is moving towards the right so that it can avoid somebody or it can save a human or a pedestrian walking in the middle? So these explanations were, in the first attempt, was mostly at the level of the reasons, a set of selectable reasons. And we also found that these explanations improve the accuracy of the prediction, like in many other situations that we had seen in recent years. Today, we also tried to see, can you actually explain this better with a human understandable way by integrating to the language capabilities of LLMs. So here, if you are taking a left turn and you are moving towards slightly far, why are you making this decision? You are anticipating that there will be something unseen or unexpected could be there in this corner, and I need to be prepared to avoid this. More explainable driving is what is possible today by integrating this driver gaze, driver intention, and the language and reasoning capabilities. Here are some more examples and visualizations of various forms. The problem is more challenging when it becomes two-wheelers. Two-wheelers are possibly very close to the human, the simple wearing glass and people walking style of videos. It can rotate very fast. It need not have a very stable view. And what we try to do is very similar in this case too. So we have a camera setup, which is the rider is wearing cameras. We are seeing the road. Camera is seeing the rider. And also there are cameras which are seeing the back, the rear view mirrors. And using all this, what can you conclude and can you predict what the driver is going to do and what can you understand the two-wheeler driving behavior? This work which is getting presented in ICRA right now. So this sort of movements are far more complex than what happens in a two-wheeler. So many of these movements or the maneuvers are possible for four-wheelers too. But two-wheelers provide a new class of movements which are not otherwise seen in the typical navigation setups in the datasets. Here are some examples. Sorry. So it's a simple movement, simple road. Four-wheelers and two-wheelers. How these data will look like. So now if you want to go down, what a typical driving data will look like. The obvious ones are easy to understand, the different agents, the four-wheelers, two-wheelers, and pedestrian, the three important classes of moving objects on the road. They continue to move, and we have RGB camera, we have the gaze. We can also have additional annotations. These additional annotations come in the form of, for example, what is a turn, what is an action, what's a maneuver. We also have the explanations based on the gaze. What gaze is going on, or where is it today, or where the rider or driver is looking. And also we have a reasoning why this driver or rider is carrying out this sort of movement or this sort. The data become more interesting when we add telemetry. So the telemetry information provides one more dimension which helps us in making informed decisions. So what is the purpose of gaze? So gaze is, till now we are trying to understand gaze from a rider's point of view or the driver's point of view. But interestingly, the gaze also provides a lot of information about what is there in the scene. So there's a scene information. A simple thing that one can observe is if the scene is simple, highway-like scenes, which is mostly the driving data worldwide. You see the gaze is reasonably stable. The moment the traffic becomes unstructured, cluttered, then the driver need to scan all over the place. For making these decisions. So gaze provides the driver information as well as scene information, which both we are is part of the driving data. Then there is a pedestrian. Now this pedestrian who walks on the street, what the pedestrian is going to see and where the pedestrian is looking. Pedestrian need to worry about multiple moving things, like not just the road, also the other vehicles. Here's an example of multiple pedestrians moving. So we have multiple agents and how they are trying to interact, signal, inform each other about their joint purpose. And then there are rare events, which are not so rare. If you look at the numbers, say 1 accident every 4 minutes. And many of these are avoidable. So the study says that the two-wheelers are major reasons for these accidents. And of course, the key reason for all of us, we know, the infrastructure, drivers, riders, pedestrians, education. Education is a very important thing. So we are, as a university, we are learning that very, very late that education of driving is very important and it is in a really bad shape. I'll come back about accidents in a minute. So we have been looking into this India driving dataset for last few years. And our attempt has been mostly centered around the scene understanding, object understanding, what is typically required for navigation, say, in a typical Western setting. And in the second phase of it, we started to think about humans and actions. Humans in this case are drivers, riders, pedestrians, how they see the road, how they interact on the road, and what are their intentions. Can you explain their intentions and actions? And how do we use this for improving the road safety? And so this has been the shift in our direction of research in the Indian driving space. So before I end, I also want to quickly talk about two small applications that we have been working on. The one was centered around like how do we understand what is a quality of driving? So the application is very simple. So if I have my Ego video available, is it possible for us to tell how good is my driving? Can you give me feedback on improvements? So in India, very often you see in the say school buses at the back, people write, if this vehicle is driving rash, please make a phone call to this number. Is it possible to get such feedbacks? Is it possible to get feedbacks by looking at raw video? Can you get explainable feedbacks? Can you know where you did right, where you did wrong, and what you could have done alternatively? This is partly an ongoing direction. So today we have a small two apps that are on Google Store, which is helping in learning and validating for people how they are learning and how they are learning driving right or wrong, and even checking their understanding of how the driving should be. For example, is it possible for us to score it now? So the question now is very simple. Given a long egocentric video, can you start scoring it? Can you start giving feedbacks? Can you start using this for improving their education? And part of it cannot be done, part can be done in real video, but it is offline. Part also need to be done in a simulator. In a simulator, the advantage is also we can create critical scenarios. Though the visuals are not super realistic very often, but critical scenarios are important for people to learn. So these two directions we are taking, building applications for improving the safety and safety of education, keeping in future. At the same time, we were also asking this question, is it possible for us to predict accidents from the data? It looks like it is possible to predict that data because we all might have seen boards saying that, okay, this is accident-prone area, drive carefully. And this comes from the data. That data get analyzed by the governmental agencies, and intimations and information come to the citizens as this is an accident-prone data. But this usually comes very, very late. So our goal was, if AI is super great, then why don't we use AI to predict accidents before it happens and even intervene? So it worked well because the technology that we used is very simple because people talk about the autonomous driving, ADAS, and road safety. Road safety being the minimal requirement, at least that our primary requirement. So what we tried to do was, like, can you mine the ADAS alerts at scale across city, across time? And this experiment was conducted for 3 years in a full city. Yeah, in a full city. So this was conducted. And the data was cumulated. So the idea was, like, as you see, the ADAS signals from a big fleet of vehicles were accumulated to understand the potential places where accidents are going to happen next. A large batch of drivers were trained to understand the potential drivers who may get into accidents soon. And all this information is fused together to know where, in a limited budget, where do you deploy? When I say limited budget here, limited civil engineering budget in intervening on the road, limited people budget in deploying the police or the security forces on the road for traffic police on the road at appropriate places within the available manpower. So this was carried out in the 2 cities, with the city Nagpur for 3 years, in highways in Telangana for 3 years, nearly 2.5 years. And both behavioral patterns and the studies were reasonably same. So you can see at the bottom, a map which shows that these are the places which are presently not as an accident-prone area according to the government or the road infrastructure authorities, but potentially going to be the accident-prone with the type of movements of vehicles that we are seeing in that area. Is it possible to intervene? Given we are not government, we are like completely external person. We have limited control over the government, and so what we do, we did also went up to the level of training first aid for the shops next to the potential places where accidents could happen, and this eventually lead to reduction in accidents. So the statistical study shows around 40% lower accidents in cities as well as in highways. And this has given glory for India as a global geotech for the AI powered in 2024. And ACM recognized our contribution as an outstanding contribution for applied computing. To summarize, driving is a complex multiplayer activity. If you really want to understand, create AI agents which need to be on the road or in the real world and negotiate with other AI agents and humans in resource-constrained situations, we need to think deeper than what we do today. Simply carrying out a certain task by imitating robots or humans is possibly not enough in many of the situations. And I hope the studies from this sort of driving helps in this direction. Thank you. If there are any questions.
Time for questions. Any questions from the audience?
Yes.
Okay.
So I'm interested in the feedback loop eventually to get this sort of, the models that you train on human egocentric data while driving. You mentioned education is of course one big thing, but I'm trying to compare it to the other skill-based learning examples that people like to give. For example, tennis swings where there's sort of live feedback. Do you think there's something equivalent in the driving setting, or is it more just a longer term education feedback?
You mean can you elaborate the question? So you training humans or training machines? The question here.
Either actually. Let's start with training humans, and then maybe there's a follow-up to training machines. If training humans is the goal, is this, what's the best?
Say training human is possible, but at the end of the day, when you are deploying here, like what's the cost of training and say how much I can use my the learned skills here? I find a faster and cheaper or way of doing a short circuit. I will do that. How do I stop that?
Mm-hmm. I think the question is, can drivers benefit from live feedback?
Yes, live feedback is what ADAS very often gives us.
Okay.
Yeah. So what we have been seeing is people want to switch off that alert. Yeah. So I had seen like a taxi drivers, like when the seatbelt was made compulsory for the safety. So now I had seen traveled myself in taxis where they have an extra metal piece. Why? No, I'll plug here so that it doesn't stop sound.
Right.
Yeah.
Okay, and then on the model side of things, so there's this common wisdom that if you learn how to drive in India, then you can drive anywhere else in the world. Do you think that translates to models directly? And so, for example, should we be just skewing the training distribution entirely to Southeast Asian countries, collect a large amount over there, and then maybe the self-driving data in the US is maybe not as
No, I don't think so. I don't think so. So because the patterns, you cannot do such short circuits in the US.
Got it.
Thank you. Yeah.
Thanks.
Hello, great to see you. So I was wondering about the prediction agents you were talking about, and was there on the agents you were predicting for humans walking around and in pedestrians as well as the motorists, were you guys able to learn any policies about how humans are behaving in that, or have you explored that? Is it completely adversarial, as you talked about, or is there any pattern to the madness?
So we have not gone that far yet. Yeah.
Okay.
It's important to study that. Yeah.
Okay, that's the direction you guys plan to. Okay. And the number you were showing about 4 minutes, is that just accidents, or are you talking about deaths?
Deaths.
Deaths.
Yeah.
My God.
The accidents and deaths, both numbers I had possibly.
Yeah,
number,
you said about 1 in 4 minutes. Is that accidents?
Yeah, that's an accident. Yeah.
Okay. Thank you.
So I'm curious, like oftentimes actions of a driver are conditioned on what other drivers are doing or other two-wheelers are doing.
Yes.
And it can be like someone is in front of me is doing something wrong, so I need to maybe take risk, and even my action could be suboptimal, but it's something I'm forced to do because of what the other person is doing.
Yes.
Or it could be the other way around, that the other person is fine, but I'm impatient and I try to maneuver based on that. So is there like some sort of work in this direction where it's not independent decision making, but conditioned on what other people are doing?
So we have not done that part, but that's what I possibly emphasized a lot by saying that, okay, look, in India driving, you have to do that. So group activities are very, very important. And how do you coordinate, collaborate, complement, compete for the limited resources? Yeah.
But I guess getting data for that kind of studies is tricky, right? Because it's subjective in sometimes.
Yes. Yeah. But it is subjective, but we all know very often like what is really going on if you're even lived in such a setting, isn't it?
Yeah. And the second question I have is, you mentioned about the apps for giving score to people.
Yeah.
Like, are there incentives that people need to actually use that app? Is that something they just put on their dashboard? Like, why would I use that app?
So there are two apps I mentioned. One is a set of apps that we are now trying to work with government in terms of can the government make it compulsory for driver education or at the licensing time or at different stages. The second is about how do you create an app which will start giving you score. So that, say there are issues like if you might have seen in India, like a mother's gift motorbike to the boys, and they drive very rash. So mothers are always keen on like how safe my son is driving. So there is a need for many people to get an indication of, just like your health band, indication of your score. How good is your health? How good is your driving? So this is important for or if you're a fleet owner, you would like to know how your drivers are doing at scale. Yeah. So there is incentive for that. Yes. Yes, absolutely.
Any other questions? Maybe have. So I got a question on the setup itself, like this Ego Exo setup inside the car. So it looks like these two viewpoints are kind of very correlated. So we tend to think of Ego Exo like a camera that is fixed and another camera that is moving with the person. But here, both cameras are kind of moving, like with the vehicles.
Yes.
And I wonder if this setup could be replaced by not having like...
But of course, sorry, there's a relative motion between these two.
Yeah. Sure. I mean, I was thinking, is this egocentric vision inside the car actually needed, or can this be replaced, I don't know, like by a gaze tracker that is fixed, embedded in the car, that looks at your eyes and maps your attention on the exo view? I mean, would this be sufficient, or would we miss something?
See, the typical commercial gaze trackers are very costly. They are not scalable if you want to collect from multiple people. Secondly, we are not even talking about still like Ego being fully used at the deployment time. It is at this moment, it is mostly to understand how to model the behaviors.
And I want to follow up on that, saying that maybe another application is getting rid of the exo cameras and trying to do everything with Ego only, meaning that one day you have these devices and apart from reminding what to buy at the grocery store, they also help you in the car. And it's not something that is tied with your car.
Right. Nice, good, yeah. More challenging
Thank you.
for the community. Yeah.
Any other questions? Okay, so I would say let's thank Professor Jawahar again, and
thank you.
Yeah, great to have you back. I know it was a short lunch break. In the afternoon, we have a number of keynotes, oral talks, but also we're starting with the EgoVis Awards. And if you haven't heard about those, I'll just start with a quick introduction. So this is an initiative by a bunch of people with the EgoVis board members. So we're not the organizers of the workshop. We haven't done much of the work in getting this greatly organized workshop. But one thing we have done for a number of years now, this is the third year, is to think about distinguished paper awards. So what are these EgoVis Awards? We are looking for original and innovative contributions, particularly to the egocentric vision research, and to recognize a selective set of outstanding works, up to 10 each year, that we believe should be highlighted. They should highlight the latest and the greatest works in the area. These typically are papers accepted at least 6 months before. So you've read them, you probably know them, and so you're able to kind of comment on their usefulness to the community. We also strongly encourage papers that offer additional contributions beyond a method, whether it is public code, models, or datasets. The reviewing is single blind because these papers are already public, but we don't kind of tell you who exactly reviewed each paper, and this will be the third round. In this round, we invited peer-reviewed papers at conferences or journals that were accepted between January 2024 and December 2025. And there will be a $1,000 award sponsorship by Google DeepMind this year. We received 28 eligible papers. Each paper was asked to provide the reviews that when the paper was accepted, as well as a prologue of why they think the paper deserves the award. The process was we had a number of people on the board, but also external reviewers who volunteered to help the board in reviewing. And as usual, in each case, we kind of distributed the paper, avoiding any conflicts. Each reviewer voted for up to 8 papers, and each paper was assessed by at least 5 reviewers, sometimes with 6. This year, we selected the top 8 papers, which were clearly distinguished from, like the cutoff point was very easy to notice. Each paper was selected for the award by at least 3 reviewers. And the winning papers are distributed as follows. We had 2 papers that were published in CVPR 24, 1 paper from NeurIPS 24, 4 papers from CVPR 2025, and 1 from ICCV 2025. The top 8 papers, this is a typo, will be presented next in no particular order. And each winning team, if they're around, will be given a 2-minute speech reflecting on the path that led to this paper and its success. And we will take a picture. So please, if you come to receive your award, wait for a picture. I don't know who is taking the pictures. And then you'll have 2 minutes to kind of tell the audience about the experience. And this is recorded, so it will be online. And the winners for this year actually in alphabetical order. So they're not in no particular order, but implying, we haven't ranked the 8 top winners. And so I'm presenting them in alphabetical order. And the first is the NeurIPS 2024 paper, Differentiable Task Graph Learning, Procedural Activity Representation, and Online Mistake Detection from Egocentric Videos. And I'm hoping they're around. Okay. Congratulations.
Photo now? Or?
Yeah, photo now. Okay. And the floor is yours.
Thank you. First of all, thank you for this award. For me, it's very important because this is my first paper as first author, and also it was a spotlight in NeurIPS 2024. And this paper, born from a simple question, can we make a machine able to understand procedures, activity as a sequence of, as a structured process instead as a sequence of actions? And then we decided to extract this structure using a differentiable approach, because at that time there were only handcrafted approaches. So having a differentiable approach means that you can use features from videos or text to extract these task graphs and use these task graphs for resolve online mistake detection. Then we worked in an extension and we resolved different downstream tasks. And we got accepted our journal extension at PAMI in 2026. So I'm very happy, very excited. And this is my final award for this paper. And also I have to say thank you to Antonino for everything, for his guidance, and also to Giovanni Maria Farinella that is not here, but he is one of the authors. And thank you because I'm very near to finishing my PhD and I'm very happy. Thank you again.
And the second award goes to EgoGen, or EgoGen, an egocentric synthetic data generator. Please.
Thank you very much for this recognition, and thank for all of my co-authors and the recognition from the EgoVis board members. This paper is that the story of this paper is that in the era of LLMs and multimodal foundation models for third-person view models, some people would argue that the data is the real driving factor for the success. And if we want to follow a similar trajectory or training recipe in the egocentric vision, to see what the scaling laws look like in egocentric vision, we need the data. However, the egocentric data sets are very limited. Collecting real-world data sets is very expensive and non-scalable. So our solution is to propose a synthetic data generator for egocentric vision. And the paper is called EgoGen because my name is Gen. However, synthesizing realistic egocentric data is non-trivial because there exists a interdependency between the egocentric perception and action. So how we move determines what we see, but what we see also determines how we move. So to close this loop and to solve this interdependency, we propose a novel world model for the embodied human motion and demonstrate that EgoGen can really scale up the performance and boost the performance of egocentric perception models and paves the way as a data infrastructure layer for the multimodal egocentric foundation models. In our follow-up work in the EgoM2P published in ICCV 2025, we validate this vision to see that EgoGen can really drive the pre-training for multimodal egocentric foundation models. And the fun fact is that when we submit this paper, the first version to SIGGRAPH Asia, I got strongly rejected. So this award really means a lot to me. Thank you very much.
Great. The third selected paper is Ego Life, Towards Egocentric Life Assistant. So we have a video recording, which I will play next from the first author. Hopefully you'll be able to all hear it. Let's hope so.
Good afternoon, everyone. My name is Chung and I was the lead of the Ego Life project. Today, I am very happy and honored to accept this year's EgoVis Distinguished Paper Award on behalf of the whole Ego Life team. When we started Ego Life, most egocentric data sets only record a few minutes or few hours of activities, but real life is much longer than that. Our friendships, habits, conversations, memories, and experience happen across days and weeks. We feel that if we really want AI to understand people, we need to show AI what real life actually looks like. That was how Ego Life started. The story began in early 2024 when the Meta area team sent 6 Meta area classes to our lab, MM lab at NTU. My advisor, Professor Willy, gave all these 6 classes to me. After that, I was thinking day and night about what we could do with them. I wear them everywhere, to Taylor Swift concerts, trying to record Ego Taylor. I wear them to football matches, but find Chinese football team cannot beat Singapore. I keep coming up with different ideas. Then one night, while I was watching Mr. Beast knock hundreds of the people in the island, I think I got what I want to do. It was 2 a.m. I sent a message to Professor Zui. I asked, Professor, can we buy an island? He replied with a question mark. So instead, we rent a house, invited 6 people to live together for a week. So that's become EgoLife. I would like to thank Professor Willy for always supporting big and sometimes crazy ideas. I would also like to thank all of the collaborators and the participants. There were many unexpected problems during data collection, cleaning, training, and building the entire system. But everyone worked together and made it happen. Looking back, EgoLife became much more than a data set. It helped inspire many later projects on long-term memory, wearable AI, and first-person intelligence. It also changed my own path. A few months ago, I started a company working on egocentric AI, action model, and robotics. Without EgoLife, I don't think I would be doing what I'm doing today. I hope we can share more exciting work with the community very soon. Finally, thank you to the organizers, thank you to the reviewers, and thank you to everyone in the EgoVis community. Let's keep building things together and make egocentric AI better and better. Thank you very much.
Yeah, great. Great. And I'm wondering where he's walking. Like, I kept thinking, where is he walking? Anyone knows the answer? Traveling. At the airport. Okay. And the next award goes to Ego M2P, Egocentric Multimodal Multitask Pre-Training.
Thank you very much. Thank you very much for this second award. I'm really grateful. I'm really honored. So with more and more real-world egocentric datasets and unlimited synthetic data from EgoGen, we wanted to answer a question: is that can we really scale up the pre-training for egocentric 4D perceptions, like spatial temporal understandings in egocentric vision? So we trained Ego M2P with 8 egocentric datasets, totaling 400 billion training tokens across RGB video, depth video, camera trajectories, and gaze dynamics. And the model is able to perform any prediction from any modality to predict another modality. And when we scale up the training, the key challenge is that the egocentric datasets are inherently heterogeneous. Some datasets don't have depth, some don't have gaze, some don't have hand motion, and we propose to use masked modeling to unify our model and to have a single model that is able to perform many tasks across perception tasks and synthesis tasks, and the model is matches or outperforms specialist baselines while being an order of magnitude faster. And another question is that is Ego M2P really scalable? So in our follow-up work, Revive, it is not published yet. We further scale Ego M2P to more dataset and more heterogeneous modalities such as hand motion and body motion. And given a monocular RGB egocentric videos, our model can reconstruct both the viewer and also the view in 4D in a feed-forward fashion. So I'm really grateful that none of this work couldn't be possible without my amazing co-authors and supervisors. As I wrap up my PhD, I'm on the job market now, so I'm actively seeking for research scientist or assistant professorships. So if you find me a good fit, please reach out. Thank you.
And the next award goes to Ego XO4D, Understanding Skilled Human Activity from First and Third Person Perspectives.
Okay, so it's my honor to accept this award on behalf of the 101 co-authors of Ego XO4D. Fun fact, well, first of all, I like to invite the co-authors of this work to stand, and I think half of the room will probably stand. So thank you all. Not many people know that this effort was significant, not only in terms of number of authors involved, but also in terms of time and dedication. So I think it all started out several years ago at CVPR in New Orleans, where we met in person PIs and students to discuss fundamental question: how do we teach AI to recognize skills in physical activities from video? And following that in-person meeting, we had essentially weekly VC meetings for the following 2 years, discussing the nitty-gritty details to get AI to actually learn skills. And we quickly converged on this idea that we need to build AI that actually mimics the human way of understanding skills. So by effectively looking at other people performing the activity, so from the third-person perspective, but then remapping that observation onto our own first-person perspective. And so that led to the idea of synchronized capture of ego and exo videos. That also meant hiring an army of experts, domain experts, in a range of activities, including climbing, dancing, playing soccer, playing basketball, fixing bikes. And so it was a lot of fun because it meant that basically AI researchers had to work side by side with these domain experts and who were trying to teach us about these skilled activities. So the project really originated by an observation of a gap, a fundamental gap in the data for the computer vision community. But I should say that that idea traveled far, and so the impact of EgoXO4D, I think, is now recognized in a variety of fields, including cognitive science and robot learning. Finally, I want to thank Kristen Grauman for bringing us all together, and the hundreds of you who worked with us in order to make this possible. This was one of the most fun projects I've ever been involved with. Thank you all.
Excellent. And the next award goes to Expert AF, Expert Actionable Feedback from Video.
First of all, thanks to all the co-authors, Tushar, who's here, Georgios, Chris, and Kristen. This project came out when we were ideating what we can do with EgoXO4D that Lorenzo just described. One of the most interesting part of the data set, according to me, was we had expert annotations for the first time where experts watched people do things, and then they had spoken commentary about what they did correctly and incorrectly. And also the data set had pose sequences. So I think the presence of these expert feedbacks with the pose kind of helped us ideate that doing sports-based feedback generation would be a really interesting task for us to pursue, and that would also be interesting from application perspective. And especially I had this very I like watching sports in general, so it was also like a personal flavor to the choice of the tasks that we focused on. And I mean, thanks to Expert AF, then I kind of completely switched on to a lot of these physical skill understanding tasks and had several follow-up papers after that. And now, I mean, I want to go more and more into like the sports skill understanding part, which I think all started because of Expert AF. And yeah, I'm kind of happy that we came to this problem statement, and it kind of helped me shape my research afterwards. So yeah, again, thanks to all the co-authors for their guidance, and yeah, I'm looking forward to more progress in sports understanding. Thank you.
We have two more. The next award goes to HD Epic, a highly detailed egocentric video dataset.
Okay, so I think first thing to say is this really was a big team effort. So while I'm the one standing here, there's a load of other authors in the crowd. Maybe you want to stand up or wave hands or something. Great. Yeah, and I think this really was a particularly special project for many of us because it felt a bit like coming full circle. So quite a few of us who were PhDs on the original Epic Kitchens project then became senior authors on HD Epic. And we moved them from building the data set and doing all the annotation to really leading the project and even tricking our own students into doing most of the hard work. And we thought we knew what we were getting into because we'd already done this thing with Epic Kitchens. So we thought, okay, smaller scale data set, we're only going for 40 hours, not 100. Surely it's going to be more manageable. We were completely wrong. And really every component seemed to take on a life of its own. So the digital twins, the object movements, the how and why in the narrations, recipes, steps, even the VQA kind of became its own kind of large project within the dataset. And I still even remember sitting in Istanbul airport on a layover, checking the quality of the transcriptions with one panicked PhD student messaging me thinking, what on earth have we got ourselves into? But we made it through. And in the end, this really is a collaborative effort with like 15 students and postdocs really leading the work on this project. So the award is really a recognition of their effort. And hopefully the dataset is going to pave the way for a more detailed video understanding. So this is really kind of the unique selling point, is having this level of detail in all the different narrations. Yeah, and hopefully this can push forward video understanding further. So thank you very much.
What should I do? So it was that one. Okay. And the 8th and final award goes to Hot 3D, hand and object tracking in 3D from egocentric multi-view videos.
Hi. First of all, thanks to the EgoVis committee and the reviewers for considering us for this award. Really appreciate the recognition. And also thanks to my co-authors, Pierre, and others. This work was actually done kind of like cross-continent, half of the group was in Seattle, another half in Zurich. So shout out to Thomas and Cindy from the Zurich group who were not able to make it over here for this presentation. Looking back, I think Hot 3D focused on hand-object interactions, and we were quite fortunate in the timing of its publication. Like, it coincided really nicely with the uptick the community was seeing in interest on robotics and embodied AI, and how LLMs and agentic workflows can work in the physical world. And there was a lot of interest in how hands and objects interacted. And there wasn't also an interest in having a good benchmark, which had really these precise ground truth available for both hands and objects. And hopefully Hot 3D was able to help out over there. And looking forward into the future, I think one of the most common feedbacks was always around scale and the ground truth accuracy. Half the people wanted larger data sets, more objects, more people. And the other half were focused on, how can we get more accurate ground truth, better 3D mesh models, hand poses. And a lot of the follow-up work, it's really nice to see, has been focused on getting that trade-off relaxed even further. So Pierre had some thoughts.
Yeah, I want to thank the community, and I think the best reward for us is to see people using the dataset and not making complaint about it. So somehow it's, I think, the best reward we can have because they love the data, and the time we spend to make the API to make people be able to use the data, I think is the best reward for us. So it's don't underestimate this, make your data great and make the toolkit great, and it's going to help the entire community at the end. Thank you.
That ends this session. I would like to thank everybody who reviewed, thank Google DeepMind for the sponsorship, and congratulations to all the winners. And please, if you would consider next year to send your papers, we do read all of them and assess them. And for those who submitted and maybe didn't win, it was just a very high bar, but all the papers are greatly appreciated by the community. Thank you again. I think I hand over to Masashi next.
Okay, thank you so much for the invitation to present my research. The premise of this talk lies in the title. So I believe that our community has made fantastic progress on training models to see, but at the same time, most of the problems we care about, I think, require more than perception or recognition in the present. Consider, for example, the following application scenarios. For instance, an AI agent that warns you about a potential pitfall of an action that you're about to take. Or perhaps an AI assistant that guides you step by step through the execution of a complex procedural activity. Or even an AI system that observes and understands a coordinated effort by a team of people in a consequential setting such as a surgery, and understand cause and effect and comes up with a revised, more efficient plan. And so all of these scenarios do require agents or models that perceive, understand who does what, but also anticipate actions, guide those actions, and understand the consequences of those actions so that they can provide revised, more optimal plans. And so what I'm going to show you is that today AI models do really well on the perception side, not so well on the others. And I'll do so by surveying 3 recent projects from my lab. And I'll start off with Trudge Pilot, which is a model for anticipating the next actions of a user from a few seconds of wearable camera video. And as I mentioned, I believe that anticipation really lies at the core of AI assistance. If you think about it, an agent must know and understand at any time what the user is about to do in order to provide relevant contextual information. But if you look at these 3 different moments, well, each of them admits multiple possible futures. And if you simply train a model to minimize the prediction error, well, there is the risk that it's going to simply hedge and average over all these possible futures and get it wrong every single time. So in order to understand the problem, let's formalize it a bit more. Let's assume we are given as input a brief start clip capture from an egocentric camera, and optionally also a goal clip in the case of planning, which I'll discuss later. So this video context is then typically passed to a causal predictor, such as transformer, which generates a sequence of intermediate representations, Z1 through ZH, one for each of the actions we want to predict into the future. And since here we are interested in semantic prediction rather than pixel-level reconstruction, typically we want to use representations that are fairly high, such as latents from a VJPA encoder. And then these latents are passed on to a readout module, like an MLP, which maps each of these latent representations into a discrete action label. And the pipeline is very general. So in fact, you can actually instantiate it or approach it from 3 different perspectives. Action anticipation, where the goal is not given. Procedural planning, where the goal is actually passed in as an input, and the model must find a sequence connecting start and end. And even event prediction, where instead you want to train the model to classify a future outcome. And while the pipeline is fairly standard, a lot of research has been focusing on 2 aspects of this design. The first is what kind of conditioning signal can we add to the pixels in order to disambiguate the problem. And this is often necessary because, as you'll see, pixels alone often cannot really tell us what's the right future. And the second question has to do with the latent space, which, as I'll show, will greatly impact the performance of the prediction. So let me start from the first design choice. So what conditioning signal should we be using? And the natural solution is to use language. For example, we can describe in language form the intent of the camera wearer, such as whisking the eggs. And this, in fact, has been heavily used in prior work. And it makes sense because it narrows down the set of plausible future actions to consider. However, at the same time, it's clear that language is actually quite coarse, right? There are many different ways to whisk the eggs. One way is to be gentle and smoothly integrate the eggs. Another way is to be aggressive and splatter eggs all over the place. And the difference between these two ways obviously is not picked up by the description of the intent, which is the same. Is characterized by the actual motion used by the user. Interestingly, in the context of offline recognition of past action, as conditioning signal that has been shown to be quite revealing is the egocentric camera trajectory. And this is work that will be presented here at CVPR by Sherry Xu et al. And they noted that the camera trajectory recorded either from RGB or from instrumented sensors carries a lot of information to the point that actually by itself it can disambiguate the actions to perform. And this makes sense because the motion that causes the action also causes the head movement, which carries enough information to disambiguate the action. But in the context of anticipation, obviously, we are interested in the future camera trajectory, which is not available at this time. Nevertheless, it's interesting to consider if we had access to the future camera trajectory, would it help? And so we performed a simple experiment on a toy problem of a person shooting a basket. And we tried to train a predictor from the pre-shot clip of the person shown to be about to shoot the basket. We tried to basically predict the outcome. And when we used pixels only, we got an accuracy of 56%. However, when we conditioned the prediction on the camera trajectory, the future camera trajectory, so this is an oracle experiment, we achieved 93% accuracy. Again, this is not surprising, but what is really surprising is that the future camera trajectory itself is partly predictable from the pre-shot clip, from the video context. And if you condition the predictor on this candidate information, you actually force it to commit to one particular feature, and it ends up actually doing much better, 81%, recovering almost all the gain of the oracle trajectory. Now, this is a toy problem, but we confirm the same pattern on the entire EgoExo 4D atomic action dataset. And here you see the gain with respect to using only pixels in predicting future latents. And for example, we found here that using the future camera trajectory cuts down the error 20 times more than using the future atomic action levels. So again, this demonstrates that motion actually carries a lot more information than the actual language. And so these two diagnostics inspired the design of Trudge Pilot, which is shown here. So here's the idea. We take the video context and use it to retrieve K candidate trajectories from a bank of trajectories. These are future camera trajectories. And then we roll each of these trajectories through a causal predictor. And this is the key operation, because by doing so, we force the model to commit to one of the possible futures rather than averaging over all of them. And then by conditioning on this candidate trajectory, we obtain an action plan. And then finally, we use a scorer, a train scorer, to identify among these possible K action plans, the one that is most plausible. Okay, now I want to circle back to the second question that I posed. What latent space should we be using? So a natural solution is to roll out the sequences of latents in the original VJPA space. and simply pick the sequence that lands closer to the intended goal. And this works only if the distances in VJPA space relate directly to action similarities. But we found this to be certainly not the case. And you can see it here where we show that the blue bar, which measures the average pairwise distance between latents of the same action but coming from different videos, is actually higher than the average distance between latents from the same video but actually representing different actions. And so this is due to the fact that VJPA essentially optimizes visual continuity as opposed to action similarity. And so we fix the problem by avoiding to decode directly from the VJPA space. Instead, we project to a language-shaped action space, which we optimize using EgoVLP embeddings using a contrastive learning strategy. And so this essentially forces the latents to have distances that are representative of action dissimilarities. And the benefit of doing so is also that at test time, essentially readout reduces to a simple nearest neighbor operation on the EgoVLP action bank. So you don't have to train specialized classification heads for each taxonomy or each downstream problem that you want to tackle. Okay, let me show you some of the results that we obtained. And these are measured on EgoXO4D atomic action benchmark. On the left, you see anticipation results. On the right, you see planning results where the goal is given in a video form. And so the performance of our system is shown with the solid red line. And you can see that it, first of all, the plot shows actually accuracy of anticipation as a function of horizon, so the number of action steps predicted into the future. And you can see that the system actually outperforms considerably the green line, which is a strong VLM fine-tuned on this task. It also does a lot better than the blue line, which is our own same system, but not betting on a particular trajectory, so essentially not trying to predict the trajectory. And finally, I want to point out the really strong performance of the red dotted line, which is essentially the oracle. It's the model that conditions on the true future camera trajectory. And it does extremely well, which explains why our system that tries to predict that unknown camera trajectory also achieves strong performance on these problems. So we achieved similar pattern of results on planning. We also try to evaluate our system against really strong structural planners like ViterbiPlanNet or PDPP. And in all cases, we found our system to significantly outperform them, especially when the horizon gets really large. And we also have in the paper results on a variety of other benchmarks, including Ego4D Gold Step, EgoPair, and Epic Kitchens. And finally, I want to mention that we do not require any specialized hardware. In fact, we show that when we train on trajectories estimated directly from RGB, we get pretty much the same performance as when using trajectories from instrumented camera rigs like ARIA. Okay, let me transition to the second project I want to present today. And this is about procedural guidance. So imagine a user that wears smart glasses and tries to replace an alternator for the very first time. So we would like the AI agent to be able to provide in real time free-form procedural guidance in how to execute the task. And ideally, we want this system to really capture the specifics of the scene. So this guidance, for example, should refer to the particular parts or objects appearing on the bench of the user. Here is a formalization of the problem. We assume we are given a video history of what the user has accomplished up to this point. And we also have a natural language description of the goal. And the model must generate this free-form language plan. And because it's free-form, we evaluate it using an LLM as a judge across 7 different benchmarks with respect to the ground truth. And we consider 2 different formulations of the problem. One, which we call Socratic, where the video history is first transformed into a sequence of steps using a pre-trained VLM. And the other is instead a video variant where we feed video tokens from the history directly to the planner. And the fundamental challenge here is supervision. There are two types of sources for data in the literature. On one hand, we have small manually annotated data sets, such as Crosstask or Coin, which have been painstakingly annotated by human annotators that have labeled individual frames in these videos with step information. The quality is great, but there are typically few tasks that are annotated and few examples per task. On the other hand, we have big web corpora such as How to Handle Million, which contains over 1 million instructional videos, but no annotation whatsoever, except for the narration transcribed directly from speech. And traditionally, this problem has been approached by first training the models on the clean data, and then by deploying the model on the web corpus, trying to extract clean labels that are then reused to retrain the model. But as I will show, this pseudo-labeling causes errors compound and typically leads to an overall degradation of the performance. And so here is the observation that we make. We notice that, well, extracting clean labels from noisy videos is really hard. But conversely, it's much easier to take a proposed plan and check whether it makes sense against the noisy corpus. It is much easier because, well, that comparison can be carried out entirely in text space. And so here's what we do. During training, we let the planner generate multiple rollouts, so multiple candidate plans in free-form language. And then we take each of these candidate plans and compare it against the corpus by essentially performing an alignment between the proposed plan and all the narrations in the corpus. And again, this is a comparison that can be carried out entirely in text space reliably and efficiently. And then we take these alignment scores and use them as reward signals in a reinforcement learning optimization using GRPO. Now, in order to scale to the large size of the dataset, which in our case includes over 25 million narrations, the alignment needs to be really fast. And so we achieve that by using pre-computed sentence embeddings and by adopting a two-stage procedure. Stage one essentially performs fast retrieval by finding the top 25 candidates for each proposal. This is done using a fast, greedy, monotonic approach. And then in stage two, we refine this ranking using a global alignment, which is more precise. And here you see the side-by-side, the result of using the same web corpus, How to Handle Million, in these two different ways. So when we do pseudo-labeling, that's represented by the red bars, we actually often get degradation in performance. You can see, in fact, that these red bars in two out of the three cases, so we have three different model sizes here. These red bars are actually lower than the gray bar, which represents the base model before pseudo-labeling, before the fine-tuning. Whereas with our approach, which uses the web corpus as a verifier, we get consistent improvement across all three model sizes. We found that also this leads to increased procedural diversity, as shown here. On the x-axis here, we are measuring the procedural diversity of different rollouts for the same video history. And you can see that our model produces better procedural diversity and increased accuracy compared to the base model, whereas SFT degrades on both aspects. And this happens because essentially SFT forces the model to mimic a single ground truth plan, whereas our model credits the model for generating plans that are overall consistent with the corpus. Okay, let me move to the last project I want to present today. So far, I've only talked about systems that support a single user. But if you think about it, most consequential settings actually involve teams of people working together towards a certain goal. And in such scenarios, we're not simply interested in models that can understand who does what and when in the video, but the system must also be able to understand the intent or why certain actions are being taken. Must also be able to perform counterfactual simulation. So in a sense, consider what-if scenarios in order to come up with a better plan for what to do next in a coordinated fashion. And so we started thinking about, okay, what are good data sets for testing or training such systems? And we basically realized that there is a very significant gap in this area. And this happens not only because, well, most of the video data sets are about single user activity, but it's also because if you take the standard real world video data sets, well, they only test perception and temporal reasoning. They do not have any form of annotation for causal and counterfactual reasoning. And this is due to the fact that, well, it's really hard to annotate real-world videos about daily life in terms of cause and effect. So to address this gap, the community has come up with synthetic environments like Cleverer or Fire, where you can actually perform full simulation of causal and counterfactual generation. But these environments are obviously highly synthetic, and so they lack the realism of actual video and actual human interactions. And so this gave us the idea to create a novel large-scale dataset called SVI Bench. SVI stands for Strategic Video Intelligence. And this is born out of 35,000 hours of team sport broadcast video. And the benchmark tests 4 different capability levels: perception, who does what, where, and when in the video; reasoning, why did that action happen, what are the consequences of that action; simulation, where we test the model's ability to generate what-if scenarios; and finally, agency, where the model must make sense of millions of video clips and extract evidence in order to answer complex questions. And so we chose team sports because, well, they check several boxes. First of all, they represent real-world human-human interactions, coordination, also adversarial behavior. But most importantly, they contain free verifiable outcomes of cause and effect in terms of objective measurements like maintained or lost possession, or shooting or scoring outcome. And furthermore, they come with lots and lots of metadata that really allowed us to scale to unprecedented size. On the left, you see how our benchmark compares to prior related work across the meaningful scale dimensions like number of video hours, number of annotated actions, number of expert commentary sentences. And pretty much for each of these dimensions, our system exceeds prior work by nearly an order of magnitude. But most importantly, we believe that this is the first benchmark on real-world multi-user video that tests AI capabilities across these 4 levels of the stack. So in order to produce this benchmark, we essentially processed the many modalities available to us. So we obviously have raw footage, video, but we also have rich expert commentary from the broadcasters. We also have play-by-play logs. These are essentially annotations provided by professional annotators employed by sport leagues, and that describe every few seconds everything that happens in the video. And finally, we also have game reports written by journalists and game and season statistics. So we built a data engine that processes all of these modalities and generates nearly automatically benchmark task instances. So the data engine takes care of aligning temporally all of these modalities. It performs entity resolution. It uses LLMs to synthesize automatically benchmark task instances. And finally, we have a quality control stage where we remove hallucination by cross-matching against the original modality and by also making sure that each instance is hard. It requires visual understanding. So let me give you a few examples, and I'll be focusing on the higher level capabilities because you are all well accustomed to the problems of perception. So here I'm showcasing a benchmark instance that requires strategic causal reasoning. And in this case, we give the model a full basketball game to watch, and then we ask the model to identify the strategic defensive change that was employed by one of the teams in the fourth quarter. And if you look at the responses by these AI frontier systems, they look really plausible and seemingly make sense, but they're actually all opposite of what truly happened. And so this really shows that the perception that these models perform is disconnected from the causal reasoning. In this other example, we asked the model to predict who's going to win the game at 4 different times within the game. And so it's funny that the first 3 times, the system actually picks the wrong team with a self-declared confidence of 99%. And then the 4th time, the model flips completely the decision, still with a confidence of 99%. And so this tells you that the models have really no sense of the ambiguity about the event they are asked to predict, and also they don't really know their own confidence. This is an example of future generation, where we give the model an initial frame and a language description of the actions that we want to see played out in the video. And on the left, you see the ground truth video, and on the right, you see the generation. And as you can tell, the model is barely able to synthesize the players at the right spot, let alone render the actual action. So if you look at the performance across the 4 different pillars, there is a dramatic degradation. So the models start out at about 70% on perception. They fall down in the 40s and 50s for reasoning and counterfactual simulation, and they collapse down to 5% only on agency. Now, why does this happen? Well, I mean, one could say that it's error accumulation, because each capability builds on the previous capabilities. So to test this hypothesis, we actually performed Oracle experiment where we replaced video input with ground truth textual description of everything that happened in the video. And we found that the model, in many cases, is still unable to do much better than before. The only task where there is a significant improvement is agentic reasoning, where GPT moves from 4% to 54%, which is dramatic gain, but at the same time, it shows that there are still 46% of questions that GPT gets wrong, even when you give it perfect perception. Are the tasks simply too hard to solve? Not really, because humans, expert humans, can actually do it well. And it's interesting to see that the gap between human and AI performance actually mirrors the cliff that I showed you earlier. So AI is almost on par with humans on perception, but then the gap widens considerably as you move to higher level capabilities, such as causal reasoning or forecasting. Okay, so across the 3 projects I presented today, I hope I convince you that video models today have indeed learned to see quite well, but there's still a lot of work to do to teach them to anticipate, plan, and perform complex reasoning. And I want to acknowledge the contribution of all my collaborators in these projects, and I'm happy to take questions if there is time.
Yeah. Is there any question?
I have a question about the first third of your talk, where you declared a good conditioning signal is camera pose. So there's a whole spectrum of conditioning signals you could use. I've seen people use full body, joint positions, hand key points, and so on. And it gets more and more complicated at the point where people use full segmentation maps of the future and say, that's a conditioning signal. The more complicated you make your conditioning signal, the harder it is to plan. So I was wondering what you thought about why camera pose was the right thing for you. Maybe it was task dependent, or in general, what is the best conditioning signal / action space to use?
Tushar, you just mentioned, the entire sequence of future work that we intend to pursue. So those are some of the directions that we are interested in. But yeah, you made the right point that egocentric camera trajectory is cheap, can be obtained from any arbitrary wearable camera, whereas some of these other signals may require specialized hardware, or certainly lots of annotations that are not always available. So those are definitely interesting directions to follow.
So if budget was not an issue, what would your action space be?
Oh, everything.
Thanks.
Hi, thanks for the great talk. I was a bit curious about the last part where you were mentioning about counterfactual reasoning. Or maybe I missed it, but I was curious how you generate the annotations for that. Is it that you just ask the LLM that, okay, in this situation, what if this had occurred? What do you think could happen next? And then you verify it with human annotators?
Yeah.
Or?
Well, we know the future, right,
Okay.
in the video.
Right.
And we have a detailed annotation of how the actions are going to play out. And so we give that kind of as the counterfactual hypothesis. And we ask the system, okay, imagine that, in the future, things unfold according to the following script, and we ask the model to generate that future, and we test the fidelity of that future video generation, not only in terms of pixel to pixel comparison, but also in terms of, for example, are the actions that are generated recognizable as the original ground truth. And we found that that's where actually AI systems break down, particularly because they can roughly generate people at the right locations, even with the correct body poses, but they are really unable to synthesize the motion that makes the action recognizable.
I see. So it relies on the actual future that plays out.
That's right.
So I'm wondering, in this case, do you think there might be a bias towards more, let's say, common kind of future actions that might take place? But what if there's some long-tailed kind of future actions which might occur more rarely?
Yeah, we have lots. Yeah, right. That's a good question. But we have lots of videos. And so, we also, because of the scale of the data, we certainly have lots of examples where you have similar precondition and different futures. And so model trained on such massive amount of data should be able to synthesize all possible variants of that future.
Thank you.
Yeah, thanks the Professor Lorenzo again.
Hello, everyone. I'm Willy. I'm a second-year PhD student from France, and I'm very happy to be here on behalf of my team to present Action 100M. So that's a research project we've done back when we were at MetaFair. So here you can see some samples of that dataset. So what's Action 100M? Sorry, do I have to use the mouse or? Okay, all good. Yeah. So Action 100M is a dataset built on top of How to 100M, which Lorenzo described a bit earlier. How to 100M is a very large-scale narrated instructional video in the wild, so mainly sourced from YouTube videos. They don't come with any annotation other than YouTube metadata most of the time. So essentially what we do is we build an automatic annotation pipeline to annotate action on top of How to 100M. So that results in about 150 million video clips from the 1.2 million source videos from How to, which represents about 15 years worth of video action data. So two interesting parts in that data set. The first one is that it comes with both action and caption and at two detail levels. So brief action, which is basically just verb noun, and more detailed caption where you have more basically detail about the action being performed. And also interestingly, we propose a hierarchical annotation for each video. So we have the top level action and then we divide it into more granular annotation for each sample. So here I'm gonna mostly talk about the dataset pipeline, how we built that dataset. So it's mainly three parts. The first one is temporal segmentation to build that hierarchical tree of segments, and then more standard caption generation round plus an aggregation round. So the first step is maybe the most important one because, as we said, it's a raw video without any annotation label. So we need to find a way to find boundaries in those instructional video. To do this, we use a VJPA2 model to extract video embedding from the entire video. So we run it in a sliding window fashion across the entire video, 64 frame window with 8 frame overlap. That gives us a continuous video embedding for each sample. And we perform agglomerative clustering. So this is a bottom-up clustering approach with word linkage. So at each time we merge clusters that that yields the lowest variance across the entire cluster pool. And that gives us basically this hierarchical segmentation or segments for each of our sample. Once we have that, we run a straightforward generation pipeline. Here we have two ways of doing it. Because we have this hierarchical tree down to very short node, up to 0.5 seconds. The leaf node, so the bottom level node, we do image captioning using a Llama model. And for all the other nodes, we do video captioning because they are longer, so understanding dynamics is better for the last step of aggregation. So basically 2 modes of captioning for each node. And at the end, we use a very large language model, so GP2SS here, to basically provide for each node the video caption, the caption from all the children node. This is a way to add consistency in the final caption provided in the node. And also all the YouTube metadata, whether it's like title of the video, instruction, or whatever we could find, to the GP2SS model, and do 3 rounds of self-refine. So we feed the output back to the model and ask to eliminate some noise, actionless segment, too short of a segment, and etc. And so that essentially is the entire pipeline to generate that data. To validate the quality of our generated data set, so I probably won't have time to detail too much about the architecture, but VLJPA is a model we proposed in our team earlier this year. And essentially, we pre-train our VLJPA model mainly on Action 100M and show that we can outperform CLIP, SIGLIP, and P on a bunch of zero-shot action recognition tasks, despite having less sample scenes and having a comparable model size. Because it's a VJPA-based model, it's obviously better at motion-centric tasks like SSV2, but slightly worse on appearance-based tasks like kinetics. That's also the data set we use to pre-train the model with which we got first place at the Action Recognition Challenge this morning. And okay, I think I'm about finished. If I can play this video. Okay, this is just a example of annotation. You can ignore the rest because this comes from another work, but essentially the caption annotation, the action annotation can be found on the left side. That's given a certain depth level we choose in our hierarchical tree of caption. Okay, I'll let it play if you want to take a look at the sample, but essentially that's it for me. Thank you.
Hello everyone, I'm Hao Li. I'm the research scientist from Wikipedia. So we are dedicated to building the future of physical intelligence, and I'm thrilled to walk you through our latest progress in the Wikipedia. So we all know the Gen AI took off because of massive accessible data like text, image, and code. But embodied AI pipeline is currently broken. So why? Because you can just grab the physical data from the internet. So there is a massive real-world data bottleneck. Without scalable annotated data, robots simply cannot learn to navigate our world. So this is why we come in. Our solution is straightforward but powerful. We capture structured real-world interaction data at scale and at an extremely low cost. We take raw, messy, real-world movements and turn them into structured annotations that embodied AI models can actually digest. So we recently released our dataset in the wild human experience 10 million. The response has been incredible. It quickly reached out top 3 among all datasets in Hugging Face. and with over 2.1 million downloads. So how do we capture all this data? We just released our full-stack hardware Homey 1, Gen 1. We built a full-stack low-cost portable data capture device. It features 4 fisheye cameras for a true 360-degree field of view, and up to 50 hours of storage and 5 modality sources. And it's designed to be warm simply to capture general human experience. So here's a demo video. So you can see this is not just clean, simple lab data. We are capturing high complex cluttered real-world scenarios, and it's extremely what robot needs to process and need to understand and need to train. So beyond this massive data, we introduced the first benchmark of our spatial foundation model, Spatial Bench, which covers 19 datasets across 5 domains and tests through across 42 models with 6 paradigms. And further progress on corresponding data set and model to boost the performance of spatial foundation model on robotics and egocentric domains. Okay, so moving forward, we are also pushing the boundaries from geometry to understanding. So we will release the next generation data we call Xperience Plus. So we are lifting data into high quality 4D understanding. This will include fully annotated labeling without human intervention, and equipped with high quality 3D object detection across the entire scene and a long horizon 4D tracking across all interacted objects that can track object in the wild for up to 5 minutes. All of this is powered by our property AI annotation pipeline, and this is an end-to-end full stack. Raw data from our R-series hardware passes through our foundation models, which generate understanding for humans, objects, and scenes. We then output this as a data as a service process to train the next generation of world model or our robotics model or spatial foundation model. So we are laying the groundwork for the next major leap in AI, and we invite you to build the future of physical intelligence with us. Thank you.
So I'm Tengda from DMind. Very happy to be here presenting our work called Unique Lives, Shared World, Learning from Single Life Videos. Yeah, it's in collaboration with so many people, so I'm waiting for the slides too. Okay. Yeah, so we argue that there are two types of learners, or two types of learning paradigms. The paradigm one is the machine learner. Essentially, it's how currently the big models are trained. So the models need to learn from a massive and aggregated data set, and they rely on the web scale diversity to train a working or strong model, and the data is always shuffled to make it IID. But that's not how the human learns. So we argue there's another paradigm of learning that is a human learner, where human learns from a single and continuous video stream, and the data is highly redundant, highly correlated, and it's sequential and contextual, which is very different to how the machine is learned or is trained. And we call this as a single life learning. Essentially, everyone here is performing single life learning. So the key question of this work is that we want to know if the web scale diversity is a necessity to learn visual representations. Okay. So we have this shared world hypothesis. We think that everyone learn from distinct visual experiences, that we learn our visual representation from our life, which is joined, which is very different from each other. And all of this, the visual observation that we obtain are from the same underlying physical worlds. So we think, we hypothesize that the model trained independently on disjoint data streams will eventually develop a functional aligned representation, similar to how human evolves. Like we learn from our own experience, but we end up with a visual representation that seems to be common and seems to be shareable, right? We all know how to fetch some objects, or we all know like the height of something, etc. So in this work, we try to simulate this process by training neural networks. We propose this single life learning paradigm. Basically, we train distinct vision model on egocentric video streams captured by one individual. And we start these experiments on geometric understandings. So we want to know, we want to ask two questions. Is this single life models align, and do single life models generalize? I will go a bit into the details of the model. Okay, so for the model architecture, we adopted this Quirko or CMMAE architecture. It's essentially take two video frames and mask some patch of one frame, and the model is asked to predict the missing ones from the other. So we do not change anything from this model. The key components that we played with in this paper is the data, is like how we choose the data to train this model. So different to how conventional video datasets train. Okay, the GIFs are still loading, but it's fine. So typically, if you have a dataset, you will combine all the videos together, train your single video model, and claim I got some performance on this dataset, right? But actually, all of these datasets, like most of these datasets, they are collected by different participants. For example, this HD Epic dataset, it's collected by 8 participants, and working towards are 8 different lives. 8 different cities. So we propose to split this dataset in a way that we train one single model on one single life. So for HD Epic, for example, there are 8 participants. We group all the videos of one participant into like one dataset. Then we train model 1 on this. And same, like we train model 2 for the HD Epic participants too, etc. So we eventually train lots of models. And then we want to know the question we plan to ask, that 1, do they align? Second, how? So 1, do they align? Second, if they generalize. Additionally, we also have comparative lives, or like baseline lives. They are non-lives. They are Minecraft lives. So it's very fake. It's like simulated lives, and also static lives, which is essentially a static video frames. And we also train single life models on this data. Then we have 2 questions, as I said before, that the first question is if they align. So we define this mutual KNN objective as the alignment objective. Essentially, here we take 2 models, and we take one. So on the testing set, we take one query patch from the source frame, and we ask model A that which patch you think is semantically close to this query patch. So the model A might give us a heat map like this, and then we ask the same, like we do the same nearest neighbor retrieval for model B, and model B will also propose, okay, another region seems to be close to the source patch. And if the model are aligned perfectly, we will see these 2 heat maps should be identical. So inspired by this, we propose this IOU of mutual KN of model A and B, then we take the mean. So that's our alignment score. It's ranged from 0 to 1. 0 means no alignment, 1 means perfect, identical alignment. So I will quickly share a few key findings. the first finding is that so if we monitor this alignment and we train multiple single life models, as I said before, we find there is a phase shift that if the video or if the life of the data is longer than half an hour or 1 hour, this model start to see some alignment in the geometric representation. So you can see that the model trained on a few seconds, certainly they do not align. And for the models trained on like more than 3 hours or so, they mostly align. And the alignment start to plateau. So it's interesting finding and seems to be consistent in different data sets as well. And on the right-hand side, we combine all of the single life models together in a big heat map. You can see that like the data from the same pattern, like kitchen activity, for example, they tend to align with each other much better. And this non-life tends to not align with others. Okay. So last slide. We also test the generalization capability that we evaluate some depth estimation, etc., some geometry related tasks, and also we see similar trend that the longer life we train, the models will get better and get close to the upper bound where it's trained on diverse web dataset. Yeah, so it's a quick presentation, but yeah, thank you very thank you, and feel free to check out our website and paper.
Thank you.
Okay, hello everybody. My name is Alex Delijas, and I'm super excited to briefly present you our work FunRec, reconstructing functional 3D scenes from egocentric interaction videos. Over the past decade, we've seen a lot of progress in capturing real-world indoor 3D scenes, which enabled the creation of many datasets with high-fidelity reconstructions and rich semantic annotations. However, these datasets, the reconstructions they contain, share a fundamental limitation. The scenes are static and non-interactable. So, for example, articulated components in the scene like doors and drawers cannot open. This brings us to a significant question. How can we transition towards functional 3D scenes where every articulated component can be interactively manipulated and the scene state can change? So in this project, we built on a pretty simple idea that human interaction is the most natural way to discover how a scene works. In our setting, a human is exploring a 3D environment and at the same time interacting with the articulated objects in it. Given an input RGBD video from a head-mounted or a handheld camera, the goal is to reconstruct the static scene and also by tracking the human-scene interactions to discover and reconstruct each articulated part along with its kinematic parameters. To give you an example, here is my kitchen in Zurich, and let's try to build an interactive replica of this kitchen. Here you see me interacting with the articulated parts in it, like opening drawers and cabinets. And what you see here is a 4D animation. It's essentially the output of our method. The output is a functional 3D digital twin that is temporally grounded. So at every time step, the state of the 3D reconstruction matches the state of the scene in the real video at the top right. Our method reconstructs the static scene and its interacted part in canonical frame, including the object interior. So for every moving component, we discover its articulation parameters so that the motion is physically plausible and also at the same time estimate the precise pose at every frame. Beyond replaying the capture interactions, the reconstructed digital twins are fully interactable. So by adjusting the joint parameters of each part, we can freely control the state of the scene. And because all part displacements are metric, the digital twin is dimensionally faithful to the real environment. The output is also simulation compatible, so we can export it in URDF or USD format that can be loaded directly into physics agents. Here you see my kitchen into a NVIDIA Isaac sim, where we interact with the articulated parts by applying forces. We designed our system to be training-free due to the scarcity of real data on this task. In the first stage, we use a video language model to split the long video into temporally contiguous fragments. And each fragment is classified as either static, when there is no interaction happening, or dynamic, when the user is interacting with a single articulated part in the scene. Each fragment is then processed and reconstructed independently. So to process the dynamic fragments, we first estimate the camera pose and factor it out, and then estimate sparse 3D point trajectories. We use those as geometric evidence to identify and densely segment the moving part on each frame, and then run a robust optimization to estimate the articulation axis and the per time step part pose. With that, we can reconstruct the part in the canonical frame and also the static background. Afterwards, we globally align all reconstructed fragments together to get the full functional 3D scene. And since we have retrieved the kinematic constraints, articulated parts can be interactively manipulated. To evaluate our method and also motivate future research on the topic of functional 3D scene understanding, we introduced 2 new datasets. The first contains in the wild human-scene interaction videos in the real-world indoor spaces captured with a head-mounted RGBD camera. And the second contains photorealistic simulated interactions across synthetic indoor scenes, and we render it with Omni Gibson. Both datasets come with rich annotations, so they contain posed RGBD video stream, synchronized with dense 3D geometry, motion of articulated parts like interaction intervals, and also textual action descriptions. That was it. Thank you so much, and I'm very happy to answer any questions now if we have time, or feel free to drop by our poster later today or at the main conference. Thank you.
Thank you.
Yeah, thank you very much for the introduction. Very happy to be here. Okay, so I'm going to talk about what I am most interested in research, and that is details. And this is very much to the annoyance of my students when they think we've nearly finished writing the paper and I'm sending fussy remarks. But I think details are super important, and they're important in a lot of different aspects of life. So if you've ever tried to learn a skill, you'll probably recognize this, but here's just 2 examples of skills I've been trying to learn recently. So trying to learn the barbell squat, generally the exact action is the same. You're bending your knees, you're holding on, everything is the same. But then there's a load of details like how much your back is bending, how much you're tensing, all these type of things that really matter. Same in wheel throwing pottery. The motion is pretty similar, but how much force you're exerting at every point is really crucial to making this a success. So details really matter, and they also matter in a lot of really important application domains. So if you're trying to, say, learn how to do surgery, then the details of where you exactly put the suture and how much force you pull through is super important. If you're trying to ultrasound a heart, they're going to look pretty similar to each other, but the details of how each moves differently is going to be super important. Okay, and then this is why I really like egocentric vision, is because it gives us a really good view of these details. So rather than having to deal with all these occlusions, we can really see what people are focusing on and all the individual details of what they're doing. Okay, so this is kind of my goal in research, is to be able to understand these details. So rather than having these kind of coarse-grained descriptions of a task or even just descriptions of what is going on, really be able to understand how different actions happen and go even beyond the detail you see here and really understand every single aspect of what is going on in the video. So something maybe a bit more like this, where you can really recognize where each body part is positioned, how fast everything's going, all these types of different things. And ideally, I'd like to be able to do this in all sorts of different application domains. So particularly interesting to egocentric is maybe surgery, all these like chemical videos you see at the bottom, but I think there's a lot of different cases where we'd really want to be able to understand the details of videos. Okay, so then the question is, can we already understand these details, at least in domains that we've maybe already seen before? So this is part of what we investigated in HD Epic. This is a much larger scale project where we collected a really detailed egocentric video data set. You see some of the videos here. And the selling point of this data set really was the level of detail. So for instance, we're annotating every time an object moves in 40 hours of video and really grounding these movements in a 3D digital twin of the environment. And we're recording new data so that we can record details such as the person's gaze, and we have access to the participants so we can ask them details like what recipe they did and how they adapted it. And I'm not going to go into a full explanation of the data set, but I want to focus on one particular aspect, which is the detailed narrations. And these are detailed narrations of each individual action happening in a video. And here, rather than previous data sets that are kind of just capturing verb and noun pairs, we're really capturing how everyone's doing the action and also why they're doing each individual action. So here's just some example, so you can see how detailed the narrations are and really how temporally quick they are. So each time the action changes, we're getting this kind of long sentence description of what's happening. Okay, and then going back to this original question of whether current models can really understand this level of detail to determine, for instance, how action's happening, we have this VQA benchmark in HD Epic, and I'm just going to focus on this fine-grained action part that has these types of questions. So for instance, how did the person do the pick-up bowl of coconut milk action? And then you have different choices that are all potentially plausible. And what we see is current models are really pretty bad. It's only a 5-way multiple choice task, so this task could be made a lot harder. But what we're seeing is most models, like for instance on the how question, they're around 20%. The best is around 40%. So really a lot of room to go in here. And this is the same for the rest of the VQA data set, really, the VQA benchmark. So models are generally a bit better at these coarser-grained aspects that focus on like the kind of recipes and the steps, but things like the object movements or the 3D or the gaze, they really struggle with, same as the fine-grained actions. Okay, so my conclusion to do current models already provide detailed video understanding is no, well, there's still a long way to go here. And I think part of the reason for this is really lack of data. And I don't think that there's been so many different efforts of people in this egocentric field to collect some really good quality egocentric data. It's not the domain we're lacking anymore. I think it's really the labels we're lacking. So we just don't have labels that describe people's motions that are this detailed, and part of that is it's really awkward to make this description. So you're just not going to find this type of data on the internet. And it's really hard to kind of scale this up. So we did this for 40 hours, but going beyond this I think would be potentially a little bit crazy. So I think part of the reason models are struggling is because we really can't extrapolate beyond what we've seen on the internet. And I think this is, in general, a broader problem. So we also did some work in the image domain where we had these kind of 3 tasks that we were pretty certain weren't in internet scale data. So classifying circuit diagrams, retrieving historic maps, or mechanical drawing retrieval. These are aspects of data that are really hard to find online in scale. So Yonhua made her best efforts in doing this and only found like a few hundred samples. So we tested how well models at the time do with this, and really it's quite poor. At least 0 shot is pretty bad. I think these are results for the historic map retrieval. You can use these parameter efficient methods like LoRa or depth format to improve, but there's still quite a way to go, and even with our best efforts to improve this, I'm not going to go into details of what we did, but we had some kind of tricks to improve this, and still, even on the best backbone with our best baselines, there's still a long way to go. Okay, so this is what I'm focusing on in research at the moment, is this kind of low resource data. So going beyond the internet scale data, particularly looking at scenarios where we have really limited data, the problems are really fine-grained, so you really need to pay attention to details, and they're also potentially from a specialized domain, like egocentric vision, so where you need kind of different knowledge to be able to work out what's going on. Okay, so now on to how do we actually go about solving this. So we've done some initial work in this already. I'm going to first talk about adapting how we go beyond internet scale data by adapting existing knowledge from the data. And then I'm going to talk about how we can extend this to new knowledge. And I'm going to do this in 3 different ways. So looking at new labels, looking at new domains, and looking at new modality combinations. Okay, so first, adapting existing knowledge. Okay, so we did this study recently, in fact it's on arXiv today, on how best to adapt video models. So there's pretty commonly in adapting video models, you start off with this really nice strong video backbone, and you maybe learn some linear layer on top of this to adapt to your task, and maybe you do some fine tuning. But of course now there's different ways to do this. You can put a probe on your task head to really make to really change the representation specifically to your task. And of course, you can do parameter-efficient fine-tuning to not just tune the last layer and tune the model parameters. But no one had really looked at how these different things interact in video, so how the probe and the PEFT interact, and how to kind of distribute the temporal context. So we looked into this, and we have a few questions, so I'll go through them. But yeah, it's a question of really which methods are best for video and how we best set this up and allocate temporal context. So we looked into this with a few different benchmarks, all again, kind of benchmarks that you don't find much data of online. So they're all data sets that are a few thousand samples, naturally, and the different reasons you might not find so much data online. They're either a more fine-grained task, or they come from a particular domain, or they've got like really dense annotations, so it's hard to annotate. But we categorize these into 3 different categories, so appearance, motion, and spatial. And I'm not going to go into the full details of the study. You can look at this online if you're interested, but I'll give you the kind of highlights of what we found. So, when to adapt an image model versus a video model. So this is particularly important as there's a lot of work in adapting video models or adapting models for video that go from an image baseline to video. But what we actually found is that there's really no reason to do this. We have strong video models, so unless you really want good, dense spatial predictions, then you'd use something like Dino. If you don't want that, if you just want either motion understanding, even appearance understanding, you should really be adapting a video model. Which method works best? What we found is it does depend what task you're doing as to where you should adapt your model. So LoRa is best for spatial and motion because of where it actually puts the adaptation, whereas AdaptFormer is better for spatial tasks. And all of these are better than image to video PEFT. Which probe works best? So this is very task dependent. So there's a lot of work doing individual different probes for different tasks. But if you combine this with PEFT, you no longer need this task-dependent probe. So then an attentive probe will work pretty well, and you can kind of ignore this task-dependent probe design. Okay, then on to maybe the more interesting bit, which is how we distribute the temporal context. So, like I said before, there's a lot of works that are using this kind of static backbone, adding the parameter-efficient fine-tuning later to kind of do the temporal modeling. So we ask, is this actually the best way to do it? Okay, we already find results that show this is not. So then we asked, how do we actually allocate this temporal information? One option is maybe to put all of the temporal modeling in the backbone and then just do the parameter-efficient fine-tuning individually. Or we can put temporal modeling everywhere, or we can even change how much temporal modeling is done in each individual section. Okay, so when we looked into this, we had 2 more questions. So one was, do input frames or temporal modeling matter more? The answer, maybe not so surprisingly, is input frames matter most for appearance and spatial, but it really does help to have some temporal modeling still, but motion tasks really benefit from this temporal modeling. So best to have this there. And then the last question we asked was, how do we actually distribute the temporal context? And what we found here is you really want to allocate this selectively. You don't want to just give all the components of your model, the probe, the PEFT, the backbone. You don't want to give them all temporal context. Temporal context is most useful in the backbone, but it's super expensive. So what you can actually do is have a backbone that maybe has a temporal context of like 2 or 4 frames, and then put more temporal context in the parameter-efficient fine-tuning to compensate, and this will make your model much quicker without so much drop in performance. Okay, so this was how we can go about adapting existing knowledge, and we find, okay, there's models that already exist and can adapt when you have like a few thousand data pairs to adapt with. But then how do we go about extending to new knowledge? So the first work I'm going to talk about here is trying to extend to new labels. Okay, and what are new labels? So I think the thing here is that it's very rare you're going to encounter something wholly new. What you're maybe more likely going to encounter when you want to make different fine-grained distinctions is maybe splitting an existing concept into finer-grained ones. So for instance, if you've got dropping something and it's important to you how something is dropped, maybe you want to split this into things like dropping something into something, dropping something behind something, these kind of details. Okay, and this is obviously super easy to do with language. You can have your video text space, you've learned it so that your videos are close to dropping something, and then hopefully you can just add a new text in, like dropping something behind something, and this will be close to the video that shows this concept. Okay, so that's at least a hope. Whether it works or not is a different thing, but it's easy to try and do this with a vision language model. So what we asked is, can we actually do this without having any language in the model? So what we want to do specifically is we want to take a model that's already been trained and adapt this model in some small, subtle way. So we want to take these categories like dropping something and divide them. And we want to do this by just editing our model. So we don't want to have retrain, we don't want to have access to all the old data. In fact, ideally we want to have access to as little data as possible. And we just want to make a small edit that preserves most of the model performance and just splits these categories so we can make these finer grained distinctions. Okay, so how do we go about doing this? We can actually do this in a zero-shot way without any video data. So we start with this category we want to split, so pushing something, let's say. And okay, so this does only work in a kind of the situation where we do have this mix of coarse and fine-grained categories already in our model. So we make this assumption that, okay, we have pushing something, we want to split this, but we have these other categories like poking something so it spins or poking something so it falls that do make some fine-grained distinction. And what we do is with these, we can kind of make this pseudo-coarse category. So we find all the things that have a shared concept like poking. We average these, so this is the classifier weight space. So we average these classifier weights for poking something so it does something else together. And we get this kind of pseudo-coarse category of poking something. Then what we can do is extract this kind of fine-grained distinction by doing the fine-grained category poking something so it spins minus poking something. So something like this. This gives us something in the classifier weight space that describes this subtle distinction, something like so it spins. And we can build up this kind of nice dictionary of these things. We do use text here to kind of index this dictionary. There's no text actually in the model itself that we're editing, but text is a convenient way to make this dictionary. You can also do it with attributes as well. It would still work. But we make this dictionary, and then what we do, going back to this category we want to edit, we very simply take the things we want to split it into, find the similarity in what already exists, and add these distinctions onto the category we want to split. And I think what is so surprising that this works well is that we don't have this big data set where we have all these combinations. Quite often, if we're seeing these like small modifiers already in the model, there's maybe only one of these, like in one combination. We're not seeing all these different permutations. So it is, I think, quite interesting that the model can kind of split these out at the classifier space. Okay, and this is training free, no video data. What we can do to make it a bit better is do some training, still without any video data, but what we do is a kind of meta-learning where we have our weights of these different modifications. We train this small MLP to make predictions to go from the language description of this to the classifier weights, and this can adjust classifier weights a bit better to the target action and also handle cases where we really don't have any example of this in training. Okay, and this works surprisingly well. So we're starting from this fixed model and we're just trying to subtly edit these small categories. And our kind of like alternative baseline to this is taking the videos that were classified as the old category and then giving these to a VLM to be able to say, okay, which category do you think this should be split into? And ours actually works much better than the VLM in terms of the new categories and maintains similar performance on the old categories. The other case it works pretty well is if we do have some data, we can also use this method to make some initialization to then do some fine-tuning. Okay, and then where does it work well? So it doesn't really matter how many categories you're splitting into, works pretty uniformly across different categories. It does, however, matter what distinction you're trying to do, and this depends on like what the model was pre-trained on originally. So generally, direction is a lot stronger than something like how successful the action was. And what we find is also that the model is better at doing things that have these direct analogies with these modifiers in the original model training, but it also does pretty well without having any kind of correspondence of what these small modifications should be. Okay, so this is a zero-shot way to kind of edit categories in video-only models, and I think this is really interesting because, okay, it's something we could already do with language, but I think it's super interesting that we don't actually need language in the model already to do this. Our video models are already kind of semantically decomposable in terms of the concepts they contain, and we're only really looking now at the classification layer, so we can already extract some of these concepts without actually having any video examples. And so I think the question is, what if we could extract more? If we really knew what our models were doing and had a bit more explainability, we could do a lot of stuff with recomposing different concepts to be able to get new categories. Okay, so that was how do we extend to new labels. Now, how do we extend to new domains? And so this was a work we did a while ago, but the key intuition here was to be able to generalize to new domains, we want a signal that is kind of obviously more generalizable across domains. And in video, I think really this is motion. So rather than having these methods that really extract the spatial similarity, so like with contrastive learning between different videos, or even contrastive learning between image and text, or even more modern pre-training methods still really kind of focus on this kind of spatial similarity. They don't really understand motion so well. So what we did was have a way to actually make the model learn motion. And what we thought of was, okay, the current data we're training models with really doesn't have that much motion in it. So we actually inject some motion into the data, and we inject some, just by kind of moving a patch of the video, and we inject this motion into two videos with different backgrounds. So then the only commonality between these two videos is the actual motion we've injected, and then we learn the similarity between this. And this works in a kind of video-only setting where we're doing similarity between two videos with the same motion, but we can also extend it to a video language setting where, because we're injecting motion into the video, we know what motion this has, and we can actually make this way to automatically describe it and then paraphrase it to give it the variability. So then we can also learn a motion-focused video text representation. And this works pretty well. It really does allow the model to focus much better on the motion that's happening in the video. So here you see someone doing gymnastics, and in the normal case, it's kind of focusing more on the crowd. And here then we're able to see it actually focusing on the gymnast and the movements. And the other advantage is it really makes it much more data efficient. So you can deal with a lot less pre-training data or post-training in the case of the vision language setting. You can deal with a lot less data because we're injecting motion into the video, so it doesn't need as much video samples to learn motion because they're much denser in terms of the motion they contain. And this works pretty well in a few settings, so it does work in different domains pretty well. It also is able to work well when we have fewer samples to fine-tune with, and particularly when we have fine-grained actions. But it was still much more focused on these kind of action recognition tasks back when we were doing this work. And interestingly as well, even though this work's now a little bit older, so I think it was 2003, we recently did another study where we see how different models compare to transformer models in terms of CNN versus transformer video pre-training. And what we actually found was, okay, transformers are pretty good at domains now, but our model with a CNN was much better at doing data-efficient fine-tuning and much better at fine-grained actions. Okay, so that was being able to extend knowledge to new domains, particularly domains where motion is important. And now the last thing I want to touch on briefly is how to extend to new modalities. So we have this work where we were looking at completely unseen modality pairings. So the idea here was, instead of trying to train with all the different modalities you want to test with, maybe you only have access to one or two modalities paired together, and maybe you have like a different set of data that has these 3 other modalities you're interested in. And you don't ever have this data where you have all 5 modalities together. You end up with these kind of disjoint subsets where you have separate modalities. So our question was, can we actually do something with this? Even though it's quite constrained, can we actually make use of these multiple modalities together? And I think, okay, the problem's a bit constrained, but I think it could still be quite useful in cases where maybe in egocentric vision, you have cooking data, and maybe you want to combine this with information of like how hot the pan is, or maybe you want to know when someone's heart rate goes up so they're uncertain of what to do, and you want to kind of guide them through it. And I think this is particularly useful maybe in more surgical data where you have this kinematic force of the sensors. Okay, so how did we go about doing this? I won't go into so much detail, but just to give a brief outline. So the first step is to get the different modalities features within the same space. So you can easily do this with a projection layer. But then what we do is we have this alignment loss that encourages these 2 sets of features to align even though we don't have any paired data. So there's some kind of like pseudo targets of what they should be matching, and that all of the data within a modality should kind of match some of these targets, and the same targets are true for the other modality. So it's kind of like a soft alignment goal. And then the other thing we notice is, okay, some modalities are a lot less discriminative for the target task. So audio, you can't really tell what's happening yet. Maybe you can kind of tell it's water. Then you see in optical flow, and maybe you can see some hands. But then when we get to the video, you can actually see what's going on. So if we have these disjoint sets of modalities, it doesn't make sense to kind of enforce them all to the same label. So what we do instead is we still have the supervised goal, but we also have this pseudo label that kind of describes how uncertain the model should actually be about these different modalities. So we're not pushing it to kind of overfit to these labels that it really shouldn't be able to tell from the information we're giving it. Okay, and this works pretty well. We're testing this on multimedia retrieval. We also have results on EPIC in the paper, and also robot state regression. And whatever combination of modalities we're giving it that the model hasn't seen in combination before, we're doing better on. So any of these different combinations of modalities, it does help with. Okay, so I think that was all the work I wanted to go through. So to kind of conclude, I really think details matter. And they really matter in egocentric vision, and also egocentric vision is a really great way to give like an actual view into these details. So details can be both useful to egocentric vision, and egocentric vision can be useful for other data because we can see these details so well. And I think these details, while they're very present in egocentric video, the actual labels of them are quite rare, and the fine-grained concepts are just really rare in internet scale data as a whole. But we can kind of try and learn these details, and this is what we've started to do. So we've started to adapt what actually exists, be able to extend to new concepts, be able to extend to new domains, and be able to extend to new modalities. Okay, and then just to conclude, obviously research can't be done alone, so I want to thank all the PhD students that led all these different works I talked about, and then just finish with one small ad that we now have a postdoc opening, so if any of this work is interesting to you and you're looking for a postdoc, please reach out to me. And I'm happy to answer any questions.
Any questions? Okay, I'll start asking one. So let's say this is a more like general question. So you say that supervision about these fine-grained details lacks, but not the data itself, right? I mean,
yeah, so I think it depends what domain you're looking in. I think in egocentric, because there's been so much effort from you, everyone else in this room to collect this data, now we have quite a bit of data. I think, so if you're looking in the cooking domain, we've got tons of data for this. Maybe if you're looking in the industrial assembly, this is still lacking, but the viewpoint, at least, we have a lot of data for. So I really think here the labels are a problem, which is what we saw in HD EPIC. But I think there are a lot of other situations where the domain itself is also hugely lacking.
So if the data, I mean, So it looks like the data is lacking, and it will be lacking anyway. Like it's very hard to have this effort of fixing the data.
Yeah, I think the problem is structural. It's because there isn't necessarily researchers that have tried to do this specific domain of data, because it just doesn't naturally occur online. So I think without a targeted effort to actually collect data in these specific areas, you're just never going to have this data.
Right, and I guess my question is, maybe we should not try to learn this in a supervised way. And I think so the way we learn things about details is that we live in a physical world, and if we are not doing things in a specific way, then there are consequences. So we should maybe think about switching to that rather than just watching passive video and...
Yeah, I agree. It's action will hugely help with this, but also just learning kind of cause and effect and what happens when, which you can probably already learn from passive videos, but we don't really do. I think, these are really important things for learning details. I agree.
Thank you. Other questions? Okay, I'll use this mic.
Thanks for the talk. Very interesting. I think the narrations aspect is quite valuable. I'm wondering if you've thought about bootstrapping at all to increase the quantity of narrations collected and the quality as well.
What do you mean in terms of...
Bootstrapping as in train a model to produce narrations and then humans produce narrations faster by editing them.
Yeah, it could be. We haven't tried it because we designed HD Epic specifically as a test set, but this could for sure probably help. I think what was really tricky with the narrations is if you don't have the person that was doing it, it can sometimes be quite hard to describe like how and why they were doing it, because they can't like physically imagine themselves in the space. So I think that you could certainly try the models doing it, but getting people to edit it well would maybe be the challenge.
Got it. Makes sense. Thank you.
Okay, so any other questions? Okay, so let's conclude the session and let's thank Hazel again.
Okay, so thanks for the nice introduction. And I'm Zui. I come from the Nanyang Technical University, Singapore. So today I'm very honored to be here to share some of recent works from egocentric experience to interactive intelligence. So building the world in first person. Okay, so first I want to revisit like the 3 dimensions of the counselor's nature. Okay, so you will see it's very aligned with how the whole vision intelligence evolved. So from these sensibilities to understanding and to reason, it's just like how our the vision community evolves from perception to geometry and finally to action. So I believe in a very recent interview by Demis Hassabis, the CEO of DeepMind, so he proposed the ultimate AGI test for LM. That is, we used all the text before like the 1900. And then we train this LM, use all the text before that point, and we see whether the LM can invent the theory of relativity by its own, okay? So here I propose another visual AGI test. That is, given you all these egocentric videos of Newton, right, of interacting with the world, can these visual agents or these visual models can also discover this Newton's law, right? That's, I believe, the very interesting question to think about. That is, we're going from this perception to geometry and finally to the action. Okay, so this whole evolution of this visual intelligence is not just on this kind of this concept levels from pixel to shape to experience. It's also on how we collect the data. Okay, as you know, the dataset has driven the whole progress of this computer vision and deep learning research. From the very first generation of the ImageNet that is learning from the raw visual signals, so the data is actually collected passively that we're using these crowdsourced images from internet. Then we go into the era of the 3D learning or the shape learning. Then we have this dataset of Objectives. That's when learning these structured 3D representations from either native 3D collections or 2D image collections. So for this Objectives, the data is passive. It's still passive. That is, we want to collect from the internet. However, here is data itself is not just collected by the layman users. It's collected by the expert, right? It's expert curated because it's kind of created by the 3D artists out there. And the final stage, from perception to geometry and finally to the action, I argue that for experience level, we need another dataset that can support the research on that. That is what we're building nowadays is called Xperience 10 million. That is learning from interaction and feedback. And for this collection of the Xperience 10 million, it's no longer passive. So now it's active. And it's just like the agents explore the world and how can we collect data around us. The agent can be our humans, or it can be other forms of digital agents. So it's also about the real world data bottleneck. As you see around of this year's CVPR, there's lots of like the workshops on the LLM, on the generative AI. So they have a very successful pipeline of these data combined in models. That is, they first try to download all this internet data, like the text, images, or code out there. Then they have some annotation pipelines to do it, to the labeling, and also curate the data, and finally train foundation models. Can either LLM or agent models out there, then it works. So the only problem here is how can we scale up the data, scale up the annotation, and finally scale up the model parameters. However, for this physical AI, this paradigm no longer works because there's no robotics data on internet. So even though we have lots of egocentric data on the internet, if you download all the videos, you will see the meaningful videos out there have these meaningful interactions is very limited. The second is we don't have scalable annotation pipeline for this physical AI because of this physical world is inherently 4D, right? Inherently 4D. So now we don't have effective 4D foundation models for us to do the annotation. So even though like for the past year we have the VGGT out there, but they still don't have the required accuracy from this just molecular views. So this one is broken. So how can we enable this pipeline for physical AI from this egocentric perspective? So our solution is we have an initiative, it's called Ropedia. So we want to capture structured real-world interaction at scale and also low cost. So Ropedia, the solutions has two forms. So one is we provide the hardware for collecting the interaction data. And this hardware is very low cost and you can use it in your daily life. The second is we have our own in-house structured annotation models so that we can have a very accurate 4D annotations for any egocentric videos. Okay, so combining them both, we can convert this real world data, movements, interactions to the training recipes of physical AI. Okay, so as I said, the solution provided by Ropedia is kind of the co-design of hardware and software. So for the hardware, we propose something called Hao Li. So it's a full stack, low cost, portable data capture device. So for this one, it's super lightweight. You can see it's only like 300 G out there. And we have 4 cameras so that we can capture essentially 360 degrees field of view of the egocentric video. And it also can support the storage and also the battery for 12 hours. That means you can like wear it all day long. It's always on device. So building on this device, we also have our in-house models that can pass these egocentric videos into the human episodes. So overall, till now, we have collected over 10 million human interaction episodes over there. And it's already open sourced on the Hugging Face. So it has like 2 million downloads in just 1 week. So it's just not another egocentric video dataset because we have all the accurate 4D annotations. So here I just showcase some of the examples over there. So of course, on the left-hand side, you have these egocentric views, but we also have very accurate this depth information because we have 4 cameras out there. You can always use stereo to get the information combined with the current foundation model for the depths. And we also have our in-house model to estimate the human skeletons, the head pose, the hand pose, how the hand is interacting with all the objects out there. And furthermore, we also have this hierarchical action semantic understandings. For example, from like second 4 to second 31, what happens to person A, and from second 10 to second like 42, what happens to person B, right? We list all the objects, all the interactions happens inside these videos. So overall, it's 10 million episodes, and you need like 1 PB storage for all the data out there. So it's not just working for the indoor scenes, it's also working for the outdoor scenes. So here we show the in the wild data capture. So you can see some of them is in the office, in the lab, in the kitchen, and sometimes it's in the outdoor for the supermarkets and also for the shopping mall. Okay, I believe it can enable the capture for anybody, anywhere. So the question is, if we already have this large-scale data sets, this egocentric video plus this 3D and 4D annotations, Xperience 10 million, how can we enable the research forward? Okay, of course, there's two types of research. The first is, okay, I just design like the 100 billion models and fit all the videos inside and train just one models. Right? However, we don't have this enough compute to support that type of research. So here we switch to the second row. That is, we want to convert all these interactive appearance to simulation-ready modeling. That is, all these 10 million, we call it experience of our humans. And every experience is accompanied by these 3D, 4D, egocentric videos out there. However, to make it truly usable by the physical agents, we need it to be replaceable inside simulator, right? So all of these assets inside these videos should be simulation ready. That is our key intuition. That is why we want to go pursue this kind of research. So for this simulation ready modeling, we have like three aspects. First is on the object side. That is, how can we recover the physical properties of the objects? How can we interact with objects from just a single view? Second is on this human object interaction. That is how we can like open a refrigerator, how we can like cook the dishes out there. It's not just on the 2D, it's on the 4D, okay? And finally is the human-scene interaction. That is, when you go home, you want to lie on the sofa, can you transfer skill to your humanoid, right? So sometimes humanoid, they just not work. They also need rest, okay? Right? So how can we also enable this? So we have this human-scene interaction. So let's first talking about the objects, right? So how can we define the physical properties of the objects from just a single view? So this work is called physics anything. That is simulation-ready physical 3D assets from a single image. So this work will also be shared in this CVPR. So the key insight is that the current 3D communities, they are more emphasized on the geometries and textures. So from our egocentric communities, we also do this kind of 3D tracking or 3D reconstruction inside, but most of the time we are neglecting the physical grounded modeling. Like what's the weight, what's the density, what is the Young's module, right? So if we lack in these physics properties, we can't support real world applications like simulation and body AI, right? For example, given this box, if you know the weight, you know the size, you know the material, you actually don't know whether it can stand under certain gravity. Okay, so here talking about physical properties, we have like three levels of definition. So the first is called identification. That is, how can we determine the basic nature of the objects? So the basic nature consists of the absolute scaling and also the material, like Young's module, Poisson ratio, and density. So the second level is on the function side. That is, how can we understand these possible potential applications? For example, given you a knife, so where should you hold it? So where is the affordance? And if you hold it, how can you cut the apple, right? The function description out there. And finally, it's on the operation side. So most of the very valuable interactions in the human lives are using tools. And most of our human tools, the tools used by our humans, they are not static. They're articulated. So how can we understand articulations inside? That is, how can we model the kinematic parameters? That's also important. So here we actually enable a human-in-the-loop annotation pipeline. So previously, we only have the pipeline for the third-person view. Now we already incorporated the first-person view. That is just using these egocentric videos, how can we discover all the properties inside? So imagine you have an AR/VR glass, and you are going to certain like manufacturing factories out there. So how can we convert all the human skills into digital skills, right? So that's the problem. So here we propose the human-in-the-loop annotation pipeline. So we find that the SOTA VLMs like the GPT or Gemini models, they are very good at certain like aspects of the physical properties, but they tend to hallucinate a lot for others. So here we are using observations to design the human chat just for that very fragile aspects of the physical properties. And for the kinematic parameters, we have this pipeline from contact region, plan fitting, candidate generation, and finally to the kinematic parameter determination. That pushes this egocentric research from observation to the action, right? Because you know how to interact with all the objects. So with this pipeline, we're building a large-scale dataset. It's called PhysXNet. So it has like 26K richly annotated 3D objects with all the physical properties inside. Then we further augment this dataset using procedural generation. That is, we try to use in the back of this chair with the bottom of another chair. So in that way, we have 6 million richly annotated 3D objects. So with 6 million, definitely we can train some foundation models. So here, our key insight is that which model to train, right? So I can choose 3D models. But here, I believe many of you are already using like Cloud Code or Codex every day. So the coding agent already works. So how about we just like modeling this interactive world? For example, the 3D objects as a physical code. Okay, we're just modeling as the coding problem. So we have the URDF, we have the XML. We just have to design certain decoders that can decode all the information from some base model. So here our base model, we're using like QN3VL, a very mainstream vision language models to output this 3D information. So in this way, we can combining all this physical modeling with current like video understanding, single image understanding to enable a truly unified model. So this decoder consists of two parts. The first part is called controllable flow transformer, that is for recover all the geometries out there. The second is for the physical format decoders to decode all the physical properties like the affordance or like the densities out there. So you can see here is the results. So compared with the previous work like the URDF former or can do anything, so our model performs pretty well. So you can see the input is just one single image, or in other cases with just egocentric videos. We can recover from this single image or these extended videos to this fully interactable 3D assets. Okay, so that's very important because these 3D assets can be reused in any simulators. So here is the comparisons for affordance prediction, description generation, material identification. So you can see our methods consistently achieve lower error bar. And here's the animations. Here is the quantitative comparisons. So we show that by enabling this physical properties prediction, it's not just only enable itself, the physical prediction, it's also improve the geometries. So that's quite amazing because it's just like humans. If we know the physical properties of certain objects, we also know it better of these geometries, right? So you can see they are helping each other. And finally, we can show the results. So it's all simulated objects, just using one QM models outputting the physical code. We can do in pretty good simulations of the articulated objects. So it's not just about articulation. Each object inside, we also have the material for each part. So I know if I use certain force to poke it or to push it, like what will it behave? So we have this coarsen effect inside the model. So here's more results on these simulated objects. So some of them are quite complex, so it still can work pretty well. And we can even kind of put all our simulated objects into simulators to learn the policy, right? So you can see it can already learn the policies for the robotic arm to enable these simulated interactions out there. Okay, so that's our first part. That is, if we have this large-scale interaction data, of course, we can first identify all the objects inside it and also try to predict all the physical properties. And after single object, definitely we have another very important issue, that is the hand-object interactions, or the human-object interactions. So here I just talking about the human objects. We also have another work on the hand. So maybe if you are interested, you can check out our lab website. So for the human-object interaction, the work I want to share is called ART-HOI. It's articulated human-object interaction by 4D reconstruction from video priors. So you can see inside our home, we have different like tasks. For example, open the fridge, find what you need, or close the laptop, or like open the tea cabinet and pick your favorite blend. Okay, so we want to doing all the things. So we actually want one generalized models, not overfitting to each of the interaction. So that comes with lots of challenges out there, right? So task here, I give a very clear definition. That is, we first have all the Gaussians, all the 3D assets for humans, objects, for scenes. So given you a task, can we synthesize these 4D scenes, accomplish this task? For example, opening this fridge. It's 4D, so you can actually see it from different viewpoints, and it's also simulation ready because we have all the 3D permutations inside. So for this one, the challenges here actually are threefold. The first one is actually on the data. Do we have enough interaction data to learn it? The second is on the design of the HOI models, because these models can have to handle both the human motions and object motions. Okay, so for these three challenges, we have three different ways to tackle that, right? So lack of 3D interaction data, of course, the first way is I just use the Xperience 10 million, right? This is our large-scale human egocentric interaction data set. Another way is, okay, maybe I just pick a general video generation models like View 3 or CDANS 2.0 or like one models. I fine-tune the model with Xperience to turn it into egocentric generative models. Using that way, I can tackle this lack of 3D interaction data. So I just use video prior, right? Video prior. So the second challenge is limited to rigid objects. However, in the real world, all the objects are not rigid, they are articulated. Of course, the first way is we can use the physics anything I have just introduced. Another way that is faster, we don't need another QM models, right? Another very QM model is we're just using flow-based segmentation. It's pretty fast because it's just point tracking across these segments. So it's very fast. The third is the coupling of the human-object contact. So when you're trying to grab something, if your estimation of the hand is wrong, of course, the contact of the object is also wrong, right? So that's the coupling issues of this human motion and object motions. So here we propose we're just doing two-stage. We are not simultaneously to predict them together, right? Just two-stage. First doing the human, then doing the object, or first doing the object, then do the human. So here comes the 3 stages of our method. So the first one is we have some video prior. It either comes from Xperience 10 million, or it comes from some general video generation prior, like View 3. Then we have a very fast part segmentation modules. It's flow-based. It can track all the points. So if you don't mind about the inference time, of course, you can replace this part with the physics anything I've introduced, right? It's a QM models. And finally, I just decouple these two parts into first doing the object, then doing the human, right? We find this more robust. So compared with other works like Zero HSI by Stanford and it's Lingo by the BAI, so you can see our model have also the right motion and physics. It's open the cabinet, look inside, and for this one, it's open the microwave. And for others, it's it's not obey the physical law. And close the laptop screen gently. So it's 4D readouts. Okay, so after talking about the object and the human-object interaction, as I said, the final very important aspect is the human-scene interaction, right? So our humans, sometimes I just want to lie here, sometimes I want to sit on the chair, sit on the sofa. So how can we model in that interaction? So this work is called similar physics in the loop reconstruction of simulation-ready humans interactions. So the keyword here across all the work is I want to transform this human video or egocentric interaction videos into simulation-ready assets, interactions, right? So for this one, I want to inject physics in the loop. So the challenge here is actually if I just using the SOTA models, like here, this one is from Berkeley, you can find that they are not very well modeling the human-object interactions. Lots of penetrations, it's also no physics involved. So what's first? If I just convert this one or import this one into the simulators, it will fail. For example, if I want to climb this one, it will totally fail. If I want to stand on the table, it will fall, right? So not working anymore. So how can we reconstruct the human's interaction is not only looks good, but also actually physical correct, also stable in the physical world. That's the important thing. So our key idea is, okay, how about we just leverage this simulator interaction feedback to optimize the human motion and the scene geometry together? So that's also comes to the beta lesson everyone is talking now, right? So for the egocentric research or for the 3D research, the beta lesson is that we should just optimize for the final goal instead of all the proxy metric. For the reconstruction, many people like caring about like a PSNR or the chamfer distance of point cloud. So we argue that we just go for the final goal. That is, if I step onto a table, whether I can stand on it physically, right? So that is very important. So if the simulator tells me, okay, I roll out 10 times, like among the 10 times, 3 times I'm doing good, 7 times I'm fail and fail in different ways, how can I leverage all the feedback? Okay, so that is the idea we want to explore in this work. Just doing some casual captures. So I have shown that egocentric capture is very effective. Then we're just using this simulator as critical models to backplot all the gradients. So stage 1 is the motion optimization, while the scene-targeted reinforcement learning. So you can see here we want to reconstruct this human with the scenes. However, if we import it into the simulators, sometimes it will fail. Okay, so the table will fall. So this 4 also gives us some information whether our reconstruction is good or not. So we can keep rolling out to fix the errors. You can think of it just like some test time computing or like the chain of thought in the large language models, except that the COT here is on the simulators, on the interactions. So after that, we find that the human is good. The human motion is good. However, the structure is suboptimal for the chairs, for the tables, for the scenes, right? So how can we also compensate for that? So here we show that we can still using the simulator feedback. So the same idea can be applied to both humans and scenes. So given this table or given this chair, if before I sit on it, it's already not stable, that means it's not good, right? So that means without human, whether a scene is stable or not, that's a very important cue. Very important cue. So we use this cue to optimize. We have 4 types of error. So that's consists of like 4 different reward to optimize our reconstruction models. Okay, so by combining the idea of this learning from simulated feedbacks, we have also built a dataset. It's called HSI Bench. So it's actually for evaluating whether we can do this physics well reconstruction of the human scene interactions. So have like 19 objects, over 50 motion sequences, recorded by like 2 male and 1 female participants, totaling 300 unique interaction instances out there. So here are some cases out there. So of course, our method didn't need these lab settings of this green screen. So we use the green screen here just to capture the ground truth so that we can compute the qualitative metrics. So you can see here, we also capture the sitting, the same motion with different chairs so that we know the OOD performance, out of distribution performance, whether it's robust or not. So the good thing is that we find that this simulator feedback is extremely effective. So compared with other method, yeah, the stability, penetration, or motion qualities really achieve the best performance. And for the scene reconstruction, it's also good. So here we show the results for the real-to scene. That is just given the egocentric view or third-person view, we can reconstruct this human scene reconstruction very stably in the simulators. So it's actually very hard because you have to adjust your weights. Here's another case. So what's better is that we can also enable this sim-to-real. After learning these policies in the simulators, it can be transferred to the real humanoids. So here we show that we can do behavior cloning. With just several episodes in the Xperience 10 million egocentric videos, we can mimic the same human motions for the robots. You can see this one, it's just sitting in the chair. We will also change the chair to other chairs to see whether it has the robustness or not. So sitting is very easy for a human, but it's very hard for humanoid, okay? Especially for the unitary humanoid, yeah. Okay, so I think the key message today I want to convey is we are moving from a world that is seen to a world that's experienced. So previous data sets or previous methods are more like from distance, but now we are going to modeling all the interactions, experience out there. So I hope we can achieve this together as a communities. Thank you, and I'm happy to take any question.
Thank you so much. We can squeeze in one question while the panelists assemble here for the next session. If anyone has a question, go for it. And then in the meantime, could the panelists for the next session please come up?
Thanks for the great talk. My question is about what's the limit of this? Sorry, what's the limit of this egocentric videos, and can it handle fine-grained modulation? Do you foresee that if we get enough videos, even though the hand pose estimation is not accurate enough, but we can still figure out a way to zero-shot transfer to robots for fine manipulation tasks? Thank you.
Yeah, I think that's a very good question. So I believe it depends on two aspects. The first is the accuracy of the human hands or hand estimation is not actually the only indicator for the final successful rate of the humanoid transfer. I also have another RL stage out there. So if you have a very good RL algorithm, you can tolerance certain inaccuracies in the estimation. That is the first thing. The second is that we also see the scaling lower of our own in-house models for the hand estimations. So as we collect more data, we also have better annotation. Of course, if we have very large occlusion, we need other type of solution. If the occlusion is minimum, we can do it pretty well. Yeah. Yeah. Yeah, that's a very good question. So for the very standard pick and place task, we don't need tactile or other physical properties. We have some experiments on that. But for other contact-rich task or long horizon task, we find that tactile helps because we are now trying to enrich this Xperience 10 million with some tactile annotations. So we find that it will definitely help with the contact-rich tasks. We have our own glove for the tactile collection. Yeah. Okay, yeah, thank you.
All right, let's thank the speaker one more time. All right, now we have the panel session. Let's welcome our panelists. These are a combination of the keynote speakers, some of which you've heard today. Jawahar, Dima, Jacob, Hazel, Saurabh, and Ziwe. And Jacob and Dima are joining us as special guests on the panel today. So let's welcome them. All right, thank you for your time. So the way this is going to work, I have a couple of questions planned. I'll try and set up the topic, set up the theme. These aren't necessarily my opinions. I'm crowdsourcing controversial opinions out there. I'll try and address it to some of you, but of course, anyone who has a strong opinion, feel free to chime in anytime. Let's start with something that I think a lot of you might actually agree with, so maybe it's not as controversial. The topic is about egocentric data's role in training large AI models. So far we've seen egocentric data treated as one small part in a relatively larger data mix. There's no special treatment really with respect to object interactions, persistent 3D space. There's no focus on geographic or cultural diversity. This is just something that gets thrown into the model, right? It's one tiny slice of the mix. And at the same time, Gemini, ChatGPT still work in quotations on egocentric video to some extent. And so the new Google glasses that are eventually going to come out are likely just going to have Gemini as is slapped onto the pair of glasses. And also this morning, Saurabh told us that he's agnostic about whether the video is ego or exo. So maybe it doesn't matter at all. And so the question here is egocentric data just another slice in the data mix? Are long movies the same as long egocentric videos? And are the current large open source or academic institutions making a huge mistake by treating them the same? Let's have Hazel and Jawahar give their opinions on this. Either of you, whoever wants to lead. I picked Hazel because she complained about Gemini.
Yeah, no, I think I agree. The
there is a role of egocentric data, which is different from the exo or the third person data. And that may not be possibly obvious today because we are still seeing the early results of a large amount of data solving the problems with reasonable or acceptable performance. So when you go to the very specialized tasks, very advanced tasks, really the role of the egocentric data will become more and more obvious. And that is where possibly we will. Until then, any data is good enough for a deep learning system. Unfortunately, we are possibly still in that stage.
Yeah, I pretty much agree. I think it completely depends what you want to do with it. If you're just trying to do some like text description of it, doesn't matter. You can just throw it in the soup with everything else. Probably you can just see clearer what's happening and it gives you a better description. But if you're really trying to do like some spatial understanding or some understanding where people are paying attention or something like with embodiment, you really then need the egocentric data to be treated differently, I think.
Yeah, go ahead.
So I think I would like to make a distinction between two things, the viewpoint and what is the video, okay? So if you have someone just going around doing their daily task, and you're capturing that from the viewpoint of ego or the viewpoint of exo, that's one dimension. But then there's the other dimension you mentioned, which is like a movie, right? The video of a movie is a highly edited storyline. It's not really a continuous flow of something. Things are edited and cut out and designed for a particular reason. So I think we have to make the distinction between the viewpoint. Probably, if you want to learn about daily tasks, you can learn from both ego and exo. They're both two different viewpoints, the same thing. And the dimension of what is this video? Why did someone create it? What's the intent of it being made available? And I think that dimension is so diverse that I don't think you can learn the same thing from a movie and from an ego video, but probably you can learn the same thing from an ego and a tabletop video in terms of affordance.
Yeah, I want to agree with you, right? Like, I think it comes down what is actually different about egocentric data. It's perspective, it's the longitudinality, as in like one continuous long stream rather than lots of clips. And I think the third one that actually is different is that we have, I mean, the way you just talked about it, right? With Project Aria, we've also started that. Multi-view, calibrated, not just video, but a lot of other like properties that come with that. Like those are, I think, the three things. When it comes to foundation models, I think the perspective doesn't really matter that much, honestly. They'll just learn to interpolate, extrapolate. Is difference of a video from a head so different from a smartphone? I don't think so. The longitudinal aspect, I think that's what matters. And frankly, no foundation model is very good at that. So it doesn't matter right now in practice, but I think it will matter in the future. And then the third one is the multi-view, calibrated sensor data, multimodal sensor data, same as you'd get for robotics, for example. I think that's a real gap, and foundation models should get better at using that. And right now, they're not very good at that.
So is it safe to say that as long as egocentric video in its final form is part of the data mix and is scaled up, it's okay? I guess the question over here was, it's even though like no one's debating whether it's different or not. Of course, it's different and special in many ways, but then the way it's being treated is identical. It's still like text labels, captions. Maybe it's relevant to what you see in the egocentric view, yes, but it's largely treated the same. And is that okay?
It's currently not in the data mix in most cases. It's currently being treated as, it's too much. Camera is moving too much. It's too blurry. It's too long, it's too redundant, so let's just get rid of it. Mm-hmm. That's the problem. Huh? The problem is that it's not currently in the data mix.
Well, and if it is in the data mix, it gets chopped up into like 5-second segments, and then that's in the data mix, right? So that gets rid of any longitudinality anyway.
Okay, so then the follow-up, are people making a mistake? What should we do to make sure that it is in the data mix in the form that we want it to be? Anyone? All right, next CVPR then. Okay, go ahead.
I think I've tried, there are a few of us who've been doing this area in this area for very long, and we clearly have failed to articulate why it's special. So maybe the new generation will do a better job.
All right, let's move on to something a little bit related. The topic for this question is more about moving from the data. It's more about what is the correct way to build an egocentric foundation model, whatever that might mean. So one version of this is the stance that you can't just take a gigantic multimodal VLM and then throw in a bunch of data into it, which is what we've just been talking about. The other is you can, and those are these implicit world models plus a renderer, and I think Ziwe has worked a lot on this, where you very much can. So the first take is you need the 3D, you need the explicit 3D sort of models in this. So is there one obvious answer here, or are these two just sort of incompatible directions? Ziwe, do you have any thoughts?
Yeah, so I believe this kind of the model choice also aligns with the mix with how we design the data, the egocentric data. So I want to echo with the previous question, that is the unique value of the egocentric data is actually on the kind of the activeness of the data. So all this XO data with third-person data, they are kind of like passive. So we're throwing lots of videos into this VLM, we'll never learn the activeness of the agent. So if we learn from this egocentric data, we are not just have the video contents, we also have our pose, the head pose, how we move inside the 3D space. We have our global world coordinates. I believe that's very important, because from this evolution of the life, you can see all the lives coming from this very passive way, like the plants, go to very active way, like the animals, right? So I believe that's a very important, unique properties. So how do we design the model? Also, depending on how we define our data.
Anyone else wants to add to this?
I think 3D matters, and I think a few of us say 3D matters.
Okay.
Explicit or implicit, I'm still on the fence.
Okay. Is there anyone who's very pro 3D is definitely needs to be there? Looking at you.
I mean, for certain tasks, certainly, right? It comes down to what you want to do with it. Like certain things, yes, you need it. A lot of foundation model pre-training actually, can use 3D as ultimately a loss function to induce some kind of latent 3D representation.
Mm-hmm.
And then you throw away the decoder and you lose the latent 3D representation for other stuff, right? So, is that using 3D? To some extent, yes, right? But also not. It's not the explicit output that you're looking for in the end. It's a means to an end. Literally, it's a training objective, right? Frankly, just the same as we're training lots of foundation models encoders by generating images or videos, then throw away the decoder and use the encoder for something else, right? Like very common practice.
Mm-hmm.
I think 3D representations have a similar role in many cases, right?
But do you think this is just it's a matter of compute and scale at this point, where it might help in the short term and maybe isn't necessary? Or do you think there's a fundamental limitation in this class of models that literally only process RGB frames and nothing else, and you can never hope to do a 3D task and name such a 3D task, or name such an egocentric perception task that you think may never be done unless you have 3D explicitly?
I stand by my statement from 10 years ago in a workshop on SLAM that I don't think end-to-end learned models will ever be better than like the VR algorithms that we have today. And the analogy here is that next token prediction to multiply numbers works up to some point, and then at that point, models just write Python code, execute it, run a floating point multiplication unit, and give you the answer. They don't need to do like math in next token prediction. I think the same will apply for lots of other things. Now, what those things are is a bit TBD. But yeah, my answer remains the same. I think some of the things that right now we do with explicit 3D will never be replaced. Now, how needed they are, right, and for what task, like that's a different question. They'll just become tools, just like every agentic system uses tools, so they'll just become that.
All right. Any other thoughts?
We're all 3D biased, I think.
I think Jacob said it very well. I think there is this system 1, system 2 sort of a thing, right? Like if there's something which you do very often, you can probably compile it into a feed-forward network, and that may be okay. But there may be things where you have to actually explicitly reason and such, and their geometry lets you extrapolate where learning only interpolates. So I think that's and I think the tool use is a very good example. Like LLMs, the fact that they are, the company's pouring in lots and lots of money into this, but the fact that they are using tools suggests that autoregressive prediction was not sufficient. And if the same answer is true for vision, that geometry is a tool that gets called, I think that'll be fine. I think that's a practical way of building models. I also want to push back a little bit on compute and data and power as being thought of as infinite resources. In academic settings, they're actually not infinite resources. And what makes us believe that NVIDIA and Google are going to collect lots of data and train a model and let you use it for free? They may not, and then we are faced with, okay, we don't have the data, compute, and the power, but we still want to make use of AI. I mean, geometry helps you reduce those burdens. Practically producing a better system is easier that way. So I think I'll also make that engineering more practical argument.
All right, I'm going to keep you on the hook, Saurabh, for the next set of questions, specifically about the next bet for egocentric data. So the context here is we've seen this mixed directions about when people talk about the next egocentric video data set. You started with something like Epic Kitchens that was focused on kitchen environments. Then we started expanding and we said Ego 4D, unconstrained, 3,000 hours. And then we had Ego XO4D, which was smaller, and we sort of was more focused on multi-view. HD Epic is focused on a smaller set, but just much, much more denser annotations. At the same time, you also have these larger data sets with tighter scopes, like Xperience 10M that has a focus on physical interactions, Ego Scale that's 20,000 hours, but still very much hand-object interaction. And so the question here is, has in the wild egocentric video data failed us? Why did NVIDIA have to collect 20,000 hours of this sort of constraint data? Why didn't we just train our robotics models with Ego 4D?
I really would like to answer that question answered.
That's Saurabh's job.
I really would like that question answered.
Why didn't you try harder?
No, I don't know whether it's why. Yeah, I went to a few of these papers that there was a paper recently that published and said Epic Kitchens and Ego 4D are not suitable for robotics. And I'm like, well, why? I would very much like to know. And I think the conclusion is robots currently can't move like humans. So they want something that's purely tabletop. Because this idea that people move and are very, flexible is very far from current limits of robotics. But the problem there is robotics, not in the Ego vision. But I do think, has egocentric video datasets failed us to date? The answer is yes. The answer is yes. We haven't yet got to agree on something. Jitendra is not in the room, but he claimed that Ego 4D will be the last dataset we'll ever want to collect. We were in that room when he was saying this. I'm like, clearly you knew that not to be true. We're very, very, very far from breaking the barrier on Ego datasets because Ego devices are not yet in people's hands. And so we're not at the flexibility where people are uploading egocentric long-term data every day and we're just sitting and waiting for them to just use it. So we're still actively collecting. We also haven't agreed on what is it we want to solve. The longitudinal thing is something some of us are very, very passionate about, Ego Live, but there are other people who don't think this is the problem. So have we as a community failed to agree and push and solve one task, say object recognition? We haven't agreed yet. Do we need to agree? I don't know. Maybe we can solve it without agreeing. But if we agree on solving one problem in Ego, we will be able to push for it. But how do you get humans to agree?
You don't. You have to debate. No, I think fundamentally there's kind of two different goals that I care about when it comes to egocentric data, right? One is robotics. And for that, I think, Ego 4D is too complex. It has too many things in there, right? Like right now, robotics is about like picking up objects and kind of like manipulating, cooking eggs maybe. But it's a bit, free-form human experiences are way too far away from what robotics currently can do or can use, right? That's one. I think the other one is deeply understanding humans better, right? In order to, help humans communicate better, help humans become better humans, be a coach for yourself, right? I think there's lots of good reasons why egocentric data can help us understand humans better, and ultimately, turn into, personalized superintelligence that makes you better at whatever you want to be better at or do better. in the long term, they might converge, right? They will converge. But I think right now and for the foreseeable future, they're relatively separate. So that's my answer, right? Like things like Ego4D, I think are more suitable to understand humans than to train robots right now. Again, that might change in the future, but right now robotics is much more like constrained, right? But I think I want to push back on the kind of premise a little bit. I don't think egocentric data has failed at all. I'm going to claim there's already like over 1 million hours of dedicated egocentric data collected today across like various companies, across academia, used to train robots, including lots of the like demos that you all might have seen. I think it's going to be 10x that by end of this year. I think egocentric data already is the main driver for robotic training, robot training. So I don't think it failed us. I think it's doing splendidly in that field.
The question was more just about the unconstrained version of egocentric video. So absolutely, NVIDIA is going to scale up from 20 hours to 200 hours next year. But more about like if you take Ego4D and then you scale it up, will Saurabh be unhappy?
No, I think I agree with the previous two statements. So the simple answer is that robotics has to advance faster to actually use the egocentric data. They're moving slow, and we possibly don't want to get stuck in that thing. So we should be able to also look at problems beyond the robot egocentric world. We don't want to get into that local minimum as a community.
Histories, like if you've been around for a while, when Epic Kitchens was released, people were shocked how bad our systems were because we had only been collecting, videos in very controlled settings. You have to put the flag far, right? Even if someone says it's too far, you have to show those examples. And I think, so I think eventually things will converge. But I think as a community, we have to just say things what they are. The flag for learning from something completely, for understanding humans or for assistive or for robotics, that flag is still very far. But the data is leading the way. The worry is if people don't want to see that way. Like I'm happy where am I? I'm going to solve robotics tomorrow and fold 10 million t-shirts and problem solved. So as long as we don't, maybe that's what we can solve now, but we have to keep an eye on where the further flag is.
Got it. So, Saurabh, one thing I want to push back, or not push back, but just ask.
I want to respond to that.
Oh, okay, perfect.
So I think I feel there's gap, right? Like what I can do with my hands, even if I take an anthropomorphic hand, I mean, if you take the Allegro hand, Leap hand, commonly used in academic settings, I mean, they're anthropomorphic, they have the same 4 fingers and such, but the physics is very different. And the strategy that I will use to, let's say, flip a page, let's say, with a robotic hand is going to end up different than what I would use with my human hand. I think that's this notion of gap between embodiments, which prevents like a direct transfer, if you will. And so I think, do I imagine that if I just have very large amounts of egocentric data and now suddenly my robot will work without any robot-specific data? I don't think that is going to happen. So I think it has to be, we have to kind of understand how our egocentric video is going to help robots. And I think maybe it is about task planning. And I think use of VLMs for task planning is very well regarded. I think that's almost a success at this point, right? So I think so at a very high level, it is clear what does video data provide you, not just egocentric, but exocentric as well. The low level, I'm not very hopeful. I think the question is, how far down can I go from the high level? What more can I learn at the mid level, which is also helpful and useful?
But it is helping. I mean, like EgoScale is a good paper. Like the point is not to not use robot data, right? Or not use simulation, not use like the point isn't to not use robot data at all. The point is to
augment,
pre-train or learn imperfect prior from humans, and then fine-tune that or adapt that to a specific robot morphology.
And I think that is possible, and I think will happen, even if it's not happening right now.
Well, it's already happened. Like EgoScale is a great paper. They show that
right.
The more egocentric data you use for pre-training, the easier or the better your then fine-tuned robot model works.
That's right. That's right.
There's many other ones, so it's already happening.
No. I mean, and I agree, and I think we just need to do more of that, right? If you have more, I mean, the other thing which videos give you is task diversity in some ways, right? I think it's very easy to collect humans doing lots of different tasks.
Yep.
It's harder to collect robots doing lots of different tasks. So I think, let's say humans have 1,000 tasks worth of data. Robot, there's only 100 tasks worth of data, and now you can start doing some of the held out tasks also easily, right? So I think that axis will continue to grow and blossom in my view.
So do you think we're done learning from human video though, for the high level semantic thing? So the reason I'm asking is your work a couple of years ago was largely focused on these human video priors, right? And then I think now it's still very much egocentric in the viewpoint, but it's shifted to robot egocentric video. So you think the things that we can learn, you listed out in your triangle, your pyramid diagram, have you already sorted them out?
No, I haven't. And I think I think the bottleneck right now is I'm not able to show like a robot using semantic information, high level information well. I needed to do the basic thing, pick up the cup first. So I think in some ways my focus has shifted to actually getting the manipulation to work. And then once we have that, then you can inject the high level semantics. That'll be more interesting at that point. So no, I'm not done yet. I'm just, there are other problems I need to fix first.
All right.
I think that articulates the state of robotics pretty well right now. But I think there's this right on the very, let's say, low level of manipulation details, or how a robot hand exactly has to move, how it uses its tactile sensing to get feedback. You won't learn that from human data, or very limited, right? So on the very low level, I think that's where you need, maybe teleop, likely simulation, likely real robot, data engine, training, no question, right? I think on the very high level, actually, egocentric data also isn't very useful. I think on the very high level, frankly, ChatGPT or LLMs do pretty well at decomposing tasks, telling you what to do. All that planning stuff, right? It happens to be very well doable in language domain, at which point LLMs are already very good at it. I think the high level, the low level are actually not egocentric data. The middle, and especially the middle when it comes to the long tail of, what are all the different things you might do? You might get robot data for, half of that, a quarter of that, but the long tail of how to interact with the world. I think that's where the sweet spot is for egocentric data, right? It's not the very low, not the very high level.
So I'm getting stressed at the fact that ego data is only for robotics. I don't care about robotics. And if it's useful for robotics, good for them. But I think I want ego data to be useful for humans. And so this worry that ego data is proving value for robotics, and so that has to be our focus, I would be extremely sad if that's the status of our domain. And if that's our only success, that's a failure.
I agree, right? That's why I said there's the second priority, which is understanding humans and effectively building AI that can help humans be better humans, whatever that means to humans, right? So yeah, I agree. I think it's those two.
I was just going to say, if there is an application which uses ego videos in some impactful way, I think that could suggest things to do. I mean, let's say Google Glasses was still a thing. Then it's clear this needs to be done, and that motivates, okay, this is the kind of things people want to do, and 3D, no 3D. I mean, all of those questions can be resolved in that.
It's coming back.
But is it coming back? Okay.
I think so. My typical analogy is this thing that is telling me how many steps I've walked. How did they manage to sell that many? How did they manage to convince me to wear it? It's such a, it's just a one-dimensional signal of my life. And now when I sleep, and if it tells me I slept well, even if I feel I haven't slept well, I'm now convincing myself that surely the data is right? So this is the dimension that I think ego data can offer, right? It's to be able to complete that ability of us understanding the full extent of what we do, and behaviorally change, what we want to change to become, as we said, better humans. Hazel is here, and my best example is when she told me that I don't know how to cut onions because she watched my videos cutting onions, which were disastrous, and she bravely walked into my office.
Send her a video of me doing it to teach
and
her.
I told her, what does that mean? And she said, I'll send you a video. And so I now know how to cut onions. So I think this is the level that I think is completely unseen, and it's not an application that is already there. And we shouldn't lose track of the potential of being able to kind of, observe, monitor, remind, improve, just kind of do similar to what this stupid thing is doing, because it only counts my steps.
All right, so this is the perfect segue to the last sort of theme, which is on exactly the future of egocentric video. The reason I picked this specifically is because in my intro slides also, I shared just that we've seen some sort of unprecedented acceleration in all things AI, agents, coding agents, regular agents, humanoid robots, whatever it is. The question is, do you think that the progress in egocentric perception has matched up to that pace? This question is for Dima specifically, because in CVPR 24, she said, in 15 to 30 years is when most ideas are going to materialize. This is a position paper that sets sort of the horizon as 2050 for all of these things. So I'd love to hear everyone's opinion on this, about just what was the killer capability that you used to say you worked on and had in all of your slides that we now maybe already have, or did we get there? Have the goalposts moved? Dima, go ahead.
I don't think the goalpost moved. I think we're exactly where we were in 2018 in terms of capabilities. We're not exactly where we were in terms of people seeing the data and figuring it out and admitting it's hard. But I don't think the goalpost of usefulness has moved much.
So the example in your slide from 2024 is exactly the same example in
For me,
2026.
yes, but I'm happy to hear others' opinions.
What was that example before?
I think we kind of wrote this paper, which is an outlook into the future of egocentric vision, where we kind of looked at we kind of dreamed what the future would look like, and kind of assisting people across different things. And we wrote these nice stories, which we then sketched out. And some of them were obvious, which is telling a worker in a factory that they're at risk, right? We kind of have been promising this for very, very long. But some of them were very, very imaginative, like assisting a movie director to kind of go around the scene and sketch what the movie will look like through their ego vision and just by walking and doing stuff. And I think there's plenty of potential completely untouched. But yeah, I don't think the goalpost moved, except the fact that people now know what egocentric vision is. So maybe that is a goalpost that moved really, really far and really quickly, and credit to everybody here in the room. Maybe that's the starting point.
Anyone else have the examples that they have in their slides that they'd like to share, and whether they have moved or not?
Yeah, so I guess I started my whole PhD just trying to rank how well people did different tasks. And okay, maybe the example's not quite the same in my slides anymore, but I did see a paper using these exact data sets I proposed back then. It's barely improved.
One thing that I like, right, like egocentric data, what it has done is it has taken people out of the curated data set domain and into the real world a bit more. I don't think egocentric data is the only thing that does that. Honestly, robotics is also really good at that, right? Because it's exactly not somebody who knows how to take pictures so nerves work well, going around the house, taking nice pictures so nerves work well, right? And that kind of like being what the community focuses on. And that, similar patterns I've seen in other communities. Slam is a great example as well. Where sort of, if you know how to move a camera, you can make Slam work really well. If you put it on anybody's head, it breaks. Okay. So egocentric data has been really good at getting us out of curated data sets and into the real world, showing that things like break, right? I think it's done that job, right? And I think we'll keep working on that.
All right, then I guess we will retain our 2050 timeline, and we'll revisit it then.
2040, come on. 2040, come on.
Fine, 2040. I'll settle for that. All right, let's thank the panelists again for their time. This is great.
Okay, well, thanks everybody for staying through the end of the day here at EgoVis. I'm James Ford. I'm a research product manager at Meta Reality Labs, and I'm happy to be here at another CVPR to show everyone Project Aria and provide some exciting updates for our community. The human body itself is an extraordinary sensing and perceiving system. And today we mostly provide the distilled output of that sensing system to AI via language. But we massively compress and always filter and distort the raw data through our minds, and necessarily so when we transform the data into the linguistic symbols that we provide to modern chat-based AI agents. Project Aria is a different kind of extraordinary artificial sensing and perception system that allows us to experiment with new ways of providing data from the world and from our point of view to AI systems. We can experiment with what perception means, how we compress representations, and new ways of interfacing with AI models. So this brings us to Project Aria's mission. Our aim is to bring the human perspective to AI. Aria is a tool that enables research in spatial, contextual, and ethical areas, and it enables research across disciplines like mapping, robotics, health, accessibility, and cognitive science. The research community is making astounding progress on bringing the human perspective to AI, one benchmark data set and one publication at a time, and things are adding up rapidly. To date, we have over 380 research laboratories across the world using Aria for robotics research, social and contextual AI research, and spatial AI research. 328 papers have cited Project Aria or Meta's Aria datasets, and partners have produced and open sourced more than 30 egocentric datasets developed with Project Aria. This is just a subset of those. It's getting difficult for me to represent these things on a single slide at this point. So the Aria program started in 2020, and we're now on our second generation of the device. Academic and commercial researchers applied to use Aria with the application form on our website, which you can access using the QR code that you see on the right. And we still have a lot of researchers using Aria Gen 1. We're now fully migrating the program over to Aria Gen 2. And I'll explain exactly what that means at this point in time. So number one, we're no longer taking Gen 1 proposals. We haven't been for a while. We encourage anybody that wants to use Aria to submit an application that will be for Aria Gen 2. And Aria Research Kit is ready for full-scale research activities with Aria Gen 2 across all major functional areas of the kit. We've begun providing Gen 2 devices, and we are processing our large backlog of Gen 2 proposals. So thank you for folks that have applied and who we have not moved forward yet. We're getting to our backlog. And we'll soon send a notice to recall Gen 1 devices. Generally, we're trying to do that by the end of 2026. That's not a super hard rule. We're going to have an exemption process. That means we will not interrupt your research if you have Gen 1 today and you're continuing along. We're just going to try to do it by the end of 26 if it's possible for you. Okay, now let's dive into Aria Research Kit, and I'm going to talk about what's possible with the Research Kit and some new updates with the Research Kit. So Aria Research Kit is comprised of the Aria device, that's obvious. It's also comprised of machine perception algorithms and a set of tools that work on your phone and your PC that help you use the Aria device. And there are two primary use cases we've seen our community adopt with Aria Research Kit. The first is egocentric data recording and preparation for model training, benchmarking, and open sourcing. So this is the development of data sets. And the second is the development of interactive prototypes. And these are usually proof of concepts or live model testing prototypes. So now let's walk through each of those major functional areas. I'll talk about the device in detail. So to start off with, I'll have a look at the sensor suite. And Aria contains a 12 megapixel RGB camera, 4 high dynamic range grayscale cameras that capture a broad field of view, eye tracking cameras, a GNSS for global positioning, IMUs for inertial tracking, 7 spatialized microphones, a contact microphone that can isolate the wearer's voice, a time alignment radio for multiple devices working along the same time scale, a PPG sensor for heart rate estimation, and an array of other specialized sensors. The glasses also have several input and output mechanisms for interactivity. There is an open ear stereo speaker for text-to-speech or other programmable audio. There's a programmable action button that can be used for real-time prototypes and to start recording and streaming sessions. And there's a way to easily connect an audio source via Bluetooth. For example, you could even play music on the device. The device is packed with compute capability, including a Qualcomm AR1 Gen 1 chipset, and we utilize that for the majority of the on-device logic, which you could imagine you may utilize in the future for the development of on-device applications. And Meta's own custom coprocessor that enables ultra-low power computing critically for Gen 2 on-device machine perception that can happen in real time. We have 4 special computer vision cameras for very wide field of view applications. The front-facing CV cameras form a stereo pair with significant overlap that enables off-device depth reconstruction of a scene. And I'll show an example of that right now. The stereo overlap enables us to achieve depth perception when paired with a model such as NVIDIA's Foundation Stereo. And here we see the results of a pipeline running Foundation Stereo optimized for Gen 2 sensors, with our RGB camera data reprojected into the depth output for a sort of colored picture of the depth. And we also have rendered the ARIA wearer's trajectory and the estimated body pose in a third-person view, just for some context here. And we invest a lot in sensor calibration, both at the individual level and across sensors. Here you can see calibration stations for the computer vision and RGB camera, the microphone and speaker, and our eye tracking cameras. Calibration is fundamental to sensor performance, and especially when you're dealing with multimodal sensor fusion. So now let's look at another way that we make things extremely accurate on the device. These are pictures of a timing measurement tool showing 2 devices stacked on top of each other. And again, I mentioned we have a special radio that facilitates the transmission of recording timestamps between the devices. And this is showing how accurately we can achieve sub 10 microsecond time alignment between devices. Now, why does this matter? Well, when you really zoom in space and time, and we've slowed down and taken a small crop of sections of recordings on 2 different devices, top row is one device, bottom row is another device. The left column shows without time alignment. You can see when you really zoom in space and time, things get quite sloppy, even if you do your best to manually align things with best practices. And with the sub-gigahertz radio that enables time alignment, we can see much, much more accurate time-aligned multi-view recordings. Here's a view of our high dynamic range RGB and CV cameras that make it easy to work with ARIA Gen 2 in dynamic lighting conditions. And this CV camera sensor features 4.6 micrometer pixels in a 512 by 512 array. It enables single frame, single exposure high dynamic range imaging with a dynamic range capable of 110 decibels. And now I want to talk about a new capability that's available in ARIA. We are enabling ARIA to remote stream over the internet, and we're really excited to release this capability. We have a few ways that we enable this. This will be available in the Q3 timeframe, and you'll be able to stream ARIA data over the internet, both in a true peer-to-peer fashion, and that'll be an extremely low latency sort of means of working with streaming. And then we'll also enable this via a relay over the open internet. You can imagine streaming, let's say, from here in Denver to Seattle to Europe, and you can enable long distance streaming applications. Now, why does this matter? Well, the motivation for this, I'll just go back to something that Dima said, which was, I hope that ego data isn't only used for robotics. We have another application to show you.
A straight length of rope with one end visible. Good. The next step is make a loop with the end by passing the end over on top of the rope.
Should I use the right end?
Yes. Bring the right end over the standing part so it lies on top. Good. The next step is push the end under the rope to make a second loop. Good. The next step is push the end through the first loop.
I'm going to barge in here. You actually want that to be on the loop on the right, not the loop on the left. This one? Yep, perfect. I'll hand it back over to the AI.
Now, pull both ends gently until the knot is snug and neat. Good. Done.
Thank you.
Okay, so what did I show here? This was a case where we had somebody wearing ARIA, performing a task, and an AI assistant was helping them. But the AI assistant didn't quite solve the problem in helping them out. And so we had a remote expert to whom this data was being streamed live in real time in a remote location, barging in, overriding the AI expert, and providing the right instruction. And this kind of data we believe is critical for AI assistant reinforcement learning and post-training. And so we're really excited to engage you all as a community and say maybe the next egocentric data set is a data set like this that can be used for benchmarking AI assistants or for training models like this. I know we have folks in this room that have done work in this area. So looking forward to releasing that to you all. Okay, now I want to shift gears and talk about machine perception, sort of another core pillar of the research kit. And machine perception turns raw egocentric sensor data into what we can consider the primitives of the human perspective. And today we provide out-of-the-box machine perception for slam trajectory and mapping, hand tracking, and eye gaze. And these are what you could consider the fundamental building blocks that enable an algorithm to understand where the wearer is, what's surrounding them, what they are focused on, and how they are interacting with their environment. This is a snippet from the Hot 3D dataset that shows these all coming together in one single scene. And then I'm going to break down each of these individually. This is perhaps my favorite all-time animation. This is a view of our per sequence pose estimation, which leverages a proprietary visual inertial SLAM system. It's been built for Meta's products, and it combines a VIO front end with a large-scale capable mapping back end. It contains both causally computed open-loop odometry and loop-closed and globally optimized trajectory calculation. And you can expect 0.2% to 0.4% metric translation error under typical conditions, and up to 1.5 centimeter global RMS error in large environments. And this is being run in a funicular, like a tram going down a hill in Zurich City Center. And this was done by ETH Zurich as part of their Lamaria data set. I think it's one of the most stunning examples of the SLAM system running, and I'm really proud to have partnered with ETH on this. Switch slides here. We also have a multi-trajectory SLAM algorithm, multi-sequence trajectory SLAM algorithm, which aligns and jointly bundle adjusts multiple recordings that overlap in space. And this is really important for longitudinal studies, maybe building up a map and seeing how a map changes over a long time frame. This is an example of one of the Meta buildings being built up over, I believe, months of recordings. Okay, now I'll switch gears to talk about hand tracking. ARIA Research Kit provides 21 joint hand tracking, and the hand tracking algorithm utilizes our wide field of view computer vision cameras. And we've most recently made some pretty interesting improvements to significantly reduce hand stealing. This is a false positive of a hand tracking algorithm. So this is where, I'm wearing ARIA and I'm watching somebody else who's in front of me and their hands are in view, and my device accidentally picks up their hands as my hands. That's called quote unquote hand stealing. So we've recently released a version of the algorithm that eliminates this hand stealing problem or greatly reduces it. So for those that are using ARIA today, please have a look at our latest hand tracking algorithms released on MPS and give that a shot. And then one more thing I want to show you all is related to our eye tracking capabilities. I want to show you how eye tracking can enable gaze object interaction. And this is just an example of a quick demo that we mocked up to show you how you can start to sort of see objects over time. I'm going to just play this, and there's audio again, so you can hear something.
What am I looking at?
You're looking at a teal metal stool with 4 legs.
You can see the gaze projected in the RGB frame on the left as the red point.
Now you're looking at a red can of Coca-Cola on a table.
I'm just using an agent to identify when
That's a tablet device lying on the table with its screen on.
an object is seen.
What is this drink?
It looks like a can of Fresca, a citrus-flavored soda.
So you can imagine how you can use real-time machine perception to develop prototypes like this, build data sets from them,
Did you see
even
a
test
napkin in
things
the
in
room?
real time.
Yeah.
All right. Now I want to move on to tools. This is, again, how you can use ARIA with different companion tools. The first is the companion app. This runs on your phone or your tablet. And you can pair glasses and manage recordings with the app. It really operates like your remote control for your device. It enables you to take ARIA away from your desk and into your research environment. You can manage your recordings, adjust sensors and algorithms, and you can even see a streaming preview of your recording, confirm it is seeing the right range that you think it should see, for example. And then we have ARIA Studio, which has recently been updated, and it enables you to run both Gen 1 and Gen 2 glasses through Studio now. The other things that are new in Studio for those that may have not used it recently is you can now even record and stream directly from ARIA Studio. So you can plug in your device, and just on a desktop application, you can very simply start streaming, and you can see live output from the device without ever writing a line of code or opening a terminal. Here we can see a stream. Yeah. There's also an SDK that's a comprehensive toolbox designed to facilitate control and interaction with ARIA devices. So everything you saw on the app or in Studio, of course, you can do programmatically with the SDK. It's more feature-rich and functional. You can do device management, streaming support, recording. We have Python and CLI tools and a bunch of example code. But of course, that requires coding. Project ARIA Tools is a tool set that enables you to work with ARIA data, but all of this requires coding, and who actually codes anymore? So now you can access all this functionality directly from your favorite agent. And we've open source plugins for Claude, Codex, and Gemini that are optimized to enable you to easily interact with ARIA Research Kit directly with natural language. These skills provide pointers to our documentation. They provide your agents with clear direction on how to best utilize our tooling to accomplish your goals. And what you see here is actually just a very natural exploration process of opening up Claude Code and saying, hey, what can I do with ARIA? Oh, I can do a recording? Oh, okay, let me do a recording. Let's do a 30-second recording. Oh, can I visualize that? Hey, I heard there are some annotations that I can produce. I can produce hand tracking annotation. Let's check that out. Let's visualize. So it's really just, using an agent to lead you through the process. And we provided all the right context through these skills to make it very natural to interact in this way. So these are available on GitHub. Really encourage folks to experiment with them. Of course, we keep the ability to anonymize data and data privacy central to our program, and we continue our research on EgoBlur, which is the model that we provide for folks to anonymize their data. This is available with ARIA Gen 2 now. It's fully functional with ARIA Gen 2. So you can check that out and use that for your data set creation. So now I want to talk a little bit about how we share our research with you. We have a whole program around taking research that we do in our organization with the device and making it available broadly to anyone that either has ARIA or does not have ARIA. And these data sets and models are available to folks. We have them all on our website. The first that I want to talk about, which you may have heard Jacob talk about earlier today, is that we've made a major update to the original Nymeria dataset, now called Nymeria Plus. And Nymeria is an expansive egocentric dataset designed to push the boundaries of human-centric AI. Building on the success of the original 2024 release, Nymeria Plus is a major evolution focused on precision, compatibility, and dense scene context. The updated release delivers significantly optimized body motion, and it introduces a semantic layer through thousands of 3D and 2D bounding boxes and 3D object meshes. And it's complete with 47 entirely new recordings and 600 plus hours of additional data. So check out Nymeria Plus and see how it can work for any of your egocentric sort of body pose oriented research. Also, we've enabled or we've released a pipeline with NVIDIA, basically that works on NVIDIA's foundation stereo model, and it enables ARIA to become a metric depth sensing system. And we leverage foundation stereo alongside our own VIO system running on device to provide metric online calibration of the stereo cameras. And then we can produce very high accuracy depth data in real time. So check that out. These are just some examples you can see in the beginning comparing with some of our SLAM data. Very, very accurate depth has been achieved. And then something really interesting, we use Unity sometimes internally as a prototyping tool, and thought it'd be really interesting to open source the SDK that we've built to interoperate with Unity to the community. So we've done that. And actually, it should be released within the next couple of weeks. We're in the final stages. But basically, if you have a Unity project, you can take ARIA's sensor streams and stream them into your Unity project. So you can imagine you might have a digital twin application where you're in a room and you have a digital twin of the environment. You could stream the data in directly into Unity if you represent the digital twin in Unity, for example. All right. One more that we've open sourced, which you can see at our booth also, is we recently announced Boxer, which is a new lightweight and modular model designed to lift open world 2D bounding boxes into high precision metric 3D oriented bounding boxes. And that enables just more detailed annotation of objects in 3D space. We're really excited about this. This has really taken off in the community, and people have applied it also to non-ARIA recordings. Daniel is over here and will be at the booth as well. He's done the research here. So yeah, really excited about this release. And then we have many more data sets and models. I can't go into all of them in detail in the time that we have here, but we basically have research on objects and environments. So we have ARIA Digital Twin, ARIA Synthetic Environments, the Digital Twin Catalog, and Shaper. And then we have ARIA data sets and models that are focused on mostly people and environments, roughly speaking. And these are the ARIA Gen 2 pilot dataset, the ARIA Everyday Activities dataset, the Hot 3D dataset, and the Reading in the Wild dataset. So that's our offering. Now, what's next? Just as your takeaway, you can download the datasets and models that I just talked about using the QR code on the left. In the middle, you can apply for the ARIA Research Kit. And again, if you have ARIA Gen 1, you want to move on to ARIA Gen 2 as a research device, again, reapply. We're processing those proposals. That's on me to process a backlog. I'm getting to these as quickly as I can. And then also sign up for the ARIA newsletter. And you can get the latest announcements that we have as we make those available. Maddie does that newsletter. So thank you for your time. I can answer any questions that folks have and appreciate your attention at this late time of the day.